Does anyone know what those sounds were? It wasn't a sound check from AV. What was it? Somebody said Sputnik? Sputnik. Those were the sounds of Sputnik as it circled the globe in 1957, October. It scared the bejeebies out of the United States. And one of the consequences of Sputnik was the creation of an agency called DARPA, the Defense Advanced Research Projects Agency, which for 50 years has had consistent track record of breakthrough innovations. The reason I'm talking about DARPA is because the DNA of DARPA is in ATAP, the Advanced Technology and Projects Group. Now, unlike DARPA, ATAP is not a response to a crisis. ATAP is a response to an opportunity. And Project Ara shares and demonstrates the essence of the ATAP DARPA innovation model, challenging conventional worldview of what's possible and challenging it not truculently, not rashly, but thoughtfully and fully understanding the risks involved when you go about trying to create breakthrough technologies. Now, when Paul first proposed Project Ara, the idea of a modular phone, they told him he was nuts. They rejected the idea and said most of the people who create phones this way said that's not possible, it's impossible, because you're going to pay a size, weight, cost, power penalty. And from their point of view, mic down, end of story, that's it. You don't build phones this way. But what the ATAP DARPA model of innovation teaches you to do and say is, okay, got it. We're going to pay a size, cost, weight, and power penalty, but how much? Is it 10%? Is it 25% of a penalty? Is it a 50% penalty? And more importantly, what it teaches you to then ask is, if I'm willing to pay that penalty, what new things can I do that I couldn't do before or that I can't do today? Those of you in this room here today and everybody else joining us online, you are the ones who are going to answer that question. What is it that we're going to be able to do that we can't do today? You are going to do it by the modules that you develop and field, by the modules you create. You. Now, it's not going to be without frustration. It's not going to be without elation. It's not going to be without a lot of hard work. But it's you that are going to make that happen and answer that question. And in the coming weeks, months of Project Ara, what we'll begin to see is going from that impossible to maybe just improbable. And like many other breakthrough technologies, eventually, simply as inevitable. So let's get started. And I'd like to introduce Paul, who's been leading this all along. Thank you.
Thanks very much, Ken. Good morning. This photograph by John Stanmeyer of National Geographic depicts migrant workers on a beach in Djibouti trying to catch a cell phone signal from neighboring Somalia. It is aptly titled Signal. It is a stark reminder that the vast majority of humanity does not share in our luxury of ubiquitous access to the mobile internet. we forget that it's relatively new, even in the developed world. But worldwide, only 1 billion of the 7 billion people on Earth have smartphones. Another 5 billion are feature phone users, and another billion are not connected at all. And yet, even this relatively light level of penetration has changed the world. It's changed political regimes. It's changed the way we work, the way we learn, the way we socialize. If you were to imagine a smartphone for the next 5 billion people, what would it look like? It would be inexpensive. It would be easy to use. It would be highly configurable to suit demographics, geographies, usage patterns, and individual preferences. And it would be aesthetically custom. Now think about what else fits that pattern. The only two things I can come up with are food and clothing. So we want to give it a shot and see if we can make a smartphone like that. Now, how many of you know what this is? I see a show of hands. Anyone? Anyone? So it's not fireworks. It is a static snapshot of a beautiful visualization of Linux kernel development over 2 decades. It shows the growing structure of the Git repository and the names of the developers who contributed it over the years. You should look it up on YouTube. It's beautiful. And remember, this is the kernel that underlies Android, that runs on most of those 1 billion smartphones that are out there today. So software development is perhaps the best example of a pure meritocracy that's out there today. The economic barrier to entry is almost zero. It's modular, so many people can work on it on independent pieces of projects at once. There are minimal capital costs, the tools are free, and the merits of your work can be assessed almost instantaneously by compiling and running the product. Don't you wish we could do that for hardware? Oh, wait, we can. Early integrated circuit design was very much the way other engineering systems are designed today. There were a lot of heuristics, a lot of sweat, then it was built, and then you repeated that whole process over and over again. And so the image of the early Intel 8008 very much depicts that paradigm in a graphical fashion. By the early 1980s, the inexorable march of complexity that is Moore's law proved that this was not a scalable model. Enter Mead and Conway. The subsequent 3 decades of VLSI design have been based on 3 basic tenets: abstraction, modularity, and simulation. Effectively, this meant giving up optimality in exchange for time and verifiability, and the ability to compile the system quickly to see if it would work. It also had the effect of lowering the barrier to entry, the barrier to participation in the ecosystem, and opening the floodgates of innovation. Suddenly, there were thousands of fabless designers, and in large measure, this made the first wave of Silicon Valley. And again, you can see this starkly in the evolution from the 8008 to the 386 to the Pentium processor. You can see the modularity. Now, we want to make the smartphone hardware ecosystem more like the software ecosystem that underpins Android. On this plot, you see average new product development timeline in months on the vertical axis, and a measure of the effective number of competitors in a particular market on the horizontal axis. The measure of that is something called the Herfindahl-Hirschman Index, which is something the Justice Department uses to measure antitrust, to measure market concentration for antitrust purposes. So you see, somewhat unsurprisingly, somewhat intuitively, that product development timelines are shorter in more competitive markets. There's a software trend line and a hardware trend line plotted here. And you see that hardware, also somewhat intuitively, takes longer to develop than does software. So what we want to do is we want to grow the size and the competitiveness of the hardware ecosystem, thereby reducing average time to market. And we want to make hardware design more like software design by lowering the barrier to entry and by deploying a new generation of tools that lets designers simulate the product that they're creating and lets them and make those tools free and open source. Now, you might wonder, why would I want thousands of cell phone designers? I have a smartphone in my pocket, and it seems perfectly good to me. And I would posit to you that the smartphone ecosystem is in its infancy. It's where automobiles were maybe in 1918 or thereabouts, when Henry Ford uttered that infamous statement, "You can have it in any color so long as it's black." What we have seen subsequent to 1918 is the adoption of automobiles by the makers, the DIY enthusiasts, the people that are willing to hack the platform and explore new features, and the integration of customization, both functional and aesthetic customization, into mass market products. Today, approximately 25% of the value of an automobile is in user customizable options, both functional and aesthetic. And we want to make that trajectory real in the smartphone world as well. So last summer, we did something called Make with Moto. You'll see an item on the agenda for tomorrow titled Make with Moto Showcase, where you can see some of the products of that. But basically what it was an open hardware platform, a hackable version of an existing phone that we loaded up on a truck full of state-of-the-art 3D printing and other rapid prototyping equipment, traveled around the country, visited 15 colleges, 4 maker fairs, and a variety of other events, corporate, individual, and otherwise, and held makeathons in a 48-hour format. And we wanted to see what would the ecosystem produce around an open hardware platform. Our purpose wasn't to productize. Our purpose wasn't necessarily to make modules. Our purpose was simply to explore what kinds of things people would create. It was an existence proof, if you will. And we discovered 2 very interesting things. There were 2 modes, if you will, among the projects that emerged from that pilot activity. One was around medical devices and the devices that enable accessibility for cell phones. The other one was around personal transportation, things that pertain to driving, skateboarding, bicycling, etc. And so to us, those were existence proofs of a vibrant and untapped ecosystem of things that today can't make it on a mainline cell phone product as a feature. So we want to enable that. In essence, we want to take that power user customization, scale it, and deploy to the mass market. Deploy to 6 billion consumers around the world. Now, we also looked at what is the value to the consumer of customization? Is it just a fad, a superficial fad? Or is it something that has tangible economic value? And so what you see on the plot in front of you is on the vertical axis perceived value. It's measured by willingness to pay, which is one of the many economic measures of perceived value. On the horizontal axis is the dimensionality of the option space, if you will, which is the number of different categories of choice that a consumer can make. So it basically corresponds in the Chipotle model to the number of stations that you have at which you have to make a choice. And so we've tried to parameterize a variety of different products that have some aspects of customization on those 2 axes. And you see some of those examples there. In the limit of the dimensionality of the option space is the ability to make something that is completely unique, that has infinite dimensionality of the option space. It's irreproducible. And so you see that there are, the vertical axis is logarithmic, so there are a couple of orders of magnitude across a wide range of products that increase the value of that product to the consumer, and that value accrues due to the customization aspects of that device. I would particularly draw your attention to the IBM System 360. It was the first modular peripheral computer system, and up to 4x of the value of the base system came from peripheral substitution. Now, why doesn't that exist in cell phones today? And I want to explain why using 2 sort of canonical examples. One is the B-52, the Stratofortress. It's an airplane that entered service with the United States Air Force in 1955. It's an airplane that's in service today and it's an airplane that will continue to serve for several more decades. In essence, the lifetime of that platform is infinite. We don't know when that airplane will leave military service. Very few components. In fact, one might go so far as to say that virtually no component on that aircraft that flies today is the same component that was there in 1955. The entire system has been refreshed, ranging from the structure all the way to the electronics in the battle management system depicted on the slide. However, the morphology of the product is recognizably a B-52. It's not a different airplane. You can point to it and say, that is the same airplane that my grandfather might have flown. Second example is, again, the IBM System 360. Introduced in 1964, base configuration cost about $100,000 in then-year dollars. Typical installed configuration was in excess of $5 million. It was the first open peripheral modular computer system. So why doesn't this exist in smartphones? Smartphones have obvious affordances for modularity. They have Bluetooth, they have an audio jack, they have a USB port. Yet the size of this modular ecosystem around smartphones, things like credit card readers, things like headsets, and other kinds of things, is something like 7 or 8% of the overall value of the smartphone ecosystem. It's anemic in relative terms. And the question is why? And I would argue to you that there are 3 reasons. The first is that the morphology of the device doesn't stay constant. You hang this Christmas tree of stuff around the device. Things that hang with wires, things that are wirelessly tethered, but have to have their own power source. You either drag a charging unit or you drag another cable. The second reason is that there's an anemic ecosystem of third-party suppliers. The OEMs do not encourage and groom the modular ecosystem around smartphones. So the question, we asked ourselves the question, as Ken said, what would it take? What do the numbers say? What would a modular device with a constant morphology and a broad range of substitutable components so that everything in the device can be substituted, what would that look like, and what would the modular overhead be? So what you see in the table in front of you are 2 variants. An FPGA variant, something that we could build relatively quickly, and one based on ASICs, application-specific integrated circuits, or custom chips to instantiate those field programmable gate arrays. And you see that the FPGA variant is, sporty, kind of large. Over half power penalty, very significant volume and weight penalties as well. However, taking that to a custom variant with custom ASICs, we can shrink the modularity penalty down to about 1/4 of the size, weight, and power consumption as compared to a traditional tightly integrated device. And so we asked, okay, 1/4, is that good enough? Do we think that consumers will be willing to accept that in exchange for having access to functional as well as aesthetic customization? And you'll see in a separate presentation tomorrow that details our consumer research to date. But the short answer was, we think so. And so maybe we have a program. So the Project Ara program objectives align to the 2 strategic goals that I outlined, which is to deliver the mobile internet to the next 5 billion people and to make the hardware ecosystem more like the software app ecosystem in the pace and level of innovation. Those 2 strategic objectives translate to 3 measurable things that we're trying to execute on in the program. The first one is an order of magnitude increase in the consumer perceived value of the device. That doesn't mean that we want to charge 10 times more for the device. In fact, if anything, we want to charge less. But we want the consumer to have a perceived affinity for it that's an order of magnitude higher as measured by willingness to pay. In order to do that, we want to compose the device out of an interchangeable set of functional modules. We want to make the exterior of the device aesthetically expressive. And we want to afford the user a co-creative user experience. This is what Harvard Business Review has called the IKEA effect. If you actually participate in making something, you have about a 2 to 3 factor increase in affinity for the final product. Cost. We want to be able to configure a device for 5 billion people, for the next 5 billion people. That means the device has to be priced at the crossover point of existing feature phones. So we're driving the bill of material cost, and it's very important to note that I'm talking about bill of material costs. I have nothing to say about how the device will necessarily be priced. That's something we have to figure out downstream. A bill of material cost of $50. Now, how is that possible? That is what we call the gray phone. That's a very simple device. It's an entry-level device that has a display, it has an application processor, it has a Wi-Fi connection, it has a battery. That's it. That's enough to find a Wi-Fi hotspot, to run the Ara configurator, and to be able to upgrade the device and configure that device functionally and aesthetically. Of course, we also want to be able to support deluxe $500 plus kind of configurations, bill of material cost configurations off of a common platform. And we want the user experience to be universal, something that the mass market in the developed and developing worlds can get behind and use. We want to allow people to do incremental feature evolution in that price regime, in that order of magnitude of bill of material costs from $50 to $500, as opposed to buying your entry-level feature phone and then a smartphone and then a better smartphone and then an iPhone and having to throw them away. We want to afford the consumer the ability to make very fine-grained steps through that value chain. They can save up for the next module. The device can evolve with them on the same platform over their own life and their own evolution up the socioeconomic ladder. To that end, we want to keep the platform stable and the lifetime of a platform to have several traditional generations of device refresh in it, and of course to make it backwards compatible. And last but not least, to the point of making the hardware ecosystem more like the software ecosystem, we want to compress the development timelines for new technologies, for the introduction of your new technology into the smartphone market by about 5x. We want to get at least 10 to the third, order of 10 to the third competitors into the module developer ecosystem. We want to trivialize the barrier to entry, make it more like software, make it more like downloading an open source compiler. And we want to reduce the design build iteration, let people do virtual prototyping, let people do multi-domain physics analysis of their modules long before they ever have to build them. So those are the Ara program objectives. The program is structured in an analogous way, I should say, to the way the market, the ecosystem would operate. It's a two-sided market between developers and consumers. It's very much the App Store model. On the right side are developers, module developers. That's you guys. As well as developers of shellmaker apps, and I'll talk about those a little bit later. On the left side are consumers, and Google is in the middle. We are the facilitator of this two-sided market ecosystem. We specify the platform, and we provide a user experience. Now, there's one small detail. Hardware is different than software. You got to manufacture it. Software is just an act of copying. So there's a manufacturing block. And I'll tell you about what we're doing in direct digital manufacturing to enable us to create one-off devices efficiently. So let me start with the platform. Most of you have seen this. The very first thing we had to do was create an industrial design. We think it's beautiful, but it's for the market to decide. It's for you guys as well as the consumers to decide. The industrial design allows modularity on the front and the back of the device. It affords 3 different variants, with the medium variant being the default or the preferred variant. It'll be the first one that we focus our development efforts on. But we would like to allow a mini variant as well as a large variant. And you'll hear more this afternoon about exactly how these came about and the parceling schemes that underlies them. The parceling scheme is key. The parceling scheme is what maintains platform stability. So we commit to 3 different types of rear-facing modules, a slightly more complex ecosystem of front-facing modules, a basic Ara building block, a 1x1 module, what we call, is 20 by 20 millimeters, 1x2, 20 by 40, a little bit in excess of that, and a 2x2 is 40 by 40, a little bit over that because you have to lose the rib. So those are the form factors, and we will keep those form factors stable so that you can develop against them. Now, not all modules fit into exactly that. The footprint in the parceling scheme stays constant, but we do allow exceedances, or the expansion of the design language, subject to a few basic tenets, a few basic rules or grammars, if you will, in our design language. And those are articulated in the MDK, and you'll hear our lead industrial designer describe them in some detail this afternoon. From a color, material, and finish perspective, there's a spectrum. Basically, you should be able to create, the user should be able to create his or her own phone that is not just custom, it's not just unique, but it's actually expressive. It can tell a story. It can be a reflection of them. It can be the kind of thing that you put on a table at dinner, and the first 10, 15 minutes of dinner can be a conversation about why does that look the way that it does. So we're relying on 3D printing, an emerging technology, one that has never been applied, to the best of my knowledge anyway, in a mass market consumer-facing application. And we want to, there's a variety, the industrial design language supports a variety of color, material, and finishes, or CMF for short, that range from celebrating the 3D printed aspects of our modules to concealing the 3D printing. Either making the 3D printing look like something else, like polycarbonate or some material that you're familiar with and consumers are familiar with, or even using non-3D printed materials in some cases. Mechanical configuration, you'll hear a lot more about this as the Developers Conference progresses. But the device, in essence, consists of an endoskeleton that is the physical instantiation of the platform. That is where the modules come together. That is what we will supply. We, Google, will supply. And a set of modules. We have strived in trying to make the industrial design something that isn't blocky, that isn't Lego-like, that overcomes the visceral association that many people have with modularity as being something that's bulky, something that's unfriendly, not sleek. And we have maintained a rigorous focus in the mechanical and industrial design on a beautiful, pebble-like, sleek, almost watertight appearance to all of the modules. And so a lot of the mechanical configuration choices that you see flow from that value, that industrial design value. Now, they usually also have functional features, as most good designs do. So, for instance, the modules, as all of you have probably seen in the press, the modules are held in the lateral direction using an electropermanent magnet technology. It's a magnet that has an on state and an off state, and is passive in both of those states and requires a short voltage pulse in order to be able to switch between them. It's not a technology that we invented. It's a technology that exists today in industrial applications. But this will be the first time that an electropermanent magnet is miniaturized to this scale and used in a consumer-facing application. The electropermanent magnet allows us to avoid connectors, latches, and other kinds of bulky things that ruin the sleekness of the design and the signature experience of the end user. Additionally, we made a strategic choice to use contactless data interconnects for the modules. This, again, allows us to maintain the sleek, watertight appearance, pebble-like appearance of the modules. It also allows for increased longevity, reduced wear and tear on any sort of connector. And it also actually ends up saving significant amounts of real estate within the module, of printed circuit board real estate within the module, versus a traditional connector. A little more on the contactless data interconnect. It's a technology that is not in the 0.1 MDK release that you all have undoubtedly seen. It's a technology that we're maturing in parallel and that we're going to spin into probably the 0.15 release of the MDK. And you'll see more detail on that as the conference progresses. So we're in the process of doing trade studies, and you see a dev board depicted there on the right of the contactless data interconnect. And we're making sure that it functions across the full range of data throughputs and associated frequencies across that interconnect. Now, one of the key aspects, of course, of modularity is the on-device network. It's interesting. A lot of people say, oh, you know, a packet switch data bus on device is unheard of in the mobile arena, which I think is ironic because it's bracketed on both ends. We use data buses and modularity at the chip level, as I talked about. We use data buses that are fairly modular and allow plug and play to some extent at vehicle level, in satellites, in automobiles, and other kinds of things. Yet, in traditional cell phones, everything hangs off the application processor using a dozen or more different interface standards with frequently bespoke implementations of those interface standards. So we think there's no systematic or philosophical reason why we can't have a universal packet-switched on-device network. And so we've settled on the MIPI Unipro protocol stack for that on-device network. You'll hear from MIPI this afternoon more details on Unipro. But it's basically a nice modern standard. It's very lightweight. It doesn't have a lot of legacy stuff in it, and it underlies layer 2 through 4 architecture for a variety of other MIPI standards that are already on the drawing boards and are already permeating the ecosystem. So depicted here is our Gen 1 on-device network architecture. This is what's in the current release of the MDK, the 0.1 release of the MDK. And it aims to demonstrate Unipro, pure and simple. That is the #1 goal of this first release of the MDK. We saw that as the biggest risk, and this MDK release, this platform, and the associated prototypes retire that risk. The way the architecture works is it currently employs tunneling of a variety of native protocols, DSI, SDIO, I2C, GPIO, and tunnels those protocols over a Unipro network. That Unipro network, in the near term, utilizes an LVDS layer 1. So that's an 800 megabit protocol. It is not the protocol that we envisioned for the objective system, and it is not the protocol that Unipro was designed to operate over. But it's something that we could do quickly, and it's something that we could do in FPGA. So those tunnels are implemented at an FPGA bridges that reside on each module. That's the 60% overhead per module that you saw in the FPGA variant. This is probably not something that you would go to market with for most modules, but this is something that you can get started developing on. Tunneling by its very nature requires a corresponding source and a corresponding endpoint. So unfortunately, this introduces a degree of coupling between the application processor and the peripheral modules or the endpoints, such that there has to be a one-for-one correspondence between ports on the AP and modules. This is not a desirable end state. We want to a truly modular system decouples the modules to the maximum extent possible. So the Gen 2 network architecture, for which we're aiming in September, makes a variety of improvements. So first, it introduces the M5 physical layer. This allows us to get 10 gigabits of throughput to most modules with a couple microseconds of latency, and 20 gigabits to the larger modules, which have two interface blocks. It also replaces the tunneling architecture with what we call remote host controllers. And that concept will be explained further throughout the conference, and particularly in this afternoon's MDK walkthrough. But in essence, what the remote host controllers allow you to do is it alleviates the requirement to match ports on the application processor. In fact, the application processor is interfaced using some generic bus interface, something like a wide parallel bus or an HSIC interface. And that need not correlate to the endpoint protocols, meaning that the endpoint can be anything. It can be GPIO, I2C, SDIO, et cetera. And we are working with Toshiba and happy to invite other partners to the party on instantiating a series of ASICs that bridge UniPro to native peripheral standards. We're also instantiating a UniPro switch, which in the previous slide was still an FPGA, as an ASIC, as an application-specific IC that's much smaller and has relatively low power consumption. Now, we hope that the world is not always so. Our gamble, our hope, our aspiration, and we hope inevitability is that UniPro becomes ubiquitous. It's an open standard. As I mentioned, it's a very nice, clean, fairly legacy-free standard. And so we want to precipitate UniPro adoption as a native interface in a wide range of peripherals, including displays, including cameras, application processors. Now, there will be certain things, very lightweight peripheral devices, that will never become UniPro native. These are the kinds of things that speak I2C or UART today. And so for those devices, we will ensure that there is availability of general purpose UniPro bridges in the marketplace that bridge those lightweight protocols, to UniPro. So this is the worldview in 2015, when many peripheral vendors, hardware vendors already have UniPro on the roadmap, and we hope to precipitate the emergence of that sooner and more prolifically than is already planned. So I want to talk very briefly. Again, this will be the subject of a whole brief this afternoon about the software stack, because many of you are probably wondering, and I've seen the comments online that say, well, Android can't do this. How is this going to work? And indeed, Android does not support dynamic hardware configurations today. The good news is that we're Google. So our vision for the software architecture, this is not what's currently instantiated in the 0.1 release of the MDK, but the end vision for the software architecture is a set of generic class drivers, somewhat analogous to the way USB is treated today, a set of generic class drivers for UniPro devices. This is potentially a great thing to happen to Android. Today, one of the challenges that Android faces is this proliferation of different interface standards and off-spec implementations of a variety of those standards that then require a large number of very custom device drivers that are linked into the kernel, that operate at root privilege, and that compromise both the performance and the security of the system. So the introduction of generic class drivers is one would think a very desirable outcome. Now, there will be some peripheral specific functions. Not everything can subscribe to a generic class. And we aim to push those peripheral specific functions to user land so that a module developer can write a custom user land or user space driver for that module. That driver would be downloaded to the device, perhaps through an interface similar to Google Play. But that driver does not have to be linked into the kernel. So that's the general software stack plan. The near-term implementation of this, of course, is much less elegant, and that is you write a device driver and you compile it into the kernel, and it's there for your module. But we imagine deploying an initial version of this kind of architecture in conjunction with the 0.2 release of the MDK in the September-October timeframe. And we aspire to mainline this kind of feature set with Android by early next year. So a lot of you have also probably seen these pictures with one of the modules inserted backwards. And a lot of you have seen the industrial design models, and so I have to have something new to show, right? So what I have for you is the first form factor prototype of the phone. So if we could switch to the Elmo for a bit. Now, you should temper your applause. Could we switch to the Elmo view, please? Thank you. You should temper your applause first because you can't see it on the Elmo, but I'll wrap myself out anyway. The screen's broken. Good news is you can replace the screen module, but I don't have a replacement screen module. So we did crack the screen, and the phone doesn't quite boot. So we've brought up the network. We've tested a lot of the tunnels on dev boards because our first and foremost our goal was to make sure that the platform that we release to you actually works. Our second goal, of course, was, hey, can we build a form factor prototype? And so the form factor prototype, I'll open up some of the modules in a second. So hold your horses. So the first form factor prototype is of course something that we will show as soon as it works, but we haven't finished the bitcode porting from the dev boards to the first functional prototype. Maybe tomorrow, I'm told. Maybe tomorrow. So what you have here is a very similar looking device to the appearance models. You have the modules. I think this is, if I'm not mistaken, a Wi-Fi module. I'm going to open it up. There it is. I took the antenna out thoughtfully because it would fall out otherwise. So there's the antenna with a little connector. And what you see is the module shell. This is the aesthetically customized artifact. You see the antenna that would fit into the shell. And you see the safety shield covering the module and the two electropermanent magnets, the coils protruding. Now, the safety shield would normally, for purposes of being a safety shield, would obviously be soldered on to the module. For demonstration purposes, it is removable. And so there you have a Wi-Fi module. Now, a couple of interesting things to point out there. First are the spring pins. So those are the shiny things. Those are the shiny gold things. They are not the contactless pads. And one of the reasons that I mentioned we want to use a contactless data interconnect is so that those pins can go away and be replaced by, in essence, thin metallic layers on the bottom of the PCB, thereby opening up all of the PCB real estate on top of the device for your developer customizable content. So there are the spring pins. Then you have the two electropermanent magnets, and the reason there are two is to allow the 1x2 modules to be inserted either in the longitudinal or the transverse direction on the device. There. Then you have the FPGA. So that's the Lattice FPGA there that currently carries the Unipro stack and does all of the LVDS communications. And then you have a smattering of smaller discrete components there that constitute the EPM drive circuitry and the power management circuitry. And again, as we progress through the year, we're going to make custom ASICs to miniaturize a lot of that componentry, and of course take that FPGA into a significantly smaller form factor, something that's a couple millimeters on each side. And then on the far end here is the actual Wi-Fi baseband processor and the antenna connector, teeny little connector there. So that's the Wi-Fi module. Now let's do one more. So this is this is basically a module that does nothing. And the reason that we have a module that does nothing is basically to show you what you currently have to play with, which is about 40% of the real estate of the module. So this module is actually, it has an array of LEDs that just flash on and off, so not necessarily terribly useful. But you see that all of the unoccupied area of the PCB there is available for user customizable content. Let me assemble that one back. And what else? One more. Last one. This one doesn't have a safety shield, but should. This is the current application processor module. So it has a much beefier FPGA, you see. It has an SD card slot, just so that we have something to boot off of and for debugging purposes. And it also has the TI OMAP 4460 processor. The reason we chose the OMAP 4460 is it's extremely well documented. TI is extremely helpful in supporting the product, and there's a wide range of development hardware like the Panda board that's available for developer use. So we wanted this to be developer friendly more than anything else, above all else. And that's the AP module, and so that's what in the near term has to run your drivers on it for whatever module you create. So now one of the, of course, neat things, right, is I can take the Wi-Fi module out, and I can put on a pulse oximeter, right? So there's a pulse oximeter. It's a real pulse oximeter. You sort of put your finger there, and it measures your blood oxygen content and pulse rate using an infrared LED, and measures the reflectance. And it's also a real module. There's the user serviceability of the enclosures leaves something to be desired. And so you see the pulse oximetry circuitry there. And of course, it demonstrates one of the exceedances of the industrial design that allows you to span the vertical rib. Now, a lot of people have asked me, what is this, and why does your camera not fit? And it's because it's not actually a camera. It's a thermal imager. We did that for two reasons. One is we actually wanted to demonstrate a Z direction, a height direction exceedance to show what the industrial design would look like with that. It has traceability to some interesting camera optics, and also because it's a thermal imager, it's fairly low resolution, and it got us away from having to implement CSI right away. So that may be one of the more important reasons. So anyway, so that's the form factor prototype, and of course you'll see some demonstrations, hopefully, of the dev hardware associated with it that represents the various modules. You should be able to see an EPM demonstration of the EPM turning on and off throughout the rest of the conference, mostly tomorrow, because there's last minute code being written. And I wish I could make a phone call from stage and have my Steve Jobs moment, but I guess we'll save that for a future developers conference. All right, could we switch to the back to the slides? Wonderful. So that was a whirlwind overview of the platform, and the reason it was whirlwind, even though it is sort of the topic du jour, in fact, topic for both days, is because you'll hear about it all afternoon until you're bleary-eyed. So let me change gears a little bit and talk about design tools. So I mentioned the importance of design tools, and I think that many of you are familiar with the importance of design tools in both software and VLSI ecosystems. And so we hope to do something fairly radical in this domain as well. So just a little bit of history of hardware design. So you have two plots in front of you. They're from vastly different eras, but they're on the same axes. On the vertical axis is a number of ECRs, or engineering change requests. This is basically a way of tracking in large production programs redesigns. the number of times that something has to be changed in order to make it work with the rest of the system. On the horizontal axis is time, program duration. And so this is a plot of number of ECRs over the lifetime of a program. And on the left is the Mariner spacecraft from the 1960s. And on the right is a modern cyber electromechanical system. It's actually a radar system from Raytheon. So it's something that has a significant hardware component as well as some software. The Mariner had significantly more hardware than software. And the interesting thing to note is that even though the program duration is significantly longer, gotten significantly longer over time, and the number of ECRs is up by almost an order of actually about an order of magnitude, the general shape of the curve is about the same. And the shape of the curve suggests that most engineering changes actually occur quite late in the process. They occur during system integration and test. So the peak occurs about 3/4 of the way through the program, which is right around the time when it's most expensive to make changes in the system. And the reason that happens, and you see, by the way, the various fluctuations, right? So there's like a little sine wave on top of it. Those are builds, right? So those are prototype builds. As you weed out interactions and you're like, oh, this stuff doesn't fit. I got to change it, right? So, and then there's a slew of ECRs that accrue from that. And the pinnacle, if you will, of this mountain is when you do the first system test and you're like, oh my God, we have to do all this redesign, right? And so this is a fairly ubiquitous sort of phenomenon in hardware design, and in fact, here it is for a modern smartphone, and it's a slightly higher resolution there because we actually made the plot. And basically it adds up engineering changes from Jira, which is a software issue tracking system, from Windchill, which is the mechanical engineering change tracking system, and an electrical one. And so the orange curve is the total. And you see again the sort of very similar shape of the orange curve, and you see the modulation there that's happening as a consequence of prototype builds. And yet again, the last prototype build is when most engineering changes happen, right? So the question is there a way to remedy this? And is there a way to virtualize some of those prototype builds so that most of the engineering changes occur on a virtual prototype as opposed to on a physical prototype? And again, you'll see a recurring theme here. This happens in VLSI design. We no longer do build, test, it melts, or build, test, it doesn't work, redesign iterations, which we used to do in the early days of chip design. Today, the design is largely correct by construction. You send it to the foundry, and the first chip out of the foundry is reasonably guaranteed to work. And so the question is, can we replicate this process, raise the level of abstraction, and automatically design and verify the lower levels of abstraction that you see in VLSI design, and moving from transistor models to gate-level models to RTL, and now to reusable modular IP blocks in VLSI design? Can we replicate that at the system level? So this work has its vestiges in over a decade of DARPA projects, and you'll hear the opening talk tomorrow morning about the theory that underpins what we call the metamorphosis toolchain, which has its genesis in the DARPA META program and other programs before that one. And basically the idea is to create not a new design tool in and of itself, because a new design tool requires billions of dollars of investment and may or may not actually get adopted because people have their existing design tools and they like them. So the goal is instead to create a tool chain, something that allows us to integrate the semantics of the various existing domain-specific modeling languages. And what do I mean by domain-specific modeling languages? I mean things like SPICE, things like System C, things like Modelica. Can we create a semantic framework that allows us to take the domain-specific semantics and transform them into a common semantic domain, such that we can reason across all of these different physics domains? So we can think about the analog circuit, the digital circuit, the cycle-accurate software simulation of the firmware, the thermal emissivity of the various components, the RF regime. Can we reason about all of those things using common semantics? And in fact, can we go one step further? And can we prove things about the system? So rather than just simulating and doing time step simulation traces through the system design, can we actually apply formal methods and theorem provers and model checkers to say that a system will, for instance, under no circumstances enter a particular thermal state that may be hazardous to the consumer? These are things that exist in software. They exist at the bleeding edge of software. They get used for things like spacecraft software verification. And these are things that can exist in hardware if you have rigorous, formal, semantic representations of the system across the different physics domains. So that's what we're trying to do with the Metamorphosis toolchain. You will hear a talk about it first thing tomorrow morning, and then tomorrow afternoon you'll see demos of the actual tools. We will have an alpha release of those tools coming later this summer. The long pole in the tent isn't the tools themselves. The tools themselves are actually relatively stable, albeit not terribly easy to use yet. The long pole in the tent is the existence of the underlying models. And so what we're doing is taking all of the reference designs that you see associated with the MDK and future releases of the MDK, and making sure that you have rich simulation models in SPICE and Modelica and System C for all of the components there from which to be able to compose systems. And again, it's a critical mass problem. Just as in the two-sided market between consumers and developers, there is a critical mass inflection point when that two-sided ecosystem becomes feasible. There's a critical inflection point when the modeling ecosystem becomes feasible. There's enough critical mass of models that all it takes for designers to introduce a few more and continue to build that ecosystem and synthesize viable module designs. So that's Metamorphosis. Let me take a quick pause and remind people who are watching online that if you have questions, we will actually go to you first. You can tweet your questions at us, hashtag AraDev, or there's an internet relay chat room. The channel is called hashtag AraDevCon1, and it's hosted on the Freenode IRC server. There's a web interface for the IRC server, and there's a bunch of free clients available for it. Because the in-person audience is privileged to be able to interact with the development team for the duration of the 2 days, and the online audience is stuck with only these two mechanisms, we will take their questions first, although we will also take questions from the in-person audience. Okay, that was the intermission. So, the other developer-facing activity, which I won't spend a lot of time on because we have a whole developers conference planned toward this. So I want to flag it for everybody's attention and get it out there. Is what we call the 3D printed shell makers, the shell maker apps, and the API associated with those apps. So this is a very different developer community. You may know some of them, but these are the digital artists of the world, and what we want to be able to do is to create to make it easy for the mass market, the 6 billion people, the next 5, and the existing 1 billion, to be able to create something that, as I mentioned, is not just custom, is not just unique, but is actually expressive and interesting, and is somehow reflective of their personality and reflective of their lives. To that end, we have a very, very powerful tool. We have the first full-color production volume 3D printing engine that's being developed as part of this program. And we want to make access to those kinds of beautiful aesthetic artifacts as simple as possible for people. And so we're going to create, obviously, some canonical examples of things that allow you to, for instance, in the example that you see before you, take a Connect image, take a three-dimensional image of yourself, and transform it in interesting ways using what we call Physigram as a nod to Instagram, filters to create interesting designs. Or you can imagine saying, I love you, into a microphone, transcribing the voice pattern of that, and transforming that voice pattern into a beautiful, unique, and expressive design for the shells, for the module shells. In this particular case, it's a whole phone. This was an example from last summer. And so we will open up an API and a set of guidelines for how to create designs for 3D printing, things that we can instantiate in 3 dimensions, or at least 2.5 dimensions, and in full color using the 3D printing technology. And so that's yet another community of developers that we're trying to foment and seed, catalyze, and nurture. And we expect to have a developers conference for them in late July. Now, fulfillment. Just so you have a mental model, right, I'm just moving around that diagram that shows the different parts of the program. And so those were the 2 developer-facing activities, is the actual system platform and the ShellMaker apps. Now the fulfillment. So how do we get your modules to the consumer? So we have envisioned 3 different ways for an individual to be able to get an Ara phone. These need not be exhaustive. These are 3 orthogonal dimensions that we want to explore in the course of the Project Ara R&D effort. They can certainly be combined, and they can certainly are not to the exclusion of much more traditional channels of commerce for the modules. One of these is the gray phone. And I mentioned a $50 BOM goal. That's broken down there on the chart on the left portion of the slide as to how that might break out. These are some very notional numbers at this juncture, so don't hold me to them. But the idea is that a gray phone is something that could be shrink wrapped and that could be available at your local convenience store. You go and you buy your gray phone. There will be a very small number of variants of the gray phone. Again, to make this easy, this is not meant to be a choice, an exercise in choice. The exercise in choice happens once you get it. You fire up your gray phone, you run the Ara Configurator app, and you start purchasing modules from the marketplace, reconfiguring your device, upgrading various portions of the device, and creating new aesthetic shells. The gray phone is called the gray phone because it's meant to be a drab gray to invite people to customize, to aesthetically customize it, as well as to functionally configure it. The second canonical approach to getting an Ara phone is the peer-to-peer experience. For those of you who remember the Gmail, the original Gmail launch, just about 10 years ago to the month, I guess. It was by invitation only. You had to have a friend who invited you to get a Gmail account. And the reason we're interested in exploring that particular approach is that a lot of our consumer research has found that being able to navigate the choice space, the number of different functional choices and the number of different aesthetic choices that a consumer has to make about the phone is tricky business. It's the fact that the consumer's affinity for choice and affinity for customization, while when presented with that choice or the options for that customization, and getting extremely freaked out, it's called the paradox of choice, right? You want it, but then you're presented with it, and it causes undue stress. So one way that we're looking at resolving the paradox of choice is by ensuring that you're configuring your Ara phone on a friend's Ara phone, using friend mode in the configurator app. And that friend can then curate the experience and walk you through the experience and share their experience with the architecture. So that's the peer-to-peer fulfillment approach. And we're also experimenting with in-person, physical experiences, places where you might be able to touch Ara modules and actually engage in a tactile configuration process, whereby you can potentially play with real Ara modules or simulator modules that have a touch screen on their face, even rear-facing modules, and that can pretend to be and give you information about the kinds of modules that you're assembling your device from. So that's also an approach to tackling the paradox of choice. People have a very different tactile experience than they do interaction with a display. So those are the 3 canonical examples of UI experiences on which we're pulling. All of them rely on a common infrastructure. That common infrastructure includes a central fulfillment node that also is the back end for the Ara marketplace, as well as a number of forward fulfillment nodes distributed around the globe to enable people to get shells and more commonly used modules in a more responsive fashion. Those forward fulfillment nodes could also provide an in-person experience where the consumer could interact with some of the back-end processes, like view the actual 3D printing happening in action. And if that sounds like meh to you, wait till I show you a picture of the 3D printer. So that's the basic fulfillment architecture as we envision it today. Now, sort of a different view of the same thing. This is the developer to consumer flow of goods and of information. So how do you, as a developer, enter that marketplace and enter that ecosystem that I just described to you? We envision three types of developers that have to be treated for various reasons somewhat differently. The first one and the most challenging one, and one that we have totally punted on in the 0.1 MDK, I admit, but that we are hard at work on figuring out all the gritty details, are developers of emitter modules, RF emitters. So these are the cellular baseband modules, things that require regulatory certification. So those emitter modules, so the three categories are emitter modules, non-emitter modules, and design apps, which we have renamed to shell makers, and I forgot to update the slide. The certification process can kind of run the gamut, right? On the one end of the certification process, it's just about finding out who you are and having you stand behind the design. So it's your reputation that's at stake. So you have an incentive to make a good design. To a large extent, that's the way the Android Play Store for apps works. You digitally sign the app, and then there is a consumer feedback mechanism or consumer review mechanism that's transparent. On the opposite end of the credentialing and certification spectrum is what the U.S. government does. And coming from the U.S. government, I can tell you it is not a pretty process where you X-ray all the ASICs and you try to figure out if there is any malicious functionality in the X-ray of the ASIC. This takes a very long time and is not something we're at all interested in doing on the project. So that's the space. And that's what's depicted on that gradient there. So we imagine falling somewhere in between. So we will ask for a tech data package associated with each module. We will obviously review that tech data package. We may simulate that tech data package as we move towards some of these formal modeling methods and tool frameworks. We will also ask for engineering samples, and we will test those engineering samples against data fuzzers. We will do power excursions on those engineering samples. We will do thermal cycling on those engineering samples. But we are not going to do detailed behavioral analysis, except insofar as it's required by the regulators. And so that in particular applies to emitter modules. As I mentioned, we do not yet have a formalized framework for certifying emitter modules, although we are in discussions with the regulators, and you'll have a little bit of a preview of that, of what process we imagine there this afternoon. Now, for non-emitter modules, the certification process doesn't include the detailed behavioral analysis or the lab entry process. So it's just some of our back-end testing of engineering samples. Now, once the modules go through the certification process, and again, I just want to emphasize, right? I describe it in some detail, but our view of the certification process is largely the liberal view, right? So in the Android Play Store versus iTunes model of app certification, we're much closer to the Android Play Store in terms of the level of scrutiny of the modules. The modules then go into the e-commerce system, into the back end of the e-commerce system, and become listed items in the marketplace. We are developing, because this is a completely unique creature, we are developing a new e-commerce system. It's based on the 3D Systems Cubify system that's used for fulfillment of 3D printed goods. And it's obviously an adaptation of that specifically for Project Ara, and it would run complementary to Google Play, which we would rely on for delivery of any Ara apps or any user space device drivers for Ara phones. Now, so the module that goes into the back end of the e-commerce system is a module, just a module with a base, a connector block, a PCB, and a safety shield. The module enclosure is something that we provide for you on the basis of an outer mold line, right, or a geometric specification for that module enclosure. And in most cases, we expect that geometric specification to conform to one of the standard module enclosure types. Now, in order to facilitate the creation of things like the thermal imager module that I showed and the pulse oximeter module, we certainly will afford the opportunity to be able to create custom geometries that somehow exceed the envelope. But you give us the geometry, and we pair that geometry with the consumer's aesthetic design and aesthetic customization of that geometry, and send it to the 3D printer and provide separate fulfillment for that. Now, the next big and interesting aspect that's different for Project Ara, and I'm highlighting the things that are really different from traditional e-commerce. The standard things will all be there. Is the aftermarket support, right? So what you don't want is for the consumer to have 10 toll-free numbers, right, corresponding to each of the modules in the device in order to be able to figure out why the device won't turn on or something won't work. So we actually have to architect a new type of customer support mechanism, we together. The intent is that there will be a system-level entry point that will be managed by Google, and there will be module-specific support modules, if you will, that will tie into the back end of that entry point. So that we can do a quick diagnostic at the system level, try and hone in on which module might be causing trouble, and refer the consumer to the module developer to assist with the detailed diagnostics of that. So that, in a nutshell, is the developer to consumer flow. Now, obviously, a significant part of that is the aesthetic customization or the creation of the 3D printed module shells. This is an isometric view of the 3D printing platform that our friends and partners on this project at 3D Systems are developing for Ara modules, for Ara module shells. Note that it looks very different than the 3D printers that you are probably used to and imagine. It is not a reciprocating platform. A lot of the speed, a lot of the speed penalty of a traditional 3D printer comes from accelerating and decelerating the carriage as it goes back and forth. So if you want to do this at volume and be able to produce millions and hopefully billions of units, you want a continuous motion system. So the 3D printer is based around a racetrack architecture where the module shells move in a continuous flow. And there are off-ramps to do various finishing steps, to be able to put inserts, and to be able to do other kinds of manipulations with those modules. We anticipate being able to print in full color. What that means is cyan, magenta, yellow, black, white, clear, soft on top of that, and be able to mix those materials in various combinations to get the full spectrum of the palette, and be able to make soft, hard composite materials to improve the survivability properties of the individual modules. In addition to that, and you see that as an artifact, as a test sample down in the bottom middle, and here's a bigger view of it. We're looking at not just 3D printing the aesthetics of the module shells, but actually being able to 3D print functional elements, and in particular the antennas for the individual modules. So we're still in relatively early phases of the conductive inks work with with 3D Systems, with Carnegie Mellon University, and with X5 Systems, which is our RF partner on RF design for Project Ara. But ultimately, what we aspire to be able to do is to be able to print the antenna as a set of conductive layers as part of the module enclosure. In the near term, and probably for the market, for the initial pilot demonstration on the market in early 2015, we will do the antenna in a manner similar to what I showed on the Elmo, which is a similar design process. So these are computer generated. They're bred using genetic algorithms. Antennas for a particular antenna pattern, and they're conformal, so they're two-dimensional deposition for traceability to 3D printing. But for now, they're made using traditional subtractive PCB manufacturing methods. Okay, so now the last last few minutes on the last few feet. Let me introduce David Fishman, who many of you have probably met in the or virtually met in the course of trying to register for the conference. David makes the wheels turn on the project on a day-to-day basis. He's the project manager, the chief of staff, and responsible for most of our performer and vendor relations on a day-to-day basis. And he will talk to you about the consumer experience. David.
All right, thank you. So the consumer experience. So Paul talked some about our configurator app, right? How we're going to enable people to explore all the choice the platform allows and make decisions about how they want to functionally and aesthetically customize their device. So when we say app, we do mean literally an app running on the phone that you may be using either on your own gray phone or your own customized phone, or maybe on a friend's phone in the friend mode for the peer-to-peer experience. And so right now, what we have is a really nice spatial model. And you'll see this trend a little bit as we step through the different areas of the app that sort of mimics in a virtual way some of the physical realities of the device. As Paul disassembled our form factor prototype here, you see that we go down the different layers. We have the aesthetic shells that live on the outside, and down to the functional layer and to the endo. And so this slide here sort of shows the spatial model that the app lives in that allows you to navigate through those different layers of the device and make decisions at each layer. So you'd be in the enclosures or shells layer when you're making your aesthetic customization decisions, and then you could move through to the other layers of the device. Paul also mentioned shell maker apps. So that's actually one piece that wraps around this central framework, and there's another piece as well, which we call phone makers. So I'll start the story with a phone maker. This is another way to help facilitate the choice process, and this is another area of this configurator app that we're opening up for development and ideas from the developer community. So you could imagine you start with a blank phone, you're not sure what direction you want to go to customize it. So you try one of these phone maker apps and it helps you. So it asks you, take a picture of your cat. You take a picture of your cat, and then it asks you to hold your phone in your hand and do your favorite dance move. And your phone collects accelerometer data while you do that, and then from algorithms that the phone maker designer has put into the app, it uses that data, manipulates the image, and creates a unique and beautiful design for your phone. And then from there, you can go on to customize it more, but it gives you a starting point. And then the other piece that wraps around this central configurator experience is the shell makers, which Paul described, that designs the individual enclosures for the modules. So to move through these layers of the phone, we have one of the signature interactions of the experience that we're calling the pinch to peel interaction. And this interaction allows you to move through in Z. It's sort of like instead of pinching to zoom, you're pinching to remove layers of the device and move through the different layers of the configurator. So another key interaction that we feel is really important with the device. And it's sort of a magical moment when you're sliding these modules in and out of the endoskeleton. And so another place we mimic that virtually is when you're selecting modules and looking at the detailed level of those modules to see what they do and whether or not you want to buy this module or how it interacts with your overall device. So you're going to see these signature interactions mimic that virtually. So when you select a module, it would have this sort of a sliding effect, right? And you would zoom in on that module, and then it slides back into the endoskeleton. And this also has sort of a function for someone who's new to the platform and maybe configuring their first phone. It provides suggestions for how the device itself is configured, so when they have their device in hand, it helps enable that experience. So these are just wireframes, obviously, of the app that is in development, and you're going to see that demonstrated in some of the later sessions at the conference. We have it running on a phone, and it's quite neat. So this is a similar flow illustrating the zooming and pinch to peel interaction that allows you to move between the layers of your phone as you're deciding whether to configure it functionally or aesthetically. And it just sort of illustrates the module zooming in as you do this interaction, and just gives you a sense of how the app is going to feel and interact. But again, the demos will do this much more justice. Okay, so as I mentioned, we feel this tactile interaction with the device could be entirely key to the experience. So we're looking at ways to bring that experience globally so that everyone can have that option when they're making their decisions about their device, instead of just having to do that process on a touch screen. So we've been experimenting with physical spaces. There's a challenge there of how do we actually physically get this space and everything that we're going to put in it to 5 billion people. So one of the decisions we've made is to use one of the most mobile self-contained platforms that we could think of, an ISO container. These containers are shipped all over the world today. They're moved by truck, by boat, even by plane. And so it gives us some good global accessibility using this form factor. So within that form factor, we've done some trade space exploration of different configurations, both the exterior around the container as well as the interior. These impact how people interact with the space, how they flow through it, what they gather around. It impacts the throughput for the space and the types of interactions that people have while they're there. So corresponding with the physical space, we've done some throughput studies and economic models to understand how that affects how the space is used. We also, you see a picture on the top right here, have mocked up a container in our prototyping space. It's a little rough, but it gives us the ability to change the configuration and do some user testing and research with how people interact with different spaces as we refine how that physical UX concept is going to look. So one potential approach for resolving or facilitating users through the paradox of choice that Paul described with this deep ecosystem of choice and options that the user is going to have on our platform would be the use of non-invasive biometrics. So we could use these to monitor the excitation and valence of that excitation to adapt a UI in real time accordingly for the responses of the user. For if they're stressed or if they're feeling confused, we could reduce the number of choices or help give them options that they have positive reactions to. So this could be done through a number of different technologies that are out there: eye tracking, galvanic skin response, heart rate. There's several different ways to collect this kind of data, and there's lots of different signals that we could consider using that the user would explicitly consent to when they're using this configuration experience on a tablet or they're standing at a counter in the physical experience. We see a number of examples here, and a potential mock-up for what that space would look like for a user to engage with that. And with that, I will hand the stage back over to Paul until I return later.
Thank you very much, David. All right, so a few other miscellaneous topics that that undoubtedly you guys are dying to know about. So one is why did we go public? Right, a lot of people have asked me over the last few months. This is you guys are developing the next great thing in smartphones. Shouldn't you be super secretive about it? And actually, we made a strategic decision to develop Ara as much in the open as practically possible. We still have locks on our doors, but we want to show as much transparency into the development process of the Ara platform as we can, and we're doing that for you, for the module developers, because we want you to see exactly where we are. Exactly what problems and risks we face, so that you can make intelligent, well-reasoned, and well-supported investment decisions on your part into the module ecosystem. And so that is a pledge that I can make to you, is that we will be as transparent and forthright about the status, the technical risks, the risks we've retired, the aspects of the platform that are stable, and the aspects of the platform that may change. And so that is a commitment. That is a commitment that we make to you. Now, the initial Project Ara public reveal was an interesting phenomenon, partially I think because it was such an unusual creature in the mobile world, and so I just wanted to share some statistics. So we revealed, in conjunction with many of you have seen the phone blocks videos, and Dave Hackins is here. So say hi throughout the conference. And he had a thunderclap, and I think we struck a resonant chord in terms of the values that he espoused in the phone blocks concept and the kinds of things we were trying to do with Ara. So we actually moved up the public announcement of Project Ara by about a month in order to sync it up with his thunderclap and announce it to the phone blocks community and the relationship with the phone blocks community. And so you see plotted there the sort of the chatter volume. Now, we were still at Motorola. ATAP was still at Motorola at the time. And so this is vis-a-vis the typical Motorola chatter volume. And then down on the bottom, you see the official Motorola blog total page views. And we were about 10x the next most popular story that Motorola had ever put out in the history of its web tracking statistics. So we thought that was pretty interesting. But the really important aspect of that isn't just the fact that we got lots of web hits, but the fact that people actually engaged. And we stood up and we announced something called the Ara Research Scouts program, which is, many of you are probably Ara Research Scouts. And it's a way for us to give you voice and a way for us to conduct research about preferences, needs, wants, desires, aspirations for the Ara platform, and actually help us make design decisions. Design decisions about mundane things, mundane but important things, like dimensions of the device, and also give developer inspiration for the kinds of modules that we ought to be able to think about in the context of structuring the platform, and other inspiration for the user experience, for the fulfillment mechanisms, the fulfillment flows, and things like that. And so as soon as we announced for the very first Ara Research Scout mission, we got 47,000 snippets. So it's an interesting statistic to gauge engagement from and level of commitment and enthusiasm that the concept has received. Now, we're still in the process of architecting the Ara brand. And one of the things that you probably have noticed conspicuously is that there's no Ara logo. And we kind of like it that way. One of the reasons is because we think that the endoskeleton itself is the functional symbol. It is all of the semantics of Ara are contained in this artifact right here. So it in and of itself, I think, is iconic of the project. And we think by pushing a particular logo or particular artwork on our developers, on our consumers, and on the ecosystem, we think it's a disservice because we want them to make the aesthetic choices about the device. So we're still exploring how to do that. It's untrodden ground, as the project is in many different ways. But what you see here are some of the values that we think that the Ara brand represents: open, expressive, flexible, and global. And so stay tuned and send us your ideas and engage with us on how best to represent those values in the brand language, and I mean that broadly. So not just natural language, but visual language, oral language, and other facets. So I also want to say a few words about sort of how we got here. Ken, who's my boss, if that wasn't obvious, opened with Sputnik, and Sputnik was in fact the formative moment for DARPA. President Eisenhower created the agency to prevent and create strategic surprise. And DARPA evolved over the years since the 1950s into something mythical, because it did in fact have a series of success upon success upon success. So the Saturn I engine, right? GPS, the internet, stealth, and a variety, innumerable other things. A lot of the basis of cellular technology arose from DARPA. And yet nobody had quite been able to document, if you will, what is the recipe that makes DARPA successful and makes it special. And there are a lot of ARPAs out there in the U.S. and outside of the U.S. That have tried to replicate that DNA with mixed success. And there have been sort of two concerted efforts to try and understand what is DARPA about DARPA. The first one was George Heilmeyer, who was a DARPA director in the 1970s, and the author of the Heilmeyer Catechism. And so you can Google it if you don't know what it is, but it's sort of a series of questions that are gating items for creating a successful DARPA research program. The other effort was more recent. It was by Regina Dugan and Ken Gabriel, who introduced me and who is the deputy director of DARPA. Regina Dugan was President Obama's first appointee as DARPA director. And I had the honor of serving under the two of them for 4 years of my life, my career. And Regina and Ken did something different from any previous DARPA leadership. Is they actually tried to document and distill what the DARPA DNA is. And there's a Harvard Business Review article by the two of them. It was a cover article. It should be easy to find. That explains that at some length. And one of the things that Google wanted to do initially through Motorola, and since the announcement of the sale of Motorola to Lenovo, in-house at Google within the Android Chrome Play and Apps team within the company, is to try and see if we could reflect the DARPA DNA in a private sector entity. So the traditional models of private sector research and development are, on the one end, corporate labs, right? The storied AT&T Bell Labs, the modern day Microsoft Research or IBM Research. They're still here today. They are fairly capital-intensive entities, and they tend to invest for the long haul, right? So they will invest into a particular area, like quantum computing, and make a sustained investment for many years or decades. And they're very good at that and have been very, very successful over the years. What they're not good at is turning on a dime. And the speed with which technology emerges, and in particular when you put multiple technologies together, the speed is really not conducive to static organizational innovation as you would see in corporate R&D entities. So the new approach has been to do M&A, to snap up startups, mergers and acquisitions. So as new ideas emerge and small companies get formed, bigger companies buy those in order to drive product innovation. And the downfall, or downside, I should say, of that model is that you lose control over your destiny, right? You go wherever the new startup that you acquired or other company that you acquired is, but you can't go into a white space, a space that is hitherto unexplored. And so with ATAP, we're trying to see if the DARPA model can work in the private sector. And so let me tell you what we think the DARPA model actually is. And there are kind of three basic tenets to it. The first one is projects, and that's the P in DARPA, and that's the P in ATAP. And the critical aspect of projects, or in our particular semantics of the word project, is that it's something with clearly defined objectives. It is something that is relatively short, a finite, clearly scoped duration, and it's something that lives in Pasteur's quadrant. And for those of you who are unfamiliar with the construct of Pasteur's quadrant, you see it depicted there in the upper right on two axes. The horizontal axis is practical need. The vertical axis is fundamental scientific insight. And so the two quadrants that flank Pasteur's quadrant are, on the one hand, Edison's quadrant. And this is what Edison did, right? He tinkered. There was a practical need. He saw the practical need, and he tinkered until he solved the problem. On the vertical axis is Bohr's quadrant. And that is an homage to Niels Bohr, the famous physicist, where there is pure basic research that is predicated on a fundamental scientific insight with no practical application, at least not for many, many decades. Pasteur's quadrant is at the intersection of those. So it is fundamental scientific insight crossed with a compelling moonshot practical application. And so Project Ara, as an example, lives squarely in Pasteur's quadrant. So there's a variety of new technologies. I mentioned the first consumer-facing miniature electropermanent magnet, contactless data interconnects, 3D printing, conductive inks, other kinds of things. So these are all fundamental scientific breakthroughs at some level, and they're crossed with a compelling practical application, a phone for the next 5 billion people. So that's an ATAP project. Now turning to people. People at ATAP have limited tenure. I know my expiration date. I started on April 1st, 2013. I will be done on April 1st, 2015. I will take this project to fruition, and I'll explain in a second what that means. But it creates a sense of time urgency. It creates the sense of finite scope and saying that time is not your friend. And innovation under time pressure is the best kind of innovation because it gives you a carte blanche to take risk. And the other aspect of people is that we have a very small internal team. There are 3 of us at Google who are full-time on Project Ara. There's a number of other people who shouldn't go unrecognized on the legal side, on public relations, comms, and others who support the project, of course. But there are 3 of us at Google who work on this. The external team are our performers. They are the people who do the vast majority of the development work. And you'll hear from those performers, and we've tried to recognize them in the title slides and on the agenda as to where they come from. And many of you have probably thought that's kind of weird, right? Like, why is Google having all these contractors talk about their project? It's because they do the real work. They are where the innovation comes from. And most of them, or all of them, are external. We work with a variety of different performers. We work with academia. We have 3 or 4 different academic teams from MIT, from Carnegie Mellon, and other schools on the project. We work with companies, we work with small companies, we work with large companies like 3D Systems and Toshiba, who are our major partners on this project. And the reason we do that, the reason we externalize the talent, is to allow us to capture the best-in-class mind share. So these people are absolute rock stars in their fields, and I could never, ever convince them to pack their bags from wherever in the world they live and come work for me full-time. But with a compelling enough application, with a compelling enough moonshot intersected with the fundamental scientific insight, I can hold their attention for maybe 6 months, maybe 12 months, maybe 18 months, and get them to contribute their mind share to the project. So that's another unique aspect of the model. Obviously, we have to be very careful about management of intellectual property in this kind of ecosystem, and that's our lifeblood. That's what I do day in and day out, is ensure that we have freedom to operate. So one of the key tenets of our posture internal to the team, and that everybody I think is important for the developer community to be aware of, is that we try not to take ownership wherever we can, because we want other people to develop this external to the develop these technologies external to the project. So in a lot of cases, what we actually want from an IP perspective, intellectual property perspective, is freedom to operate. And you see some of those tenets reflected in the MDK license as well, because you all, by using the MDK, become to some extent part of the ATAP ecosystem. So we take a very liberal posture, so long as we have freedom to do the things that we want and to accomplish the goals that we have. Now, the last thing I should mention, it's actually under projects, but it's probably one of the more important aspects of this, and is a lead-in again for David to wrap up the talk here, is so what's the end game? Right, so Paul leaves next April, and does the project go away? Like, that's not a very good grounds for creating a developer ecosystem. So let me explain the handoff, right? And this is a very critical part of how DARPA operated vis-a-vis the military services, and transitioning of technology from DARPA to the, if you will, product and warfighting organizations in the U.S. military, and is a key aspect to the way that ATAP transitions technologies to Google writ large. And that is the notion of demo at convincing scale. And we've coined even an acronym for it, DAX, that you'll see throughout the subsequent part of the presentation. So where we leave off is not a prototype. It's not just a platform. It's not just a suite of technologies. It is a demonstration at convincing scale, which means that a demonstration that retires beyond a reasonable doubt all of the technical, all of the market, and all of the business model risks associated with the product. And after that, the product organization is no excuse to not take that product and run with it. And so this is very similar to the issue that early DARPA, as it was winding its way through the 50s and 60s, started to operate, is they realized that if they just create a prototype of, say, a stealth aircraft, the Air Force says, well, you know, it has all these other issues. It doesn't work well in rain because it damages the radar absorbent coatings on the airframe. And so you couldn't just make a prototype. You actually had to do a demonstration at convincing scale. And so with that, I will ask David to walk us through exactly what a demonstration at convincing scale for Project Ara is going to look like, and how we will get there in the remainder of 2014. Please.
Thank you. All right. Everyone's good? All right. So Paul walked through the technical areas of the program, so I'm gonna revisit many of those, but as Paul framed, it's gonna be in the structure to try and pin our milestones that are designed to retire the technical risk of the program to timeframes, so that we can clearly see how they map to the rest of the program that gets us to our demonstration at convincing scale. So as Paul mentioned, we've programmatically binned these risks into 3 bins: technical, market, and business risks. And so what we see here is a representation of our technical risks and how they're retired across the various milestones. So just to help make sense of the slide here, on the y-axis we see our technical risks, and along the x here we see our program milestones. And the shading, it gets lighter when we have sort of an interim retiring of that risk, an initial demonstration, and then where the line ends, we're considering that risk to be addressed, retired, and our solution stable. So today, here we are in April at DevCon 1, and we've seen, as Paul mentioned, our number one priority was to bring up the network on the device. So even though this phone doesn't boot today, we see Unipro network retired. It's working on the dev boards, and so that's where we've retired that risk in the schedule. We also see an interim retiring of the EP magnets there as well. So the next big area we see risks retired is in September, along with our next major MDK release, 0.2, and our capacitive prototype. I guess I should say also just for program structure, right, in terms of MDK releases. So we see 0.1 today. We also see 0.15 in May. And so the primary objective there is cleanup of the MDK release today. That's going to incorporate the feedback that we get from everybody, through this dev conference and through the other channels. And so 0.2 represents the next major release that corresponds to the technical advances on the platform. And so that's why we see more risks being retired there. Just to step through some of them a little bit, as Paul mentioned, we see capacitive datacomms today. They exist in places, chip to chip and other solutions, but we haven't seen it, at this level of user serviceable components. So they have to be very robust. We have to support, I guess M5 supports a wide range of data rates, right? And so supporting that full range through a single connector is a challenge. And so those are some of the things that we're going to address in September with that prototype. We also see, we consider our electropermanent magnets to be retired in that time frame as well, because again, EPMs are not a new technology, but to miniaturize them in this way and to put them into a mass consumer product, we think it's the first time, and there are definitely risks there that we need to retire in terms of manufacturability and robustness of those components as well. They do also help us maintain that sleek look and feel of the modules, which we think is absolutely important. And I think we can all agree electropermanent magnets are just pretty super cool too. So those are the big milestones we see in September, along with that prototype. And then looking forward a little bit as we get closer to our demonstration at scale, we see some more milestones coming up. And so let's see, our driver architecture and modularity penalty. So Paul talked some about Android and how it's currently designed for static configurations, and how we're working to address that. And as has always been true, modularity comes with a penalty, and so we're driving that down through a number of different ways, and we think again that the functionality afforded to us by this modularity outweighs that penalty, and that there's some balance that consumers are going to be willing to accept. And so as we move closer to our production components and layout and objective vision, that modularity penalty is driven down to our objective real estate for developers. And so we really hit that that minimum penalty when we start to scale up to production processes and components, right? And so that's why we consider that fully retired as we hit the pre-production stage and the prototype. And then finally, January is when our demonstration at convincing scale is here. We'll say first quarter. So these are going to be consumer devices. So just as phones are today, there's a lot of robustness testing that we need to do. There's considerations for, are the shells strong enough? If you put them in what we call the purse test, right? Can they survive all the scratching and the wear and tear that these devices inevitably have to go through. So there's a lot of industry standard stuff around that, and when we have those pre-production devices, we're going to run it through all those tests and make sure that we're on track to retire those risks there. And then we also see the 3D printing, as Paul described as well. Again, it's a first of a kind capability for this kind of volume and consumer grade product. And so our printer development milestone schedule roughly aligns with the timeline seen here. The printer is very impressive and very cool, and our partner 3D Systems is working hard to tackle the challenges and the risks that are there, like getting parts through the printer fast enough, and addressing the throughput challenges as we look forward to scaling to 5 billion people. All right. So our next risk category, market risks. So a lot of these extend all the way across. So I think we can do user testing and we can do research and we can make hypotheses now, but a lot of these are really tested when we hit scale and really see large volumes of people responding to the product. And so that's in general how some of those align. But today we see the industrial design being retired. We've worked very hard on that design. We think it's beautiful, but again, at the end of the day, the consumers are going to decide. But from a program perspective, we think we've retired that, and we're committed to the industrial design and the parceling as we see it today at the Dev Conference. So the remaining ones here, value of customization and the paradox of choice, right? So we are committed in this platform to offering an unprecedented level of customization in a product. And as Paul described, we hypothesize that this increases the willingness to pay for the product. I think we believe, in terms of a mass product, is probably the highest dimensionality of choice seen in a product. And we need to enable that configuration process to be accessible and scalable. As I talked about a little bit before about our configurator and some of our explorations about spaces and apps and testing have informed our thinking here. But again, until we hit scale, we're not considering that risk retired. And then finally, BOM cost. So again, bill of materials cost, right? So of course, modularity comes with a monetary penalty, right? But we do think that the platform allows us to offset that cost in a couple ways. We heard about the Gray phone. It's a low-cost configuration that just consists of enough to basically get your phone running, connect to the internet, and run through the configuration experience. And because that has a lower number of modules and a low-end functionality, we think we can hit. That will enable us, I guess, to engage with the entire 5 billion in terms of spanning the range of cost of devices. And then, as I mentioned again, getting to scale allows us to reduce costs as well. So when we hit those pre-production processes and demonstration processes, we see our full, our minimum BOM cost builds. And finally, our business model risks. So the risk we see retired today here is called ecosystem governance. So we've released a lot of information about the ecosystem along with the MDK this past week. And we will hear more on licensing later. But the license is definitely an important piece of that governance. You've seen the text. It's structured to give developers the freedom to develop and commercialize, but it's also very important to protect that ecosystem from disruptive legal actions and from fragmentation of the ecosystem and that sort of thing. But we think it is designed to do that, and so that's the milestone we see here. And then looking forward into the November and then Q1 15 timeframe. we see critical mass of the developer ecosystem. So to ensure that there's a sufficient amount of choice and functionality to the consumer, we need to work with developers to articulate the value proposition of participating in the ecosystem and to provide the documentation and the tools needed to develop. And then on the other side of that two-sided market, right, we need to enable the consumer to understand the platform and to engage with it and purchase and configure their devices to fuel that two-sided marketplace. And so there's a critical mass probably of choice available to the consumers where they have actually enough freedom to configure their device that the platform starts to build momentum and reaches that critical mass where it's self-sustaining. So there's a couple other pieces to sort of demonstrating at scale, right? And so one of the things on here is aftermarket support. So you can start to imagine the problem or the challenge an owner might have if we don't deal with this in the right way. If they have an Ara device with, say, 10 different modules in it, each from a different developer, right? So then that raises the question: something's wrong with my device. It's not working. Who do I call to try and understand how to fix this and get this working? So we're still developing thinking on that and to come up with an optimal solution. But I think it's clear that a sort of a very simple process for customer service and then probably a single unified point of contact to do that is going to be the best way to make sure that consumers have a facilitated and easy experience for that kind of support on the platform. And then we also have, of course, considerations around regulatory and carrier certifications and those types of things. So while existing certification regimes are really designed for static device configurations, we've started the process of engaging. We've had some discussions with the FCC, and we're looking globally and look forward to sort of, I guess, engaging regulators around the world to get us to a pilot regime strategy for where we're going to be at our demonstration at scale. And I guess it's important that it's a new way of doing products, right? So we want to come up with a way of dealing with the regulatory requirements that allows this level of innovation and flexibility while still addressing their regulatory objectives in different regions. All right. So those are the program milestones as they're laid out across the program that serve to retire the technical risk of the program and get us to our demonstration at convincing scale. So what exactly are we demoing and how are we demoing it for our demonstration? So again, this is not just a prototype run of devices. This is intended to hit a meaningful scale and to be selling complete and certified devices. In addition to just having devices coming out, into consumers' hands, we want to exercise the full fulfillment architecture end to end, and make sure that we can get, modules from developers through that fulfillment chain and into the hands of consumers. So from the user experience perspective, we've heard about the three methods that we're using: the gray phone, which is off the shelf in sort of an unofficial a retail establishment or whatever carrier would like to carry that product, and so we need to establish those distribution channels, and that gray phone variant is part of that demonstration at scale next year. For the peer-to-peer interaction, right, so it also requires that you actually have a peer with a device that you can interact with and log onto their phone in friend mode and have that experience with. So we think there's a minimum penetration density of devices within a certain population density that's going to be required to give people the right sort of likelihood of knowing someone and distribution of devices. So that helps inform, I guess, where we're looking, such that the pilot geography maps to those goals. And then finally, there's a similar, I guess, requirement for the physical retail establishments, right? We need people to be able to get to a store in a reasonably easy fashion so that they can go and engage with that physical space. And so we have some thoughts there also, roughly 1 in 100,000 people in terms of density of stores to population. And so all three of those we intend to demo as part of our demonstration. For the fulfillment architecture, right? So Paul described sort of the flow there, right? There's a lot of moving around bits and atoms that needs to happen to get product from developers to consumers. So we're going to demonstrate all of those pieces end to end. I guess just to give you an idea of the scale that we're thinking, right? So the numbers on here are 2 to 10 million units. And so when we say unit, we mean an endoskeleton. So there's going to be a number of modules that go into each one. And so it's roughly somewhere in the 20 to 100 million units in terms of modules. And then finally, as I mentioned before, regulatory compliance. In order to demo and have a certified device that goes out to consumers, right, we need to establish that certification framework. And Paul touched on this some, but this may leverage things like computational modeling or rapid scan in order to quickly identify worst case scenarios of combinations of modules, to enable that regulatory requirement without having to do a SAR test on every possible device configuration or something like that. And then the value of customization as well, right? So for here, in terms of demonstration, we just want to make sure that where this pilot takes place, that we have a broad range of user archetypes, covering different socioeconomic strata, education levels, relationships with smartphone technology, cultural considerations, things like that, so that we can get the broadest understanding of how this dimensionality of choice impacts the consumer's willingness to pay and other considerations in that area. Okay, so that takes us to the specifics of our demonstration at scale. So again, looking between now and that demonstration, right, some things in terms of risk to the platform have been retired now, and others have yet to come. So this is meant to take a look at what areas on the platform within the MDK become stable and when to help better enable the developers, right? Our primary objective here is to enable you to get started. So I guess we see two sides to that challenge. One is stability of the platform as we make it to our production variant, and so that's what this covers here. So again, I mentioned this before too, but in terms of MDK, right? So you see most of these being locked at the point 2, which is the next major release. And where 1.5 is mostly cleanup based on feedback, and where we plan to close the power bus details. So to walk through these some, so morphology and parceling, as I mentioned, we're committed to how that is laid out today, and so we see those as stable here. Power bus we see in May, but we do think it has all the features that it's likely to have, but we definitely look forward to feedback and comments tomorrow in the feedback session so that we can close that in the next release. I think I have potential to run long here. I'm not sure if this clock is I have 15 minutes left or... Okay, so I think that's the accelerate request. So you see most of these becoming stable in the September timeframe, right? And we talked about a number of these already. The bulk of them here are in the system level functions. Most of these are not currently properly implemented in the prototype, although we've started the thinking on those. But those are slated to be locked in the next major MDK release. Okay, so I'm not going to walk through this in full detail either, but the general thought here is that as this ecosystem evolves and hardware comes into the market, right, there's going to be a number of different ways for a developer to instantiate the different sections of the MDK and different elements of the platform. We think the MDK offers you all the the details, the reference designs, and the implementation of the specs to just use that data and implement things on your own. There's also probably going to be a number of components that end up being quick and easy to buy off the shelf, like the module base plates are going to be pretty standard, right? The EPMs are going to be found in all modules. So those types of things we expect to be able to buy off the shelf. And there's probably some hybrid as well, where if you're making some customizations or something like that, where you do the design, but then you send it off to a contract manufacturer and have that done. And we see sort of that similar trend across the various sections in the MDK. As another example, right? You could become you could get the MIPI spec right and instantiate a Unipro in your own RTL and do the work from the ground up there. Or on the other end, you could buy off the shelf one of the bridge chips and implement that directly. So what's next? So today, the objective of the DevCon, right, is to learn about the MDK and provide feedback and understand that in detail. We're going to hear more about this later, but we've heard about the dev hardware that's available that actually is functioning and running the Unipro network. I'm not sure if we've mentioned the prize challenge yet, but there's been some coverage of that. In terms of getting people started on that prototype hardware and instantiating their module ideas as part of a prize challenge. And so that's the developer, FPGA-based hardware. And then in terms of objective development, looking forward based on the stability of the platform and choosing areas that make sense to develop now and looking forward to what we can do on objective hardware later on in the year. So I just have DevCon 3 on here, but there's a DevCon 2, right? That's more going to be focused on the software side in terms of instantiating shell makers and phone makers. And DevCon 3 in the fall is going to be heavily focused on hardware again, and with a lot of objective system information and planning. And then ultimately a plan for our initial market pilot and demonstration at convincing scale in the winter in 2015. So that's all I got.
All right. So we are going to do Q&A. There is a ton of questions from online. To help us do Q&A, I'd like to introduce Daniel McCoskey, who is the creative director for ATAP and actually worked on Project Ara before it was even Project Ara, and before I even knew that ATAP existed. And Daniel also led the Make with Moto tour and has been a steadfast presence in all of the design and creative aspects of pulling this platform together. So Daniel is going to be the voice of our online questioners, both on Twitter and on IRC.
Awesome.
And I guess we'll alternate.
All right. All right. Well, welcome, everybody. We've already gone through the length of a full-length movie, and I know there's going to be a long line out of the men's bathroom in a little bit, so if some of you need to take a break, you can do that now. There's been a lot of kind of conversation on Twitter, and we wanted to ask some of those questions here. We also have a microphone in this aisle and in this aisle, so if you guys want to come up, we'll probably take maybe 4 or 5 questions in the room. All right, so let's start out from Twitter, from Ramanath Saga. Will Ara be supported only on Android, or will it be supported with other OSs like Chrome as well?
So our intent is to support Android and create the Unipro class driver architecture for the Linux kernel. and the user space attributes of that, and some of the HAL or hardware abstraction layer features for the Android OS. I'm certain that there will be other sorts of activities that take place in the ecosystem, and I'm not sure we have a stance one way or the other with respect to those activities. But Android first and foremost, and in terms of reaching a very large global user base, we think that's the platform to do it with.
Okay, and so kind of a related question from Ali M. Salhin says, will this be native Android? Will this be kind of stock Android, or is this custom? And how custom will it be?
Yeah, so for now, for most of this year, and at least for the next 2 MDK releases, we are working on sort of some custom features as we try and flesh out what works, what doesn't, what the developer community likes, what the developer community doesn't like. In the long run, I think some of the feature sets, such as generic class Unipro drivers, the ability to load and unload the user space portions of the drivers, as well as HALs, is something that we would hope it has to sort of earn its way, but we hope would earn its way into the mainline Android releases.
All right, we've got JW Kicklighter asking, okay, you talk a lot about this $50 bomb phone, but it's really going to cost about $600 to make a decent phone, right? Like, can you talk about, if you want a decent phone, how much do you really going to have to pay?
Yeah, so I don't think that from a cost perspective, I guess there are a couple of considerations, and I also want to emphasize one more time, just for posterity's sake, that I'm talking about bill of material costs. So I'm just talking about the cost of the components that go into the device. Pricing is something that is beyond the scope of the R&D effort. That would be a product organization question, and it's also, frankly, something that would be very dependent on geographies and relationships with carriers and other kinds of things. So strictly from a cost perspective, we showed you the breakdown, our sort of anticipated breakdown for a gray phone in the presentation. So there is some additional stuff for the endoskeleton, the electropermanent magnets, the Unipro network circuitry that has to go into an Ara device versus a comparable non-modular device. But beyond that, and so just keeping in mind that delta, which we have some loose estimates for, although we haven't embarked on serious design for manufacturability and sort of serious cost reduction activities on that front. Beyond that, the device, it's a zero-sum game, right? So if you wanna get an X megapixel camera, right, you pay for the X megapixel camera. I think the only additional factor is that we expect that the ecosystem will be much more competitive, and we think that in the long run that'll create better value for the consumers, both in terms of choice and also in terms of the richness of the kinds of things that are in that ecosystem. But there's nothing special or specific to Ara that should require $600. I mean, if the questioner's sort of threshold is $600 phones today, then it'll probably be a $600 Ara, maybe $615 Ara that'll suit his needs. But we are aiming to make a device with a bill of material cost in the double digits, well into the double digits. That is a fully functional, nice Android experience with all of the Ara features, such as the configurator app.
Okay, awesome. So here's a less kind of technical question. Actually, my mom had asked me this question. She's not on Twitter right now, but she's like, well, didn't you guys just steal that idea from Phone Blocks? What about that nice Dutch boy that had that idea? Did you just take it? Like, what's up with that?
David, I'll let you take that one.
It's a good story. We had been working on Project Ara, behind closed doors and in secret for a while. I think about a year or so before the release of the Phone Blocks video, and we saw that video come out, and we were like, "What? This is like what we've been working on." And then the internet exploded with interest in the idea, and we have Dave Hackens here, who is the creator of the concept.
Dave.
Yeah. Come on, where's the wave? Yeah. And so we immediately reached out to him and wanted to learn more about what he about the idea. And so we've been working together for the past few months now to just help build that community. And I guess with the interest and the explosion of the idea, right? So I think that caused us primarily to open the doors on our program earlier, a bit earlier than we had expected. You know, it was always going to be a program that was going to be open and transparent. But that sort of catalyzed us to do that earlier and gave us a great community to engage with and provide insights into our project.
So I think we have a shared sort of value system with the PhoneBlocks community, and the PhoneBlocks community has actually been pretty helpful in fleshing out some questions that we've posed to them. And Dave has been kind enough to sort of document through a series of videos the development process and provide insight to PhoneBlocks as well as to the rest of the world as to what's going on inside the team. So that's kind of the relationship.
Awesome. Awesome. All right, so we have at Cedar Mods is ready to go. And he or she asks, how can developers request FPGA bridge chips to begin prototyping? They want to start right now.
Okay, all right. So can he wait until tomorrow? Is that possible? So we will discuss this at some length tomorrow. So I don't want to belabor it today, but let me do the very short version. So we've been working with Toshiba to instantiate an FPGA variant of a Unipro bridge and a Unipro switch. And we're creating a couple hundred units, developer units of those dev boards that would allow you to experiment with that. We've also been working with a particular contract manufacturer. They're specifically referenced in the MDK. It's AQS. They're local here. They're small. They're friendly. And they've been working with us on the dev boards and the form factor prototypes. So by no means exclusive, but you can go to them and they have existing templates. They know how to lay out a 1x2 module. They know how to lay out a 2x2 module. You don't have to do that. You can take the MDK schematics and ECAD and take it anywhere you want. In which case we will consign an FPGA to you in order to do the near-term prototyping. Over the long run, we're obviously migrating to an ASIC architecture, much smaller, much lower power consumption, and with an M5 physical layer. And those should start being available in engineering samples for our internal team use, kind of in the late August, early September timeframe, and then from Toshiba for more general use later throughout the fall. And you'll hear a briefing from Toshiba on that topic tomorrow. So kind of the pithy version of that response is that there will be limited amounts of developer hardware available. Because there are limited amounts and because we're not selling the developer hardware, we will ask for sort of expressions of interest from developers in order for us to give it to you, and I'll describe that process in a little bit more detail tomorrow.
Awesome. All right, so stay tuned. We have another eager developer, Busy Hacking, is asking, will there be templates with minimal I/O layout already done? I think this is referring to the software toolchain you had talked about. Can I build upon and make a simple IR interface in one day? So what are the tools available to kind of quickly get modules?
So I don't want to commit to one day, but you do have all of the reference designs for all of the modules that we have to date are available as part of the MDK reference implementation package. So you should have ECAD. We will be making all of the drivers. Some of the drivers are already available. We will be making a full compilable Android distribution with those drivers available in a repository in the next couple of weeks. And so you should be able to take a template, an electrical template, mechanical template, and driver template, and instantiate. So there are sort of blank module templates. That's a standard 1x2, a standard 2x2, with all of the native interfaces that are currently available with the FPGA implementation, or you can take a complete module like a thermal imager module and just start building off of that. So all of it's out there. In some sense, you have an open source phone, the designs to an open source phone as part of the MDK reference implementations.
That's great. That's great. Okay, another question that I barely understand from MBG. This is on IRC, which I remember like when I was dating my wife in college using. So I guess we're using it now. So for those online and those that are here, there's some interesting chatter going on. We're trying to get rid of some crazy spam bots that are trying to sell you chicken. But some of you guys are finding it valuable. And MBG _ is one of you. And they ask, will the supervisor microcontroller be discussed in more detail? It seems to be one of the non-open components.
That's right. That's right. So the supervisory microcontroller, which you saw in the electrical drawings, is the entity that basically controls the Unipro switch, and it's also the entity that provides the power and EPM management for the device, so that the application processor doesn't have to, right? So this architecture kind of makes the application processor yet another module. So it's no longer the center of the architecture. It's obviously an important part because it has to run the operating system and the apps. But it's not sort of the core nervous system, if you will, of the endoskeleton. So the MDK is a module developer's kit, right? It is not an endo developer's kit. We do intend to control the endo mostly in order to ensure stability for the ecosystem. And so there isn't a lot of detail out about the supervisory microcontroller, but the API, meaning the functions that you can rely on it to perform, things like hot swap and loading of routing tables and wake detect and enumeration of devices. Those functions will be described. They are not yet all fully implemented, right? So there are a lot of placeholders in the MDK corresponding to them. But those are services that the supervisor microcontroller will provide, which we will describe how to make use of those services. But it is not meant to be a developer programmable component. It's part of the endoskeleton.
Awesome. I could use a little wake detect right now. Okay, another IRC user, RatingGen, asks, will it be possible to swap a module without reboots? And will there be a specific Android API like OnSwap, parentheses, coding language?
So I'll defer the API questions to the software talk this afternoon. But yes, absolutely. Part of the intent is to be able to hot swap everything from batteries to cameras, sensors, et cetera. I think the only things that we don't immediately envision being able to hot swap are obviously the AP, because that kind of defeats the idea of hot swap, and potentially the display, just because it's hard to do.
Okay, awesome. All right, I didn't want to discourage folks here in the room. I know you guys are being really polite. We've got about maybe 3 or 4 more questions from Twitter and IRC. So if you do have a question, feel free, step up. Also, during lunch, we'll be available. But if you want to ask a question here, we'll have some time. Okay, back to Twitter. We have @It'sShree asking, is there a way to protect each block so that if we lose it, no one can use it unless they have some password? So I guess they're kind of asking if a module has data or information and they don't want anyone else to get to it.
Yeah, so to a large extent, that's a question for module developers, right? I mean, that seems like it would be a useful feature to have in a lot of modules, especially modules that store personal information or other kinds of private information. There can be a theft protect mechanism that I could imagine, but it is not, at this juncture, we don't envision that as a platform feature, although we could certainly consider it as such if there's interest from developers. But for now, it would be on a module-by-module basis, and it would be up to the module developer to implement that kind of functionality.
Okay. And then, we have a person in person. All right.
Hey guys, my name is Garrett Kinsman with OpenMod Wireless. We're used to buying a phone from our carrier, $600 phone, but paying a subsidized price of, say, $200. In many cases, this can defeat the purpose of having a modular phone. What are you guys doing in terms of carriers to work with people to make a truly modular Android experience?
Okay, so that's a very fair and interesting question. So we have not, because again, this is meant to be a global device, and the carrier situation is very, very different from region to region. We haven't tried to establish sort of a uniform carrier policy of any sort. We view cellular communications, the baseband processing, and the antennas as yet another module that could be combined in a SoC, in a system on a chip, with the AP, as it's done by many vendors today. Could be disaggregated from the AP and in a module in and of itself that a consumer would be able to swap out. In terms of your allusion to sort of the carriers as a fulfillment channel.
Yes.
I mentioned sort of 3 canonical examples of Ara fulfillment that we've been focused on, and also said that they're not to the exclusion of traditional methods of fulfillment. So we're exploring things that are technically challenging or have other sort of business model or other issues that need to be proved out before those risks can be retired. So we're focusing on those, but again, it's not to the exclusion of more traditional methods of commerce, which also, I should point out, vary quite dramatically from geography to geography.
Oh, yes. Thank you very much.
All right, so back to Twitter. We've got KorgCube asking, will it be possible to configure Ara to not be a phone at all, as in no need for a carrier?
Want to take one?
Am I on?
Yeah.
As it's currently configured, right? You could have a SIM module that you choose not to include in your device. You could even not include a Wi-Fi module if you wanted to have no comms at all. And it could be, would still be able to run an operating system and do whatever you could do without a connection. So I think, what is a phone is sort of challenged when you can pick and choose pieces like you can on our platform. But if you define a phone by making a call over a carrier cellular connection, you could definitely configure a device that doesn't have a capability to do that.
Also, just as a parent with a 10-year-old who wants a smartphone, I love that scenario where I can have a device that's like an MP3 player, and she can kind of have basic apps, and then when she, a couple years, it can become a smartphone. So I hope we do that. Okay, Twitter, @MattValen says, how would Ara handsets be protected against the elements like water and dust, and is there going to be an IP rating? And Matt notes, this is an increasing trend. I don't know if the trend is being protected or the trend of more dust or water, but so how we know that these modules are not going to fall out anymore, but what's going to happen if I'm in a rainstorm?
Yeah, so there is, you'll note that there is an environmental section in the MDK. It's not terribly well populated at this juncture. Our goal, again, was to sort of retire the elephant size technical risks first. And so that had to do with the on-device network, with the on-device power architecture, and things like that. Our intent is to basically ensure that from a usability perspective, so from a temperature, moisture, dust, and other kinds of perspectives, it's no worse than traditional devices. And module developers would certainly have the opportunity to make modules that are more rugged or more robust against the elements if they so desire. But again, we don't anticipate sort of a significant deviation from standard industry practice on that front.
Okay, let's come back to the room. Let's go over here.
Yeah.
You have a question?
Yeah, I just had a quick question. What are your thoughts on taking the modules out and snapping them to your shoes, into a watch, into glass, and how do they interact with other wearables? Thank you.
Yeah, so this is an interesting question, and sort of, I guess, goes along with the question of can it not be a phone at all? And I think a lot of people sort of naturally gravitate to this idea of well, hey, you have a packet switch network. It has all of these services associated with it. Can it be the Internet of Things? And I don't have an answer to that. I'm not sure that I'm smart enough to answer that question. And if I did answer that question, you shouldn't believe me. I think that a lot of people have tried. A lot of people continue sort of trying on that front. And rather than trying to create a device that can also turn into a wearable, or a device that can also turn into a game controller or a thermostat or whatnot, we have focused on trying to create something that ultimately is a great smartphone, first and foremost. If it can be other things, we certainly encourage it to be other things and encourage those kinds of crossover opportunities. But the fear was that if we focus on creating the Internet of Things, we would never create anything that's great at any one thing, that it would be kind of mediocre at a lot of different things. So the focus has been single-mindedly on making a great smartphone, and we leave it to the developers and the user's imagination to explore other sort of opportunities, other branches off of that.
Okay, awesome. You, sir.
Yes, to develop like ruggedized devices like others are talking about, will the Endo eventually be opened up so that we can produce that as well as the modules? And if so, when?
So from an Endo perspective, again, the fear was early on A, loss of focus, and B, sort of fragmentation of the developer ecosystem if people started making variants of the Endo. Both of those can be mitigated over time, meaning that there can be a strict specification for Endos that allows multiple parties to produce Endos as long as they conform to the strict specification. We just haven't gotten there. It sort of hasn't been the priority has been on creating a module ecosystem, but certainly the possibility of creating an Endo ecosystem as well has not escaped our attention. We just have it's escaped near-term focus, but it hasn't escaped our attention, and the potential for that is certainly there.
All right, I'm going to go back to IRC. Nadir asks, kind of related to this endoskeleton question, what's the expected life cycle and lifetime of an endoskeleton? You're going to be putting modules in and out. Are those contacts going to wear? Like, the beauty of this thing is I don't have to buy a phone every 2 years. Like, how long are you designing that Endo to last?
So our objective, and this was in one of my early slides, was to create an Endo that can last for 5 or 6 years. There are some things that favor longevity of Endos, and some things that are difficult to do. From a favoring longevity of Endos, they're made out of metal. They're made out of aluminum, so it's a fairly robust structure. The contact pads actually don't wear out if they're capacitive. So the device that I showed here on the Elmo does have some scratch marks from the spring pins that we're using in the point one prototype. But we expect that the contactless interconnect to be fairly robust against wear and tear, and so there's no sort of cycle life limit necessarily to the connector. There may be one to the power connection. Now the challenge that we have is that in order to facilitate hot swap of modules, there is actually a small battery in the Endo that provides some reserve power, and batteries, of course, have limited cycle life. And so that does create some sort of limitation on the life of the Endo. We need to do some testing, and we actually need to do some of that testing at reasonable scale in order to be able to understand. Now, that battery only gets discharged when you're in hot swap mode and there's no other battery present in the device, right? So you can actually try and reduce the cycle times on that battery, and we need to see in normal usage patterns how long-lived can we make that reserve battery, that hot swap battery in the Endo. We're also looking at supercapacitor options, which of course don't have the cycle life limitations that batteries do. And so this is the kind of stuff that we will continue to do with the Endo, which is why we're not prepared to make the Endo an open developer platform. Why we want to continue making it great while maintaining some stability for the module developers.
I just can't wait to have a supercapacitor. That's so awesome. Okay, we're going to go over here. Gentlemen.
Hi, I teach computer science at the University of Michigan, and my view of Ara is, or my question is, have you thought about the ability of using it as a teaching tool in the classroom to help teach embedded systems and programming, not at the level of like, App Inventor, but I guess the idea that comes to mind, and I got a lot of them around this, is there a way that you could maybe design like a breakout module that would allow you to use a Raspberry Pi style environment, or Arduino shields, or students obviously aren't going to make modules. They don't have that level of experience maybe at the freshman level, but is there that you could like a breakout module that students could use as first or second year college students?
So general answer and then specific answer. General answer is I would challenge sort of the assumption that students can't make modules. I think making sort of high-performance modules that may be sort of next generation of application processor or an extremely high-resolution camera or something like that that really push the envelope, that may be too much for a design course. But I do think, and I strongly encourage the adoption of this as a teaching platform, so that 5-10 years from now we have a whole generation of engineers who just think this way, and have this platform-centric modular thinking, and that doesn't require me to stand on a stage and convince people of the merits of it, right? That's just the first thing that people naturally think about, as they do with apps today, right? Like, why don't I make an app for that? So that's kind of the general answer. The specific answer to your question is we haven't created such a module, but absolutely nothing prevents you from taking a 1x2 or 2x2 module template and creating a breakout from that module template to either Arduino or Raspberry Pi or Yo-Yo or whatever your development board of choice is.
Do you plan to have a program for universities to sign up? Like, I volunteer, if that's the case. I would love to bring this into my classroom and do exactly what you were just talking about.
So I think you shouldn't wait for us to have a program. I think you should just do it, and then it's your program as opposed to my program, right? So we want our vision in general has been to be as sort of as helpful but hands off as possible to the module developer ecosystem. So we don't want to micromanage it. We want to set some governing principles. We want to maintain the platform, and beyond that, we just want to facilitate you guys. But we don't want to micromanage the ecosystem. We don't want to run sort of a variety of programs and structure the ecosystem in the way that we imagine it should look like, because undoubtedly you have better ideas than we can imagine internally. Thanks.
And also, tomorrow, we're going to have a Make with Moto showcase session where we're going to talk about some of the folks last summer who used some of our very early developer tools. And actually, one of those guys, Mickey, is going to show you one of the projects that he's developed. And he's been thinking about how to create basically a module that interfaces to all of these kind of languages and components of hacking like Arduino, et cetera. So he'll share some stuff tomorrow. And if you want to work with him on that project, I'm sure he'd love some collaboration. All right, over to here.
Matt Stoker, Pixio, and a University of Utah. I echo the comment about education. I think that's a wonderful thing. I was considering configurations that have no traditional capacitive touch display, using things like projection and gestures for interactions. Is there a particular tie that says you must have a traditional capacitive touch display that would be required at the kernel level, things like that?
Not that I know of. So there's philosophically, from an MDK perspective, there is not. The only reason if I sound slightly hesitant, the only reason I sound hesitant is I don't know whether the Android compatibility document requires it.
Me too. We have
but we've certainly imagined platforms with keyboards and perhaps not quite as ambitious. And so maybe this is an example of why I shouldn't be imagining modules. I should just ask you to imagine modules because yours are way cooler. And so from an MDK perspective, from an Ara platform perspective, by all means, if there are some Android limitations, let us know.
Great, thanks.
And we'll go over here to this gentleman.
Hi, I'm Pete Van Kessel with Knowles Corporation. The skin of the phone is something that Google plans to supply through the 3D printing process, right? Have you guys given any thought to how you're going to address modules in which the shell or the enclosure is actually a part of the system and has an impact on the performance of the module? This, for example, would be the case in an acoustic module like a speaker module. I could also see it potentially being applicable in the RF modules. But have you guys given any thought to how you're going to address, say, differentiation among module makers and that kind of thing?
Yeah, so yes, we have, and in particular in the context of acoustic modules. So there are two approaches to it, right? One is that you can, within the 3D printing framework, right, create a module that has gills or slits, right, that allows for the air cavity to have to push air to the outside world, and similarly for microphones. in the opposite direction. So that's one approach, and that's certainly supported in the current sort of the way the MDK is currently written. We have been noodling the idea of for particularly exotic applications, right? So there are some medical sensors, right, that just can't live, that have to have some non-traditional material, or even more traditional applications like the thermal imager, right? It might have to have a special optic of making those things non-3D printed and facilitating that. So I think that there are we absolutely want to support what you're describing, and it would be helpful because I think none of us on the team are acoustics experts. It would be helpful if you told us how best to support you, and we will ensure. I mean, that's part of the purpose here of these kinds of events, right?
Great. Well, thanks. I appreciate it.
Okay, we will go to IRC. We've got a question from Rip, which asks, have you settled on a particular MFi HS gear across all modules on device, or will that be left to the module-to-module requirements? You want me to take this one?
Go for it, Dan.
Yeah.
Come on.
We have not yet settled on that, but wait for tomorrow to the MFi session, and they'll talk more about it.
It's actually today.
Today.
And I think, and I'll let the network team correct me for the record in the afternoon if necessary. But so the intent is to support high-speed gear 3, and all gears below that, so that if you throttle down, I don't see Jürgen saying shut up, so that must be about right.
Awesome. I was going to say gear 3. That's what I was
the right
thinking.
gear.
Yeah. Okay, so Smadger asks, will it be possible to create dual function modules? For example, a battery combined with Wi-Fi, or will it have to be one function per module?
Yeah, no, there's absolutely nothing in the MDK or in the vision that speaks to the partitioning of functionality across modules, right? So there's probably a minimum set of things that you have to have, but they could all conceivably live in one or two modules, like a display, and you can imagine like a integrated Wi-Fi AP battery kind of thing. In fact, funny story, in the prototype device, so we use a Samsung display here that we do a little surgery on in order to make it. I guess I should be showing it this way. In order to make it fit, and obviously it wasn't custom designed for Ara. It has some voids in the back and behind the display, and so we filled those with battery just because we could. And there was space, and why not fill it with battery? And so the display kind of neatly exercises the flexibility of the power architecture in that it serves as a power source, and then when that battery discharges, it serves as a power consumer. And it can in fact charge that battery from another battery on the device, or charge it from a charging module in the device. So the power bus is meant to be flexible enough to support all of those permutations. So I think within the quality of service that's offered by the Unipro MFi network, which is kind of tens of gigabits and microsecond latency, you can decide how to partition, or module. The community can decide what best partitioning of functionality or integration of functionality is appropriate across modules. We want to support all of those.
Awesome. All right, we're going to have about 4 or 5 more questions. I think the folks here physically in the room, we're going to have a little bit of extra time for lunch. Before we do that, we'll have a little icebreaker. Those online, you've been with us for hours now, and you probably can take bathroom breaks at your leisure, but you're probably also ready for a bit of a break. So just 4 or 5 more questions. We're going to start here in the room. All right, go ahead.
Hi, my name's... Hello? Hi, my name's Shandon Hart. I'm from Corning. I was just going to ask 2 questions, actually. One is, the rear modules, you've prescribed the size. I think the maximum size is 2 by 2, 20 by 20 for the rear modules. Is it feasible to create a rear module that's actually larger than that, but that jumps over one of the ribs? And does that make sense?
It does make sense.
My second question is somewhat related to that, and that is it feasible to have rear-facing display modules as well?
So the answer to your first question is we do not allow, from an industrial design perspective, the industrial design language doesn't allow jumping of internal ribs or the spine, but it does allow jumping of the end caps, right? So as with the example of the pulse oximeter, right? It slots in and it jumps the end rail to protrude beyond the span of the device. And I'll defer to our industrial design lead this afternoon to sort of describe why that is. Your second question was rear-facing displays, and absolutely. There's nothing that prevents a rear-facing module. In fact, the tactile configuration construct that I talked about, the in-store programmable modules, our intent is to make those modules rear-facing touchscreens so that consumers can interact with the module directly and make it do things as part of their configuration experience.
Cool. And then a question over here.
Hi. My name is Elizabeth, and I see you've already got a pulse oximeter, which is great. It's a momentary pulse oximeter. You get a few seconds worth of data. Have you already got one that does an all-night pulse oximetry or an all-day pulse oximetry? I'm loath to reinvent the wheel.
Right. So the answer is no.
Okay.
And the broader answer to that question is also that we're not trying to make modules to sell, right? So this isn't like a pulse oximeter that we're going to stamp with Google brand and put on the market. The intent of the form factor prototype that I'm showing is basically to prove that the platform works and to explore some edge cases, both from an industrial design perspective, from an interface perspective, from a user experience perspective.
Well, what I've mostly done is medical data analysis. So I'm interested in, can I get data from the patient to the phone? And I wondered if you'd already done that.
We have not.
Okay.
We have not.
Yeah, but Paul loves his phone so much that really he sleeps with it, right? And so he's going to get continuous blood concentration all night. No, but I think that's a great scenario, and this is one of the great things about Ara is it allows folks with really specific needs to kind of create scenarios where maybe use a mini endo and kind of do something really custom.
Okay.
So.
Thank you.
All right, so you, sir.
Hi, Dieter Bohn with The Verge. You may have actually talked about this and I missed it, but you guys are planning on creating a marketplace to sell modules, and I'm wondering, is Google planning on taking a cut of the hardware sales in the same way that an app store takes a cut of app sales?
Yeah, so there are a variety of different business models that could ultimately support the project in the long run. And as I mentioned, sort of in my emphasis on the ATAP model and the demonstration at convincing scale, those downstream business models, our job is to again retire risks and prove out various options, but to preserve that option space for our brethren in the product organization. So the answer to your question is I don't know, but there's a number of different sort of touch points, and Google is also very good at monetizing content through the device.
Cool. And then over here, Daniel, who is part of our Make with Moto experience in Texas. All right.
Right. So yeah, my name is Daniel, and I'm actually at the University of Florida right now. And one of my big hobbies is PCB design, the schematic and the layout. And it seems to me that you've built this this whole ecosystem where you're trying to make things as easy as possible, validate, simulate, so we can minimize the capital investment. But one of my worries is there still will be a point where you need to make some prototype PCBs, and some of the things that the MDK requires of modules is, for example, for the capacitive pads, you'll need filled vias, and it particularly specifies black solder mask. And I was wondering if Google was if Google was planning on or could sponsor for smaller developers and hobbyists just a couple of panels at a PCB manufacturer or something where this what you could call, I guess, the standard Ara flow is the standard PCBs are manufactured to standard Ara specs, so that it could maybe bring down the cost of prototyping.
Right. So as David talked about in his presentation, you don't have to instantiate the MDK from scratch, right? We want to obviously give you as the golden standard, right? We want to make sure that you can. Most people probably won't, except sort of some of the larger players that can that have the resources to say instantiate the Unipro stack, the Unipro controller, right, on their own, and do some of those things. So I think as time progresses, and hopefully not too much time, so we're talking about months, not years, that there will be off-the-shelf items, right? So you could go to your DigiKey catalog and buy a 1x2 module PCB, right? That's mostly blank, right? But that has the interface block, for instance, or has the module base, right? Or other components, right? Depending on what degree of customization you're interested in doing on your own versus what you'd like to buy off the shelf. So that doesn't exist today. Again, we're sort of in the very first throes of this, right? You're here at conception. But we would anticipate and support and stimulate that kind of ecosystem to emerge, so that these things are readily available from a catalog.
Thank you.
All right, we're going to wrap up this stimulating Q&A session with licensing about Unipro. So Yari2 on IRC asks, what are you going to do about Unipro licensing? The claim that it is open source isn't 100% true. Unipro controllers and PHYs are not open but proprietary. How do you enable this ecosystem?
So actually, it's an echo of the same response that I just gave, right? So we are the Unipro standard and the MPHY standard. They are industry-wide standards that are available through the MIPI Alliance, which is the industry consortium. So anybody can join MIPI, get those standards, and instantiate them on their own. They are relatively complex modern protocols, right? That have speed gearing and various quality of service measures. So instantiating them is not a trivial task, right? It's not something that you do in a couple of days. So we are also trying to ensure that there are FPGA implementations, there are ASIC implementations, and there are potentially whole module, blank module level implementations of those protocols. And there's a vibrant competitive ecosystem outside of Google that provides all of those components, and that you can just source them in the same way that you can source USB components fairly ubiquitously and from a variety of different vendors. And not everybody has to purchase the USB spec and instantiate it on their own. So I think that goes. I think that goes for Unipro and MPHY that the questioner asked about.
Okay. Awesome. Well, guys, let's give a big round of applause for Paul and David. You guys have been awesome. Awesome.
Thanks, Daniel.
All right, so we're just going to do a quick little activity before lunch here in Mountain View. And for those that are online around the world, some of you are going to go to bed and take a nap because it's the middle of the night. And some of you guys will get back to work, whatever else you were supposed to do today. Now, I just want to say that it's exhilarating for the Project Ara team to have you here. We've been waiting 20 months for this moment to connect with you. This project is about you, and we're excited about the things that you'll create. Ken Gabriel talked about that this morning, that the success of this project is directly related to the innovation and the quality of the work that you guys do, the people here in the room and online. And so we've been talking at you a lot this morning, but like any good relationship, we need this to be reciprocal, right? So I'm going to be helping to facilitate a little bit of a Q&A session at the end of each of our sessions on the live stream. For those of you on Twitter, it's #AraDev. For those on IRC, it's AraDev is the name of our channel. And so we're going to be asking speakers questions from online and from the folks in the room, and we really want this to be participatory. So in that spirit, we're going to do a quick icebreaker. To begin, I'd like you to raise your hand here in the room if you do not have a writing instrument. Please raise that big and high, and Jason and Andrew are going to run around and give you guys crayons. Trust me, it's going to be awesome. For those of you at home or online, you can put your hand down. I'm not talking to you. Go around and find a piece of paper and a writing instrument, a crayon, a marker, and a pencil. All right, keep your hands up. Crayons may be thrown. Okay, so I'm going to give a little intro to this icebreaker, just so you understand what we're doing. Now, actually, how many of you guys have heard of a guy named Bob McKim from Stanford? Raise your hand. You may need a crayon, or you may know Bob McKim. either way, Bob McKim was one of the very first professors at Stanford who started to kind of look into this whole field of creativity. And many of you have heard of the Stanford D School and their design program and kind of what that's done. And he was the guy that was at the beginning of this. And he researched creativity. And he would do this exercise to kind of study creativity. And this is something that Jason and I, last summer on the Make with Moto tour, did pretty much at every event that we were at. So I apologize to Daniel and to some of the other folks that were with us on Make with Moto. And what I'm going to have you all do this activity in a second. But first, it looks like we're all crammed up. Okay, so what I want you guys to do is stand up, take off your name badge, and I want you to find someone nearby that you don't know, and I want you to exchange name badges, and then sit down next to them, okay? If you're online and you're alone, you can go to your cat. You can maybe even go to the mirror, okay? So take off your name badge, find someone you don't know, exchange name badges, so you should now be holding someone else's name badge, and you can sit down next to them. Okay, I see most people sitting. We got a couple more people trying to find someone. All right. Okay, let's begin. So, you by now should be holding the name badge of that's not your name, someone else. And they should be sitting right next to you. And you should have in your hand a writing instrument, a crayon, a pen, a pencil, whatever you got handy. And I'm going to give you all a simple task. Okay, so get your pens ready. Now, the badge here in the conference has all this stuff on it. So what I'm going to ask you to do is kind of take the little empty space above the name, and that's going to be your little canvas. So you're going to draw in this area in a second. And here's what I'm going to have you draw. You have 60 seconds to draw the person whose name tag you have. Go. If you're online, you can draw your cat. You can draw yourself in a mirror. We want you to participate too. All right, 45 seconds left, folks. All right, we are halfway done. 30 seconds, folks. Fifteen seconds. 10. 5, 4, 3, 2. Okay, pencils down. Okay, now share your masterpiece with the person who you're next to. Okay. Awesome. So for those of you that are not here with us in the room, here's the scene. We had, as soon as I said the word draw, actually, as soon as I said the word crayon, I felt like a wave of like embarrassing anticipation go through the room. And then when I said the word draw, it like actually came out verbally. There was just like this like, right? And then, just now when people were sharing their drawings, there was a ton of laughter. I heard a couple of I'm sorries up here. I think I might have heard a curse word over here. Now, and I don't know what happened at home. For those of you that like drew yourself in the mirror, you may not have been as embarrassed. Who knows? Let us know at hashtag Ara Dev. Now, Bob McKim did this activity with hundreds of people. And what just happened with all of you was exactly what happened every time he would do this activity with adults. There'd be this kind of nervous kind of excitement, and then there'd be apologies, and then there'd be this kind of nervous energy, right? Now, something different happens when you do this activity with young kids, especially before, school age. Any guesses as to what happens when you do this with young children? They're proud of their work, right? And actually, it's not even that. What he found was they're just neutral, right? They're just like, okay, draw this guy over here. Okay, boop, 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 boop. What's next, right? Like, draw God. Okay, do, 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 do. Boom, what's next, right? Because children don't have this socialization that some of their creative output is going to get the praise of their peers, but some of their creative output, people are going to tease them. And I've got 3 kids, 15, 13, and a 10-year-old, and I can see, especially in the middle school years, that ruthless kind of teasing, like, oh, that stick figure looks like crap, that kind of comes, right? And you start to shut down, right? Now, we do this activity with you guys because it proves to me that creativity is not this rare gift of a few geniuses who, lead the design of projects. We are all creative. We are all creative, regardless of our discipline. We have a desire to express and to explore, and the thing that holds us back is the fear of failure. And actually, if you want to get a little more inspiration about this, you should check out Regina Dugan's TED Talk, and it's essentially about this. And Project Ara will only succeed if we and you and the first owners of the device are ready to kind of let go of that fear and to really be creative and to really be confident in my own design, that I can make my own thing. And we just wanted to encourage all of you guys throughout the conference today, throughout the sessions and those online, to just really connect in and ask us whatever you need to ask. And as you go through the process of thinking about and prototyping and creating the heart and soul of Project Ara, which is all of these functional modules, to kind of let your best creative talent shine. And I don't mean drawing all the time. You can keep the crayons. We have more. But your creativity sometimes is going to be expressed with like Gear 3 and M5, whatever. Or it's going to be expressed in your code or in your engineering and your PCB layout. And so anyway, we want to thank you guys for coming. We're going to take a break here in Mountain View and have lunch. You're going to have a little extra time. Please be back at 1 o'clock. We're going to have Elwin, who's sitting there in the back corner. He and his team have been working for months preparing the 81-page MDK for you. And he's really excited to kind of walk you through it. And we're so glad you guys came. And thank you so much. Let's break for lunch. All right. All right. Welcome back from lunch, everybody. Hope you had some good food down there. We're going to get into some sessions now around the MDK. Okay, raise your hand if you have downloaded the MDK. Raise your hands if you have read more than 50% of the MDK. Okay, keep your hand up if you've read all 81 pages of the MDK. Nice. Well done. You probably slept really well that night. So we've had an amazing team of folks. You remember that diagram that Paul showed of all these different companies and teams that we've been working with. So they've all been coming together and under the really wonderful kind of facilitation of Elwin. I want to introduce Elwin. Elwin can tell you more about himself, but he was at MIT for a little bit, UCLA, so he's kind of bi-coastal. And I asked him, Elwin, what was the first thing you ever remember making? And he had to think. He's like, I don't remember much in the past. And then he's like, oh, Legos. And I was like, well, tell me about Legos. He said, well, I grew up in Malaysia. And I didn't know this, but we had knockoff Legos because my parents cheaped out on my toys. And I only knew that because I would hang out with my other friends who had real Legos, and there was no interop. So now I want to introduce Elwin to you, who's going to create a world where everything can work together. Elwin.
Thank you, Dan. Thank you, Dan. That's a great intro there. So my name is Elwin Ong. I'm the lead author of the MDK. So this afternoon, we are going to give you a guided tour through the MDK from various members of the team. So I'm here to start us off. I'm going to provide a little bit more context as to what you'll hear later this afternoon. I'm going to tell you about the objectives of the MDK, tell you how it's organized, where you can get it, and then lastly touch on support as you get started on your development. So first and foremost, the MDK tells you how to create modules that are compliant to the Ara platform. Now there are two aspects to this. There's the objective platform, and then there's the prototype. So in many aspects, they're one and the same. So the fact that we have an endoskeleton, the form and the shape of the modules, and how they fit into an endo, those are consistent between the prototype and the objective platforms. In other areas, in particular the network stack and the software stack, the prototype currently differs from the objective. So in the case of the network stack, as you've heard, we are implementing very advanced M5 and UniPro standards. And so ASICs that implement these protocols are not yet available. So as a result, we are using FPGAs for the prototype. And those aspects are documented in the MDK. Same for the software. So it takes some time, it will take some time to mainline some of the changes we need to make to Android. So in the meantime, we're using a customized version of Linaro Android distribution. So the second thing that the MDK provides are reference implementations, which is just a fancy way of saying examples of how one complies with the specifications. So we provide in the MDK prototype module designs, but more importantly to this crowd, we provide module templates. So module templates include the actual 3D CAD models, EDA models, as well as their derived works like the line drawings and the schematics. And we will make the software available as well. So that enables you to easily take your device, plug it into the model, and then hopefully easily generate an ARA-compliant module. Sometime in the future, we also intend to put together as a separate category of items best-known vendors. So for example, there are various IP vendors out there who provide IP for UniPro and for M5. So we'll call those out specifically in the MDK. So there are two aspects of the Ara platform that the MDK does not address. So we address the endo only insofar as some knowledge of the endo is required for you to develop modules. So you need to know how the endo interfaces or fits into an endo. And then you need to know how it interfaces with the supervisory controller to perform system-level functions like EPM control, but also enumeration and wake detect. Secondly, the Ara platform has this unique architecture where users can create custom module shells that are independent of the functional modules themselves. And so we will provide, or intend to provide, specifications as well as reference implementations of how one creates design apps that will enable users to generate their aesthetically custom module shells. So in fact, 3D Systems is here, and they will provide a preview of that tomorrow. And we will, of course, have a lot more to say on this topic at the second developer conference. So how is the MDK organized? This list largely follows the order of the presenters that will come after me as well. So in section 1, we have licensing. So this section covers actually the licensing of the MDK itself. And Stephen Hahn, our corporate counsel, will be here later this afternoon to give you a presentation on that. But it also covers all the licensing requirements that the MDK references. So a good example of that is the MIPI licensing requirements. Section 2 is industrial design. And Dan Clifton will be up here shortly. And this is, I like to call industrial design, or this section, the MDK, how do you design a modular smartphone that is also elegant? In section 3, we have mechanical and layout. Ara Kanayan will give you a tour inside an Ara module. He'll tell you about the various subassemblies, as well as the various interfaces, including the electropermanent magnets. In section 4, we have power. So the Ara platform has this very flexible power architecture. It enables users to have, for example, multiple batteries, multiple chargers, to be able to swap batteries even while the phone is powered. So Seth Newberg, who's our electrical lead, will guide us through the Ara power architecture. And then section 5 is the network stack. We have Jürgen Urban from Toshiba, who leads our network stack development. Jürgen is also the chair of the MIPI Unipro working group. And so he'll actually have 2 presentations. He'll have a presentation on Unipro and MIPI, and then he'll have a presentation on how Unipro and the various network protocols are implemented on the Ara platform. In section 6, we have software stack. Marti Bolivar is our software lead, and he'll give you a roadmap as to how we think we need to modify and adapt Android and the kernel to support all the various modular use cases that the Ara platform provides. Section 7 is system-level functions. Ara Kanayan will cover that. And those are things, as I said, EPM control, wake detect, and also enumeration. Sections 8, 9, and 10 are environmental, module marketplace, and regulatory certification. I will be back to discuss those topics. So let's set the stage for what you're about to hear. So this is an Ara phone. It's composed of 2 things. There's an endoskeleton, and then a set of modules. So everything else is a module, right? Besides, so the endo has a front and a back, right? And so the way we define the front is that's fairly obvious. The front is where the primary display module lives. Now, top and bottom is a little bit trickier to define because you can flip this phone, right? And you can easily apply the top and bottom definitions the same way as you do, as you see in this picture. So what we've done is we've defined the top of the phone as where the where the volume buttons on the display module is biased. So with those 2 quantities, known, then you can define the axes of the phone. We use the Android reference. So the positive X points to the right of the display. The top and bottom are defined in the Y direction, and then the positive Z direction comes out of the display. So peeling back the modules and looking at the Endo itself, what you'll notice here are the locations of the interface blocks, which is the back plane where the electrical and contactless data connections are made between the modules and the Endo. What you also see is a singular vertical spine with ribs that go across horizontally. What you also notice on the front of the Endo is that there is no vertical spine, and the horizontal ribs go all the way across the width of the Endo. So the spine and the ribs is what forms the module slots and enables users to easily slide modules in and out of the phone. So how do you get the MDK? Well, looks like lots of you have already done so. You can download it now on projectara.com. We've put together, I think, about a 100 megabyte zip file. It includes the main document as a PDF document, as well as all the reference materials in the module templates that I previously referenced. We will also make available a Git code repository with all the custom Linaro Android distribution that we've been working off of on the prototype. Now, I want to emphasize that this is not meant to be a separate or independent Google product. This distribution is essentially just for prototyping work on the Ara platform. So that is coming soon. We're just doing some final open source licensing reviews, and we'll announce when that will be available. Finally, how do you get support? So we've stood up a Google Groups forum. This forum is just for developers. It is not intended to be a general forum, so please don't use it to ask, consumer-type questions or press questions. This forum is to serve you guys, the developers. We will have people who moderate the forum in the upcoming weeks and months. So there's actually a lot of lively conversations that have already occurred on the forums. One of the threads have asked about getting prototype development boards. And so limited quantities of these development boards will be made available through our contract manufacturer, AQS. And they, of course, have the expertise as well to provide all the layout services. So if and when you want to develop your own dev boards or create form factor modules, they'll be available to support you. Lastly, we have an email account. I want to provide a caveat in that we have fairly limited resources, so it's entirely possible that we won't be able to address every single concern or question that comes up. What we will do, however, is to maintain an FAQ on the forums. There will be myself and others on the team will monitor the forum, and we will update that FAQ as necessary. And lastly, tomorrow, after you've heard all about the MDK, we welcome your feedback. And so there will be a feedback session tomorrow afternoon in one of the tracks. I know that Paul touched on the fact that we're trying to stand up these model-based designs, and in fact, my thesis is on that topic, and I very much welcome that future. But in the meantime, hardware is different. You can't just compile hardware, so we understand that, and so we have dry erase boards, and you'll be able to do this feedback session more organically. So look out for that, and please, we totally welcome and want to hear from you, all your feedback. With that, I will give it back to Daniel.
All right. Awesome. Thanks, Elwin. Okay, cool. Okay, so I just want to share with you the format. We're pretty much going straight from now until the end of the day, until 6 o'clock. And you can see in your program the various topics in the MDK that the leads for those areas will be talking about. And so we want to encourage you guys, as you need, to take breaks. You may be more interested in the kind of mechanical design or kind of the network stack. So feel free to kind of stay for those sessions that are most compelling for you. And I see a lot of people gathering around outlets for extra power. But feel free to kind of, spread around the Computer History Museum, or if you're at home, you can go from, your bedroom to your living room if you want a break. Okay, so we're going to have half-an-hour sessions. Some of the sessions are a little longer. And what we're going to do is, if we have any questions on either Twitter or our new IRC channel, which is Ara Dev IRC, which allows us to get rid of spammers a lot more easily. If you have any questions during each of the sessions here, post them out, and we'll have a couple minutes at the end where we can kind of get some questions out. So without further ado, I want to introduce Dan Clifton. Dan Clifton is one of the lead industrial designers at New Deal Design. New Deal has been an amazing partner for us. We've had lots of folks on their team. And Dan has been one of the folks leading the industrial design. Now, the first thing that Dan remembers making was actually a car. He built it pretty much from the ground up. It's like a hot rod. He started it in high school and finished it in college. And he wanted to say, he didn't want me to tell you how fast he goes, because he'd be worried that his girlfriend would prevent him from using it anymore. But what I want to say to Dan's girlfriend is, Dan's a responsible guy. He designed Project Ara. He's going to be just fine. So Dan, welcome. And let's hear about the industrial design.
All right, thank you, Daniel. Okay, so today I'm going to share some of the industrial design with everybody. As soon as I can find this. So if we think about smartphones today, they sort of all look relatively similar and kind of do relatively the same thing. And this makes sense based on how these phones are mass designed and mass manufactured. But what if our phone was modular? And what if it was made in a different way? Can we make a modular phone be more human and unique like us? So, we wanted to design Project Ara for all humanity. We wanted it to be for people of all walks of life, everybody from the CEO in New York City to the alpaca farmer in Peru. This was for everybody. We wanted it to be empathetic and vibrant, just like us. Ara is not meant to be this monolithic black box that you see here. Ara is inherently modular, and we wanted it to look and feel that way. This needed to come across. We wanted Ara to be this dynamic, thriving expression of things like art, design, technology, and above all, personality. So, what we did when we started was rethink the phone's physical architecture. This really was required by modularity. This was the only way to achieve successful, useful modularity. So we had to rethink the phone's construction, how it's made, how the enclosures are done, all these things. And what we did is create a new set of architectural rules. So we used a platform approach when designing the product. And actually, we're not designing one product. This is a system, like you've seen. This is a system of 3 phone sizes. We also used a platform approach for designing for 6 billion people. So on one end of this platform, we have these inexpensive phones. Could be only the Wi-Fi phone, where it only has Wi-Fi modules, and this could be great for places like developing worlds where no one's even used the internet before. And then on the other end of the platform, we have these very expensive phones that could be thousands and thousands of dollars. And this could be a phone that's filled with really amazing medical modules and could be used in hospitals, saving people's lives. So, since we're industrial designers at New Deal, one of our top priorities was creating something that was just absolutely inspiring looking. We wanted to have this visceral, emotional connection to the object. This is something we always try and strive for. We want your eyes to light up when you see it. And this was kind of my first reaction when I saw these appearance models. I had seen the renderings actually for weeks and weeks. But the first time that I saw the appearance models and I saw the interaction that we could have with these objects, it really just made my eyes light up. So we also designed Ara to be timeless through personalization. One example of what this means is the ability to repair or upgrade your phone. So let's say you're out and you happen to drop your phone, smash right on the concrete, your glass of your screen just breaks. So now it's in a million pieces. So now you don't need to throw out your device. What you can do is just simply go to the store, pick up your new Ara display, put it in, and it's a few minutes change. Very quick, very simple. And that's how the phone is one of the ways it's timeless through this personalization. So another concept of this is being able to personalize your phone sort of as you go, as it has its lifetime with you. So one example is, let's say that you have a picture that you want to put on the back of your phone, and it's of your girlfriend, okay? But then 2 months later, after you have your girlfriend on your phone, you break up. Now you have a picture of your ex-girlfriend on your phone. And that's not cool. So what you can do is just print out a new module shell with your new girlfriend on it, put that in your phone, and now everything's great. Another aspect to this timeless through personalization is being able to have the phone flexible on a daily basis. So what this means is that you could actually have two endoskeletons, a large one and a small one. And during the day, maybe you watch a lot of video and you want that large screen, so you populate your modules into this large endoskeleton. But at night, you want something a little more lightweight when you go out, so you populate some of those same modules onto your smaller endoskeleton. So this is a really cool feature, how it's flexible on a daily basis. We wanted modularity to be this magical experience. It needed to be absolutely easy for people to use, and we designed it to not have any connectors or any protruding features. We just have these smooth, clean modules. And another thing what we did to make this modularity really magical is add these electropermanent magnets, and these lock the modules in. And the first time you kind of experience this and feel those modules lock in, this is all done via the software. It's really this powerful moment that really makes you smile, and these are the types of reactions we want. We wanted to communicate modularity visually with this product. We wanted to embrace this modular aesthetic, and the endoskeleton was really the signature of this look. So we played it up as much as we could. You can see here it's a different material. We're using metal for this endoskeleton. The modules are different material from that. And it creates this extremely strong icon for the product and for the brand. Here you can see some exploration that we did of how we can communicate modularity visually. Some of these don't even really look like phones, but that's actually a good thing in our office. A few more ideas. And you can see how it led to actually the device we have today. So next we have parceling. Now this is an extremely key element to our platform. It really is what makes everything work together. This is the same concept as land parceling or parceling with urban planning. It's a very similar idea, but we're using it to divide up space on the back of our phone. And what we discovered is that this is something that is becoming crucial to developers in helping them, give them guidelines for developing their modules. And you can see here, we're doing the parceling with our spine and ribs on the phone. So we've created these parceling standards. We have a standard module size. This is kind of the footprint that a developer can design in. We have a standard physical connection. This is how the modules actually attach to the endoskeleton. And we have a standard electrical bus, which is how we're doing power and data transfer. So all these things developers can design around. Now, here you can see our parceling grid system. Each unit on this grid is 20 by 20 millimeters, and you can see our 3 phone sizes. We have our large, which is a grid of 4 by 7, our medium, which is a grid of 3 by 6, and small, which is a grid of 2 by 5. Now, the base unit that you see, this 20 by 20 millimeters, this size was driven by understanding some of the components that go into the phone, and also understanding how this unit can scale to create our different size modules. So here you can see our module classes and how this unit, base unit, scales to create the modules. We have our 1 by 1, which is the smallest unit. We have a 1 by 2, which is twice as big as our 1 by 1. And then we have our 2 by 2, which is 4 times as big. Now, where this really gets interesting is when we look at shared modules between our 3 devices, our 3 sizes. Our 1 by 2 module is compatible with any of these 3 sizes. So a developer can create that and know it's going to work with any phone. The 2 by 2 module is compatible with the large and the medium, and our 1 by 1 is compatible with the medium and the small. So here's our universal electrical bus design. This is designed around an interface block. What the interface block is kind of the dark rectangle, the black rectangles that you see on the bottom of the modules. These also correspond to the black rectangles on the endoskeleton, and these house the power pins, the communication pads. We tried to organize these as much as we could and kind of keep them tight in nice contained areas on the product. So because we have our module classes and we have our universal bus system, we can have flexible module placement on the phone. So modules don't have to go in a certain place and kind of always live there. They can go in any bay that is the right size for them. So you could take your camera module and move it from a vertical bay to a horizontal bay very easily. Here you can see some of our rear rib arrangements. There's many different layouts that we have here. All of these are based on the grid that you saw earlier. And we've created one rule here. The rule is that there's only allowed 1 cross of rib and spine. All of these that you see here are following this rule, if you look closely. The reason we're using this rule is to keep a certain dynamic look to the phone. The more crosses that you add, it becomes more static looking, and that's something that we want to avoid. We want to keep this really dynamic look to the endoskeleton and to this signature of the phone. Here you can see some of our front rib arrangements. The front parceling is driven by our display sizes. So most of our phones now have pretty large displays on the front of them. So that really is sort of controlling the way we're parceling the front and understanding that need that people like their large displays. There's fewer layouts here on the front parceling. We've created a rule of 2 ribs maximum. If we kind of have more than 2 ribs, the modules just become small, and it's not practical for these large display modules. Oh, and we also have a keyboard module, which some people will love. Our Ara modules, they're inspired by these smooth, flat pebbles. This is something like you'd find these pebbles out by the ocean or in a riverbed, and they have a very warm kind of feeling to them, something you want to pick up and hold. They're very friendly and have these kind of more human qualities to them. And we wanted to instill some of these qualities into our modules, so that's what they were inspired by. So this is part of the overall module design language that we've created. What this design language is a set of design elements used to visually communicate a specific aesthetic. Now, the reason we've created this design language is so that when you're buying modules from different third-party vendors, they're going to be coming from all different places. And we want them to have a cohesive look once you put them all on your phone. We don't want them to look like they came from all over. We want this holistic and cohesive story once you put all these modules on your phone. So that's why we have our design language. So some of these elements of the design language are these 1.5 millimeter corner radii. These are on all four corners of the modules, no matter what size the module is, whether it's a 1x1 or a 2x2, or even the front modules. And this corner radii also is going to be related to the endoskeleton, where the ribs and spines meet. These are also going to have the 1.5 radii. So here you can see our locking side profile. This profile wraps all around the four sides of the module. And it's essentially this dovetail concept. And this idea of a dovetail for holding things has actually been used for thousands of years. And it's really critical to the way we're attaching modules. This dovetail plus the electropermanent magnets are what makes the modules stay in place. And it's really interesting, actually, how we're using such an old sort of technique of dovetail with electropermanent magnets as this new technology. So modules should keep to these rectilinear footprints that you see here. These are described by our 1.5 radii and our lines that are 90 degrees to each other. So you can see the modules here have different textures, different colors, different finishes, and things like that. But because they're following these rectilinear footprints, they all can fall in the same family still. Modules should use these flat planar surfaces that you see here on our IR camera. These surfaces can be placed at angles to create different geometry. Here we're creating this geometry to house the tall camera component. And we should have these small surface transitions in between our planar surfaces of about 1.5 millimeters. Now, we also have Y dimension expansion. This was talked a little bit about earlier. This allows modules to expand outside the phone's perimeter. And we're allowing this on the top and the bottom of the phone where you see these dashed lines. We're not allowing it on the sides. And what this does is it can create some really great opportunities for developers. We really want them to get creative with this sort of opportunity and see what kind of awesome things they can create. So one kind of exercise that we did to create something is the pulse oximeter that you've seen, which measures your heart rate, your blood oxygen level. You can see here we thought about, what's the interaction of this? The doctor would be holding the phone, you can see the screen, and the patient could put his finger on the sensor. So really interesting interaction with this Y dimension expansion. Now we also have our Z dimension expansion. This is going to allow us to accommodate components that are very tall in Z. An example here is the IR camera. And the rule we've created here for how to create this taller Z modules is that you continue our trapezoid form. This is the natural form created by our dovetail shape. So if you continue this trapezoid form, you can grow the module in Z very easily. This can be used if you need to grow it, 10 millimeters like you see here, or if it only needs to be 1 millimeter thicker. You can use the same technique. The color, material, and finish story of Project Ara has two main parts. The first part is about personalization, and this is enabled by some really amazing 3D printing technologies that you'll hear about later. And the second part of it is retaining some elements of the Ara identity. This is so that when people customize their phones, there's something that holds all these phones together into the Ara brand. So for the CMF, we wanted to maximize the area that you're able to personalize. So you can see here on our modules, what we did is we wrapped the module shells all the way around to the bottom. So what you see is all customizable area. The only part you can't customize on the module is actually the bottom aluminum plate. So when it's in the endoskeleton, the modules look fully customizable. And in the Ara configurator, there's going to be some really amazing ways that you can create really beautiful phones and help guide you through your creation. And one of the goals we wanted to have there is not to limit you and to really open up this configurator for your creativity. So one example of this could be our Mexico phone that you see here. This is actually what inspired the look of this phone. So it's inspired by a trip to Mexico. And let's say you fell in love with all the really amazing colors you saw and you took all these great photos. And what you can do is you can take one of these photos, import it into your configurator, and you can create a color map based on this photo, and then you can apply that to your modules and print out modules with that color map on. So now what you have is a phone that's inspired by your personal trip to Mexico. We also have 3D textures that you can put on the modules. These, again, are created in the Ara configurator. You can place it on one module, you can place it on multiple modules. You're free to be creative there. The one rule that we've placed on these 3D textures is that they can only go on the top surface. If we ended up putting them on the sides, that would actually interfere with how the modules lock into the endoskeleton. So now we have our unifying elements of the CMF. So these are things that unify all Ara phones, no matter how crazy people have customized them. This is going to be something that holds that brand together. The two elements of this are the endoskeleton and the module bottom plates. Both of these are made out of aluminum. They have a natural color to them, natural color of the aluminum, and they have a satin finish. So these two things are elements that won't change no matter how people customize their Ara phone. And what it creates is this subtle element you can see here on the Mexico phone. It's a subtle element that ties all the phones together. So here you can see some of the really awesome different designs that we could create. There's also a cat phone in there, which is pretty cool sometimes. So, Project Ara's industrial design. It's created for all 6 billion of us. It's this flexible platform that is for people in all walks of life. We wanted to create this magical modular experience that was easy to use and people fell in love with. And we wanted to create this canvas for personalization, both functional personalization and also aesthetic. Thank you.
All right, awesome. Thanks so much. Okay, so a couple of quick questions. So what's the story with the cat, man? You mentioned it.
Oh,
what's
cat.
up with that cat?
I should have known that one was going to come up. So the cat was inspired by the idea of, putting something personal on your phone. So, we thought this is an awesome image that we found. So let's use that. Let's have some fun with it. So it's about creating something personal, whether it's a cat or your girlfriend or, whatever, and having that on your phone so it's a personalized object.
Awesome. Hashtag cat or girlfriend. That's great. We actually have been trying to reach out to the photographer of the cats, who I think is in the Ukraine or somewhere thereabouts, and we haven't heard back yet. So if anyone knows the photographer who took the cat, we know him, but if you know him personally, have him track us down. Okay. Second question, will there be different materials for the modules like metal or polycarbonate or other kind of cool stuff?
Yes, there could be. So they're not yet being, that's not in the platform right now to be 3D printed, but there could be where people are developing these modules and selling them kind of separately. So yes, I would say it is possible.
Okay, cool. And it looks like we don't have anyone here in the room. They're being very respectful of online folks. We just have one more question here from @Smadger, who asks, would there be anything that you know of to restrict a connector module? Basically something that could connect two endos or more together to create some kind of larger experience. like
to
a dual
connect
screen
two
book.
endos together, not
Yeah,
not
like
two
if you want to
modules,
create
but
a
endos.
dual screen book or something, or a 72-inch
I think
plasma display.
It could be possible. It depends, do they electronically talk to each other, or?
At Smadger, do they answer? No. So I think, it's not an area we've clearly defined in the MDK, right? But there's nothing that would prevent it at the moment. But it's kind of one of those scenarios where we'll have to see. Okay, anybody in the room? Oh, we have somebody. Yeah, you, sir.
Yeah, I had a quick question. What thought have you given to vendor logos and third party? Because I noticed on one of those screens, on one of the squares, it had a embed of a Motorola symbol, and I'm just wondering, to create that uniformity, that individuality, are you going to allow, if eventually there's a Sprint module versus a Verizon, for them to tag that or imprint?
The one, we have done a little bit of thinking on that, and I think in the MDK there's some space on the bottom of the modules where we've allowed for people to have the type of module it is, logo and things like that. We don't have space on the kind of top surface of the module. I think as part of the Ara story of not having a logo on it at all, I think that's a really nice story that we might want to encourage. So we do have space on the bottom currently. Yeah, so I think that's just a relic of old times.
Back in the day, yeah. All right, guys, we have 2 more questions, and then we'll go to the next topic to keep on time. You, sir.
So permanent magnets, it's known for destructing storage devices and stuff. How bad it can be, or is it not harmful at all for this thing?
It's known for...
Magnets are known for destroying hard drives and stuff. Let's save that question for the beginning of our next session, because I think Ara will have who is our EPM expert will be able to take that one.
Okay, sounds good.
You, sir?
Hey, so I wanted to ask about the physicality of the modules. There are some things that are probably too big to put into a module, like a credit card reader, for example.
Yeah.
Have you put thought into some kind of a tray or a sled that the whole device would slide into and then be able to interface through the module connector?
So I think something like a credit card reader, we could be able to just design a module that...
So you might have to do the Z expansion?
Yeah, do some Z expansion. I think we could allow room to do that. I think that's very easy to do without having to design a whole kind of extra part that the phone goes into. But depending on how big your kind of need is, we haven't thought about that yet, but...
Or what about a module that would have a cable coming off of it to interface with another device, like a medical device, for example?
Yeah, so you could almost envision a module to have 2 parts to it, where one part comes off and it's this, part of the medical module, and it could have a cable connecting it. So I think that is more of that's something that's allowed that, we don't talk about in the MDK, but it's more of a module element that is allowable by developers.
Okay, thank you.
Awesome. All right, thanks, Dan.
Yep.
Amazing. Fantastic. Good stuff. All right. A couple of super quick announcements. Apologies for those that are online. For those that are here in person, someone left a watch at registration. So for those 3 of you who don't check time with your smartphone, check registration. Also, Smadger replied, yep. So Smadger, we're in communication. Okay, so next we have Ara Kanayan, and he's going to talk to you about the kind of mechanical design and systems of the project. Now, some of you may notice his name, and it's kind of familiar. So it is indeed true that we ended up naming this project inspired by his name. So Ara, is your mom watching right now? Is she streaming?
I'm not sure.
You're not sure?
Not sure.
She may not be. She sometimes probably gets bored with this kind of stuff. But I wanted to thank Ara's mom for naming the project, because she chose a name that's really universal and short and wonderful. And it started out as a joke, but we kind of fell in love with it. This phone that's designed for 6 billion people, let's name it after a person in the spirit of when you create your phone, it's just for you. Now, I guess there were some other names that Ara's mom had available in case he would have been a girl. This very well could have been Project Tamar. And that's an Armenian girl's name. I think that was probably in the works. So anyway, here is Ara Kanayan to talk about much more serious things. Welcome.
All right, thank you. So we started working on this project. We got a request, which is, please do not make this phone weigh 8 pounds, right? And so we've tried hard to do that, and it does not, in fact. But there's the conventional wisdom, right? That we're trying to break through, which is that modular devices have to be large and bulky, right? So look at your desktop PC; it's very modular. Laptop is less modular, but you can still replace the hard drive and things like that. Tablet, not at all modular, and gets smaller. So it would sort of seem that there's some, it's not a law of physics, but it would seem that there's some law of behavior or something that says that you can't make a small device that's modular, right? But there's another sort of industry trend that really sort of goes in the other direction, and that's that electronic devices have been getting smaller and smaller over time, right? So you look at your mobile radio telephone from the 1960s on the left here, and the progression, from bag phones, flip phones, and finally, in the last decade, we got to this sort of lunatic fringe of these incredibly tiny phones that started to come out. This phone here that's the size of a lipstick tube. And what enables that? Well, of course, familiar to anybody in Silicon Valley, what enables that is Moore's law, right? That as the lithography pitch gets smaller and smaller, that you can fit more and more on an integrated circuit, or you can have a smaller and smaller integrated circuit doing the same function. And so, but this did not happen, right? This is Will Ferrell from Saturday Night Live. I remember watching this on TV, actually, and he's got his little tiny phone that he's manipulating with his hands, and he's going to jet off to Milan or something. And this did not happen, right? And why didn't it happen? Well, it's because there's no Moore's law for human hand size, right? And maybe there's been some nutrition differences in the last 30 years. I don't know. I just made this up. But I'm pretty sure that human hands, are not doubling in size every 18 months, right? And so that gives us all an opportunity here, right? To do something else, to do something exciting with, what technology is giving us. But we got to watch out, because there are things other than integrated circuits that go into a modular phone, right? And so what are the drivers of modularity overhead, right, that we've been looking at, right? So electronics is one, but I just addressed that. Thank goodness for 28 nanometer fabs. Air is one that we were very concerned about in the beginning, and we're not as concerned with anymore. But there was this idea that, if somebody makes a vibrator motor module, but then somebody else wants to make a display module, and all the modules are the same size, my God, there's going to be all this airspace in the modules or something, and that's going to take up a lot of volume. Now, it turns out with the sort of flexible powers of two parceling system, and also the ability to fill extra space in modules with battery if there's a lot of extra space in a particular module, like in the case of the display, where the display is very thin and there's a fixed thickness, that we've overcome that. And actually, I can say that with confidence, because in the Spiral 1 prototype, I can assure you that this thing is jam-packed to the gills and that there's no air space whatsoever in there. So we feel good about that. Housings, of course, there is overhead to having double housings, right? Because there's a module on the top and a module on the bottom. But it's sort of a fixed overhead that scales with everything else in the system. So it's not something that is going to sort of scale out of control. Connectors, though, connectors are an area that we're very concerned about, and where we've sort of applied a lot of advanced technology to try to get the modularity overhead of the connectors down, because there is no Moore's law for connectors. We did a survey of all kinds of different kinds of connectors that we could use to connect the modules to one another. And there are very small connectors, very mechanically small connectors out there, but they're not durable. So if you look at, for example, the printed circuit connector in the middle there is a blade and beam style connector that's used in actually for modularity in phones today, right? There are these little camera modules that attach with a flex circuit to the main board and that kind of thing. And they typically will use connectors like that, and they're very fine pitch and very small and light, but they have rated for 10 insertion cycles, right? And then after that, the metal fatigue sets in, and you can't plug them anymore. So a connector like that is not suitable for this platform, where people are going to be replacing modules at home. There are these little mini RF connectors, that are expensive and also don't have very many cycles, that kind of thing. And so we surveyed the market of available connectors and determined that we needed something else. And let me show you what we're planning to do. So, but let me tell you first what the requirements are. What are the design requirements? So we want to be able to exchange about 5 watts of power. So this could go in either direction between the module and the endo, and be able to dissipate sort of at the upper limit 5 watts of heat. Now that couldn't be from every module at once, but for sort of the extreme of the AP module running a benchmark, it's about 5 watts. We want to be able to have 10 gigabits per second of data transfer between the modules, and that corresponds to 2 lanes of Gear 3 MFI. And then we want to be able to hold the module in with about 30 newtons of force. It's retained in 5 axes by the endoskeleton, and so there's just that 6th direction that we need to resist. And we did some experiments, and that seemed like a reasonable starting point. So here's a picture of the interface block that you've all seen. And in the objective system, we're planning to use these 8 capacitive data pads. These are on the bottom of a printed circuit board, covered with black solder mask on the bottom of the board. They're about 2.8 millimeters square. And what they do is they form a parallel plate capacitor with a corresponding pad on the endoskeleton. I'm going to tell you all about that in a second. For power, though, we didn't want to do wireless power on this project because power is everything in mobile, and even a 90% efficiency, we didn't think was suitable. And so we are using spring pins for the power, but there's only 2 of them, and so they don't take up a lot of space or a lot of cost. So these spring pins are spring-loaded pins, similar to the sort of style used for board testing fixtures and that kind of thing. And it's a one-piece interface. So there's a spring pin on one side, and then on the other side, it's just a printed circuit board, a gold-plated pad that it contacts to. Now, in the prototype system, the capacitive, I'm going to tell you about it in a minute, but it's not quite ready. And so we're using 10 spring pins, 8 for data at LVDS, and 2 more for power in a block. Okay, so I'm going to do a little deep dive into the capacitive data communication and just sort of share with you some of our development results and plans and that kind of thing. So we've been doing some work with test boards, data test boards, and doing pseudo-random bitstream testing and that kind of thing. There's three different main geometries that we've been exploring, and it looks like the result is going to be that we're going to use them in combination with each other, actually, that we'll get the best results that way. So on the left, there's a simple capacitive pad. So it's a circle, and the shape is subject to change. But the idea is just that it's a flat land on the top of the printed circuit board, forms a parallel plate capacitor. Now on the top, you see a CAD model, and on the bottom, there's an X-ray image of the test boards that we've been working with. Then in the middle, there's a spiral inductor. So this is actually not capacitive data communication. It's inductive data communication, right? Near-field communication. It's all near-field communication, really. And we've been experimenting with that. So one inductor forms a PCB transformer with another inductor on the other board. And then the third is this PCB Hallback inductor device. So this is really, you can think about this as 2 spiral inductors next to each other with one in the middle to sort of make a little U-shaped horseshoe magnet. And then that meets another one on the other side. And this is a technique for reducing the crosstalk. And as I said, I think the eventual sort of microstrip structure for coupling that gets specified in here is probably going to be some combination of these geometries. And I'll explain why in a second. So here's a plot showing the insertion loss. One of these pads, this is into 50 ohm load. And the axis here, the horizontal axis is frequency. Plot is on a scale from 0 to 5 gigahertz. And the vertical axis is insertion loss, so 0 dB, meaning all the signal gets through on the top, and then going down in decibels on down. And the blue line is an experimental measurement from the lab, and the red line is a finite element simulation result. And you see that at about 1 gigahertz, after 1 gigahertz, so it's a low pass channel, it's a high pass channel. Below 1 gigahertz, very little of the signal gets through. It's a capacitor. but then above 1 gigahertz, the signal is down by about 10 dB, and then can be recovered. Now we also, though, we want to sort of fill in the low frequency range, and so and also get the gain up. And so we've been looking at these inductors as a complement, and you can get a link over a larger range with an inductor. So there's sort of less mechanical tolerance requirement. This is the same sort of graph here. This is on a smaller frequency range scale, though. It's 0 to 500 megahertz. And you see that at about 100 megahertz, these inductors are up to minus 5 dB insertion loss. But then the high frequency performance is not as good because of their self-inductance, so complementary. Now, another thing that is sort of brought into the receiver design that's really helpful in enabling here is using hysteresis to extend the frequency range. So the idea is you send a signal, and the low frequency, say a square wave data signal, the low frequency parts of the signal are attenuated by the contactless link, but then the receiver has hysteresis, so the edge gets through, and then the level is maintained by the hysteresis until the corresponding falling edge that then pushes it down. So this has allowed us to, in our prototypes, to be able to pass a function generator with a 1 hertz square wave on the input, and to get it out on the other end from the hysteresis amplifier, even though there's capacitive coupling in the middle. So this is a photograph of a test setup here. So on the bottom right, you see the large board there sort of conceptually represents the endoskeleton, and the small board represents a module. At the top right image there, you see the 2 printed circuit boards stacked on top of each other. There's an air gap in between, and we just sort of hold them up against each other with our fingers in the lab. And then on the left there, there's an oscilloscope that's receiving some data. Now this picture that I have right here is a square wave. It's just showing a square wave getting transmitted through. But we've also done pseudo-random bitstream testing on this, and actually it's sort of passed with an eye diagram that's starting to close around about 600 megabits per second. So we're still working on the design of this and extending it up to MPHI speeds, and we've been working with the analog group at Toshiba to help us do that. And you see here is a block diagram of the system that we're designing with them. So on the left there, you see the capacitive, just a word about what the slide title means, capacitive media converter for MPHI. So the MPHI specification allows for a media converter, which is something that takes your MPHI data and converts it to a different physical layer. So you could, in theory, there's an optical media converter defined in the specification, and in theory, you could use smoke signals, or you could use carrier pigeons, or sort of any physical means of transmitting the information, as long as it can work at the rate required, which neither of those would. And then you can come back to MPHI on the other side. And so with it, the block that we've been designing with Toshiba is this capacitive media converter. And so on the left here, you see MPHI comes in, it goes into a transmit equalizer, and what that does is it removes all of the low frequency components from the signal so that they won't just reflect back. Then there's series termination to catch sort of what reflections remain. Transmission line to the microstrip coupling network. Another transmission line on the other side. So one of these transmission lines is in the endo. The other transmission line is in the module. Then a receive equalizer on the other side to improve the intersymbol interference picture. That hysteresis amplifier that we talked about to do DC restoration, and then back to MPHI. So this is the development project that we're doing right now, and we're very excited about its potential to reduce the modularity overhead for modules and sort of put connectors onto Moore's law, instead of being off as they currently are. So excited about this. Another technology that we're using for the connectors are electropermanent magnets. Electropermanent magnets are used in steel mills for moving giant blocks of metal around, and they're also used in machining for work holding. And what it is it's a sort of a cross between a permanent magnet and an electromagnet. And so you give it a short pulse of current, and it turns on. It's a magnet, and it's holding a block of metal to it. Then if you give it a short pulse of current in the opposite direction, it turns off, and now it's inert, and it's not holding with magnetic force. But it doesn't take any power when it's on or when it's off. They only take power to transition between states. And you can see in the photo here, a 1x2 module in the prototype that has electropermanent magnets to hold it in. And as we said, they only have to hold it in one direction, because magnets are, just in general, magnets are sort of strong when you pull them apart from the faces, but they're weak when you peel them off or when you slide them off with shear forces. And so luckily, the industrial design and the dovetail shape allows only one direction to need to be strong. Now, just to show you how these electropermanent magnets are put together in the image here, and by the way, we're sort of open to new designs for these electropermanent magnets in modules, and so this is what we came up with, but we sort of imagine that the developer community will be able to come up with magnets that are better. These magnets here have these 4 pieces of Hyperco 50, so those are the gray blocks there, and these are the magnetic pole pieces of the structure. Now there's 2 different kinds of permanent magnet material in here. There's neodymium iron boron, this red material, and this has a high remnants and a high coercivity, so it means that it's very strong, it applies a lot, you can apply a lot of magnetic force with it, and it's very strongly resistant to demagnetization. So those magnets have a magnetization in a certain direction and it doesn't change. Then the blue magnets are Alnico, which is a older permanent magnet material. They have the same remnants as neodymium iron boron, so they're just as strong, but they're much easier to demagnetize. And so what we do is when you pass a current pulse through one of those coils, it changes the magnetization of the Alnico, but not of the neodymium. And so when the magnet is off, magnetic flux just circulates inside the device, going through the neodymium and then into the Alnico and back, and just forms little loops inside, doesn't get out. But when it's magnetized in the other direction, the flux gets out and goes to Hyperco 50 pieces in the endoskeleton. We're excited about this, and we have some electropermanent magnets with us, and if you come to the developer hardware panel tomorrow, you'll be able to see them. Here's a module subassembly tour. So I just want to show you the mechanical layout of a module and the different pieces that make it up and their function. And a lot of these pieces are sort of multifunctional, do a number of different things. So just the names of the parts. So if you go all the way to the left, that's the module base. Then there's the circuit board, which has the electropermanent magnets, the FPGA, and so forth. There's the safety shield that goes on top of that, which is the sheet metal piece there. And then all the way to the right, there's the shell that provides the outer housing. Now, the module base, of course, provides the function of keeping you from touching the bottom of the module. It needs to be made of metal. I believe the MDK specifies 6061 aluminum. And the reason for that is that it's also providing a thermal function. It's allowing heat to pass from the circuit board into the endoskeleton, and also heat from the endoskeleton to come back into the module, so that heat can uniformly distribute throughout the system. And it's also providing an ESD protection function for the module electronics. On the other side of the board, there's the safety shield. The safety shield is important because, for a couple of reasons. It's keeping electromagnetic interference from leaving or entering the module electronics, right? And the cover does that on the bottom. And then also it's protecting the electronics of the module from being touched by the user or getting ESD hits from the user, because the shell is user removable, and the user can buy a new shell with their aesthetic customization and put it on. And so the safety shield is protecting the module electronics in a number of ways for that reason. Now, the printed circuit board itself, we've been using in our prototype 0.5 millimeter thick 6 or 8 layer printed circuit boards there. And they have, you can see there, the electropermanent magnets on there. The components there's the FPGA, which has the Unipro bridge. And then there's power components for driving the EPM and for providing the power supplies for all the module components and for the particular module function. There is an allowance for components on both sides of the board. So of course you can partition space however you want inside the module. There's no requirement that you do anything in particular in there with regard to number. You can have multiple printed circuit boards if you can figure out how to fit them, of course, and that kind of thing. It's your module. In the reference design that we have 01005 decoupling capacitors on the bottom of the printed circuit board, which under the FPGA, and then all the rest of the components are on top. Okay, now the front modules attach in a slightly different way than the back modules, actually a very different way, because there's no spine for electropermanent magnets to attach to for the front modules. And so we're using a ball spring plunger, and you can see a sort of schematic view of that in the picture, and the little ball spring sticks out of the front module and then goes into a sort of mating spherical depression in the endoskeleton so that the module can snap in place. And in the objective system, the plan is to have an electropermanent magnet inside the module that latches that ball spring plunger so that those modules also lock securely under software control in the front. In the prototype system, we haven't implemented that yet, and so it's just a ball spring plunger. And as we continue the design of this, we'll push it out in future revisions of the MDK. Now I talk about the MDK for a minute and the design artifacts that are in there. So we've put a lot of module templates or we've put a module template and a lot of example modules in the MDK. And in particular, there's a template. So there's a printed circuit board that has sort of all of the infrastructure. So Paul was saying earlier, 60% overhead in the prototype. That'll be significantly lower in the objective. But without the ASICs and with the spring pins, 60% of the module is taken up by other components, and you don't have to design any of that. It's all on the template, and you can just put the module function into the remaining space. And then also all the covers. So what are the artifacts in the MDK? So we've provided basically a whole open source modular phone. There's step models of all of the parts that you need to build a module, including the base and the cover and the printed circuit board outlines. There's complete machine shop drawings, so you could send the drawings to a shop and they would already have all their tolerance callouts and materials and stuff like that and could build it. There's a bill of materials for the EPM and the ball spring plunger assembly and some drawings of how those go together, so you should be able to make your own EPMs from that. And we're also going to try to make them available for sale to you. There's electrical, so there's full schematics of I think almost all the modules of the prototype phone. There's layouts. There's layout rules for the if you do the schematic and then send it to a layout house. There's high-speed routing rules and stuff, documents, bill of materials, PCB layout guidelines, as I just said, and then all of the material for the module. So there's a media bar, which has a speaker connected to a codec. There's the thermal imager, which you've heard a lot about. Display module with a 1280 by 720 Samsung AMOLED display. There's a 2x2 battery module with a lithium polymer battery and a charger, a USB charger module, LED array, all there. So enjoy. Thank you.
All right. Thank you, Ara. That's amazing. We got a couple of questions coming in. And first of all, my apologies. It's been so long since I've done IRC. The actual channel is Ara DevCon IRC. Ara DevCon IRC. There is another conversation now happening at Ara Dev IRC, but we're not quite as in tune with that one right now. Okay. So from Paco Bell, we have a question. I heard the EPM takes 10 amps to transition. That sounds ... pretty crazy. So can you talk about that?
That's true, and it is. Let me talk about that. So the EPM drive pulse is 28 volts, 10 amps for 20 microseconds. And that, by the way, is not a requirement of the MDK. That's the way that we've built our particular EPMs in the prototype. But it's actually fairly easy to generate that because that is the energy that is stored in 4 size 0805 decoupling capacitors. And so we have four 22 microfarad nominal decoupling capacitors on the board, and we have a MOSFET circuit that just dumps those capacitors into the magnet coil. So while it is a lot of current, it's for a very short time, and so it's only a very small amount of power. It's about of energy. It's about 2 millijoules.
Have you ever had 2 millijoules go through your body while you've been prototyping?
I was shocked with 10,000 volts once.
So
and,
it seems like that's
for the
okay.
Rest of the day. Yeah.
Awesome. Okay, so Stefan Weiberg asks, what does a user have to do to trigger this impulse? Can a user exchange them, the modules, while the phone is off and doesn't have energy? And follow-up is, what prevents the user from operating without the safety shield? So 2 questions there.
All right, I'll take those one at a time. So can the user trigger the impulse? So yes. So the idea is that there'll be an app, and you can engage and disengage the EPMs on your modules from the app. And we're still working out. The UI team is still working out exactly how that would work. But there's some user interface element on the phone that allows you to do that. I think that answered the question.
The other question is, what about the safety shield?
Yeah, and then what prevents you from removing the? So the safety shield is put on by the module developer, and so I suppose if the user wanted to desolder the safety shields, that it's a free country and that's their right. We don't recommend it.
Okay.
I hope that was answering the question.
Yeah, spoken by a true hacker.
Okay.
That's awesome. Okay, cool. Any questions from the room? We got a question over here? Yeah.
Hi. I was hoping you could speak to the different kinds of, or what kind of processors or sensors are available in the prototype, and if there would be different kinds in different form factors.
Yeah, sure. So the first, I'll answer your second question first. So there's, we chose a particular processor for the prototype that we built, but the purpose of the prototype is just to prove out the platform, and we're hoping that everybody in this room and everybody online, produces 50 different AP modules with all every processor that exists. And the same for every other peripheral. In the prototype, we were using the OMAP 4460 from TI, which we love actually, and we chose it because it was the only POP mobile phone processor that had a publicly available datasheet, and we wanted this to be an open, accessible platform, and so we wanted people to be able to hack on it from the publicly accessible datasheet. And some of the other components, or?
Yeah, sensors.
Sensors, yeah. So on the prototype, there's a thermal imager sensor. It's a Melexis 16x4 thermal imager. It's pretty cool. And then there's a pulse oximeter that uses, I think it's a TI AFE 4400, I think, pulse oximeter with companion LEDs and photodiodes. And I think those are all the sensors that are in the prototype so far.
Thank you.
Thank you.
All right, let's hear it for Ara.
All right, thank you.
Project Ara. We have awesome meetings when Ara is involved. We don't know if we're talking about the person or the project. It's amazing. Okay, now I'm going to introduce to you the other half of our amazing technical kind of leadership team. I want to introduce Seth Newberg. And Seth and Ara, they're both part of a company called NK Labs. And if you look on the program and see their last names, you might kind of realize what's going on there. They're kind of like the Ben Affleck and Matt Damon of engineering. They both kind of grew up like in Boston. I don't know if it was in the Back Bay or what, but they like have been doing crazy engineering stuff since they were like kids. And they have so many stories. In fact, there's one I won't share, but later on tonight, if you get them kind of in a corner, they may share with you some of the crazy things that they've been involved in. I'll just share one, that they were in this competition for a science project, and you had to move an egg from a starting point to a wall as fast as possible, but not breaking the egg, right? So they kind of miscalculated their falling weight that would also break, and they smashed into the wall, but then they looked at the egg, and the membrane was still intact. And the judges were about to cancel their thing, and they're like, no, 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 look, it hasn't really broken according to your rules. And so they actually ended up doing very well in that competition. So here's Seth, and he's going to talk about the power systems.
Thanks. I'm going to tell you about, talk about the power systems in the Project Ara platform today. So some of the motivations that we had in designing the power architecture for the platform is that we want to allow multiple batteries and multiple chargers. Any source of power that module developers and end users would be interested in using should be available. Also, the end user they get to decide the amount of battery in their phone. So if you want to carry a stack of batteries with you, that's perfectly fine. You can hot swap the batteries in and out of the phone, even during a call. I think that that's very advantageous for a new phone platform. Also, any module can have a battery. For example, a display module with some extra space, the module developer can choose to put some extra battery in there to allow more power for the phone. Multiple chargers are allowed. You could use a DC power source, like through your USB plug, but also inductive or solar power chargers could be included right into a charging module. You wouldn't need to have an external device hanging off of your phone or a jacket around your phone to allow these different forms of power transfer to the phone. Also, our architecture allows many different battery chemistries. Our initial prototype uses lithium polymer batteries, but maybe some users would prefer a battery that can take very fast recharge rates, like a lithium iron phosphate battery. So developers would be able to provide that for the phone. The endo is the backplane of the phone, and in the endo is responsible for power distribution and data distribution. So there's a shared variable voltage power bus in the endoskeleton, and all of the modules are attached to that power bus in parallel. The endo includes a small battery and a supervisory controller that provides power management of the system. The small battery also supports hot swap of the last battery, removable battery in your phone. You still get 5-10 minutes of battery life, so you can remove your last battery and install it. The supervisory controller monitors and manages power distribution to the various modules. And the supervisor also manages the battery charge and discharge profiles that could be user selectable, whether you preferentially discharge one battery or all of your batteries together, and then the order that they get recharged. The endo has the connector blocks in each of the module bays. Each of those connectors has 2 pins for power, one for positive voltage and one for ground. And the current is bidirectional. It can flow into or out of the module through that one connector. The endoskeleton provides power to the modules by default. So when a module gets first inserted, it receives some power to bring up the electronics and establish a communications link with the rest of the system. And the modules can be categorized into 3 different classes with respect to power. There are power consumers that always draw power from the system. There's charger modules, which are able to deliver external power supplies to to the shared power bus. And then there's power storage modules, which are batteries that normally are supplying power to the system, but can also draw power from the system in order to recharge the battery. The variable voltage power bus is required to be between 3 volts and 5.5 volts. So all modules must accept this full bus voltage range. And modules are responsible for their own power conversion, onboard voltage regulation. So if a circuit needs 1.8 volts, each module has its own power regulation to step down from the variable input voltage to the 1.8 volts. Power consumer modules have the internal voltage regulation. They receive power when they're connected to the endoskeleton, and simply enough, when they're disconnected from the endoskeleton, they lose power. The charger modules, they are required to apply power to the shared bus within that defined range, 3 volts to 5.5 volts. If you have a photovoltaic charger that's delivering voltage at a lower voltage, it needs to step it up to be within the allowed voltage range. For the power storage modules, batteries provide power on their output pins, on their voltage pins by default. And they're also required to supply the voltage in the range of 3 to 5.5 volts. And each module has its own onboard self-diagnostics, including on battery modules. The battery module would report its own battery state of charge. So a great benefit of the Ara architecture is the ability to have multiple batteries or multiple power sources supplying your system. And the way that works, we have our batteries connected in parallel on the power bus, and each delivers delivers power to the system through an ideal diode circuit. So in the example we show here, we have the 2 battery modules installed, and the bus voltage floats to the voltage of whatever the highest voltage battery is that's applying power to the system. So in this case, battery number 1 is at 4.2 volts. So the endo power bus also rises to 4.2 volts, and the power consumer modules draw power at that voltage. When you have one battery at a higher voltage, it bears the full load of the system until its voltage drops to be equal to the next highest voltage module, power providing module, at which point the load is shared evenly across the 2 modules. And as the voltage continues to fall, it equalizes with more and more batteries in the system and evenly shares the load among them. Now, using this diode logic to combine the power supplies, if we're using silicon diodes, this would be very power inefficient. You'd have voltage drops across the diode, and it really wouldn't be suitable for power distribution. So we're using ideal diode circuits, which are active circuits that use FETs and sense circuitry to create the behavior of an ideal diode circuit. So 0 forward voltage loss and very high resistance to reverse current. For recharging the batteries, so batteries are delivering power to the system by default, and then A charge module, it provides power to the bus from an external source. Now that works by when a charger module is installed and connected to an external power supply, it will signal with a UniPro data message to the supervisory controller in the endoskeleton, and to indicate that it is connected to the system and ready to provide charging current to the batteries so they can recharge. The supervisory controller through the data network would then signal to a battery module that it's now okay for it to switch from the power delivery state and switch over to draw power from the bus and recharge the battery internal to the module. And battery modules have their own charge control circuitry. A battery module is responsible for its own charge regulation. It's drawing the unregulated voltage off the bus. So this allows us to avoid double conversion losses from the step-up, step-down voltage converters. While they are fairly efficient, if the shared voltage, if the shared bus were a fixed 5 volts, for example, then some modules would have to step up their voltage to hit the regulated voltage, and then other modules would have to step down the voltage, and that leads to additional power losses that are avoided by having the variable shared bus. The power management system is based on our supervisory controller, the power manager in the endoskeleton, and each module slot that's receiving power, each port has protection circuitry built into the endoskeleton. That circuitry involves a resettable fuse, overvoltage protection, a bidirectional current monitoring, and a cutoff switch. That's so modules, they self-report their expected power usage, and then the power manager monitors their actual power usage and is able to cut off power to a module if there's any unexpected behaviors, and the module needs to be disconnected or reset. The battery that's included in the endoskeleton also has the same protection circuit with ideal diode. As I mentioned, this battery is always supplying power to the shared bus and allows the hot swapping of your last module. In summary, the architecture allows bidirectional power flow to all modules, and any module may provide charge from an external power source or provide battery storage for the system. We have the 3 module power classes, power consumers, chargers, and power storage. And there's a variable voltage shared power bus in the endoskeleton to distribute power to all the modules. Thank you.
All right. So now you see this amazing, duo from NK Labs. You guys are awesome. I don't know if we've been getting a lot of questions online. Let me double check. So if you guys have any questions here, we got one over here. Why don't you go ahead and start?
Hi, Greg Goldman, Broadcom. I have more system question related to power consumption with your module architecture. My question is, right now you're going to add a lot of new blocks to keep communication between modules, like Uniport controller, and all those blocks. My question is, what is your estimation from power consumption just to keep communication between modules? I can simplify my question. I believe actually your prototype is practically like Panda board module with some modifications. So let's assume you have Panda board, and let's assume you have Panda with all like uniports and uniport controllers. Again, my question is, what is your estimation? How much power you will need just to keep power for all those mini ports, uniports, and uniport components?
Thanks. So your question is, with our modular architecture, we have all of these extra data communications blocks, and what is the power overhead for that?
That's exactly right.
And part of our selection of Unipro and the MFI physical layer in particular is power advantages. So one aspect of this communications protocol is a strategy of very high bursts of data communication, and then switch to a very low power hibernate mode. So fast transaction, and then spend a lot of time in a standby state. And Unipro, being designed for mobile interfaces, has the speed gearing, the hibernate modes, and the burst modes specifically to address power consumption. And so the dynamic power requirements for data communication are comparable to other data interfaces used in mobile phones. We expect about 20 milliwatts per data link for the high-speed Unipro. So that is, I think it's about a 10 or 15% power overhead for the additional data interface when we are bridging from one protocol to Unipro and then converting back. When we have Unipro communicating natively between your processor and the network and the end devices, then you aren't doubling that power overhead anymore. So it's actually fairly efficient.
Cool. Thank you.
Thanks.
Thanks.
All right, we have a question over here.
Yes, I was wondering if you had any thoughts on how we could connect solar cells on the back cell into the power bus, maybe a standardized connector location in the circuit. So you could just flip the whole thing over and charge your batteries. Solar.
So you're asking, in terms of incorporating photovoltaics into the platform, how a module, how much real estate on the back could be dedicated for the for the photovoltaics?
You have the external shells on the modules on the back, so you'd have photovoltaics mounted on those back shells, and those could charge the phone if there's a way to connect them to the power bus charge controller.
I see. Well, I think that, so you're addressing if we had module covers that were, the photovoltaic is at the level of the shells, and maybe every single module on the phone would be producing solar power. And in the specification, this is something that we would definitely like to explore. There's great opportunities in how to get solar power or any type of power transfer onto the device. And in our specification of the modules, any module can be a charge type module. So if you have a cover for your processor module that has the photovoltaics, a processor module can also be a charge module. That's definitely the power functionality is something that can be bundled into any module in the system.
Right, if we have a standard jack location, so you always know what it's going to be for any module cover. Say we're in that corner where the electropermanent magnets are.
I think that's a good suggestion. I think we should consider that. Thank you.
Thanks.
That's cool. I mean, and also we'll talk about this tomorrow, but some of our Ara scouts who have been thinking about how they would use a modular phone, solar panels come up quite a bit actually. And so I think that would be, if someone has expertise in that area, we'd love to have you push the boundaries there. All right, let me go to the internet real quick, and then I'll go to you guys. Or I'm going to go to the line, as I'll say. I watched the internship last night. So let's go to the line. And from IRC, Yari2 asks, will inductive or wireless charging be possible, given the kind of size requirements? You have a maximum 2x2 module. You also have EPM magnets. Anything preventing you from doing something like the Qi inductor pads that help with wireless charging?
This platform is very adaptable to exactly that, having inductive charge modules that are integrated into the phone, so that 2x2, you have the 2x2 module area, or maybe even incorporating a loop into a display module, and that could be an excellent way to embed an inductive Qi type inductive power transfer into your phone and not have an external jacket or something hanging off of the phone to bring the wireless power.
Awesome. All right,
so
we'll come back.
Much cleaner interface.
So the display module, you have more space, you have more size.
If you need more area, or
yeah.
a 2x2 module, you could use the area there.
Cool. All right, this gentleman here.
Hi. So actually, that brought to mind another question I had about the industrial.
Just one, man.
Yeah, just one. But I could make it a two-part question.
Okay.
Well, so since there's no logo, the enforcement of the industrial design seems to be a little challenging because, how can I, for instance, if I want to make a wireless charging module in my garage, I can do that. I can buy a kit from Amazon where I can do a 3D printing kit, and I can do my own shell if I wanted to. So, how if the ID is not, it's not clear to me at least how that's being enforced, and also the signal integrity analysis that has been done for this. We're talking about this nice connector that has only one ground connection for the DC return current and any AC returns that may be needed, and that's going through some backbone that's covered by aluminum. So is that wires? Hopefully not wires. Maybe there's some kind of impedance-controlled mechanism that is actually making the interconnection there. So that was my two-part question.
Why don't you take the second part? I'll take the first part after you're done.
Okay, thanks. So the second part of the question is asking about signal integrity and like power line noise immunity issues, and what is the interconnect in the backplane of the endoskeleton. For the noise immunity or introduction of electrical noise into the system, that's something that you can look in the MDK in the environmental section, specifying a lot of these electromagnetic interference issues, and for the the distribution of power, how the wiring is internal to the endoskeleton. That's still under development, but it is we are taking a careful design process in looking at the impedances and power loads of the distribution wiring. Yes.
And on the first part of your not really two-part question, you're just two questions bundled together, is so 3D printed exterior kind of material and housings are really exciting, and we're really kind of hopeful that these will provide a way for us to on-demand completely aesthetically customize these devices, and in the future add in gradually functional components. But they're by no means required, right? You may have a company that, like, I don't know, where the material is really important, where people send in a worry stone and you mill out something, and that they're actually it's really important that they have their own material. Or if you have an inductive charging unit that people buy it, and you educate them and they understand that that has its own bamboo cover or plastic or something else. So you're not forced to kind of go to the 3D printing route.
Sorry, just for clarification, I was not too concerned about the material necessarily, but rather the enforcement of not allowing me to take more than one module size worth of space. So if I wanted to make a 4x2, for example,
sure,
right? How is that going to be enforced?
Sure, I see. I think, at the end of the day, there's situations like that. Like, no one forces you to put 4 tires on your car. But if you want your car to drive, you have to put on 4 tires, right? So I think depending on how we educate people about those scenarios that might take up 2 or 3 modules, I think it'll be up to them to really take the lead in making sure those things happen.
Thank you.
Okay, back to IRC. Louise920 asks, do the modules have a stop discharge, forcing the modules to store enough energy to still activate the EPM circuit on a dead system reassembly? It's a little more of an Ara question, but Seth, you might want to take this one. So basically, is there like an emergency reserve that allows you to unlock these guys if your battery's low?
The first emergency reserve is in that in the battery that's embedded in the endoskeleton. Although if you've really depleted every single battery connected to your system, and if they are in the locked state, I think that a good feature that that we can implement in the endo is unlocking your battery modules when it reaches end of power and is powering down. It might be a good idea to unlock those modules so you could remove the battery and insert a freshly charged one, or you could plug in your power charge cable and reboot your phone the way you would with most phones today.
Not only do I think we should do that feature, I think we should have a remote control function that reverses the power, so you can say, hey, check out my phone, and then have all the modules go in the opposite direction. Can you add that in there too?
The module ejection.
Module ejection. That'd be awesome.
We'll have to reverse the polarity, but
okay. Let's come back to the room. You probably have a reasonable question.
Yeah, well, hopefully. So I think you said earlier that each of these modules can consume like 5 watts, right? In theory. So is there anything that's going to prevent you from populating, most of the phone with high wattage, consumers that grossly exceed the capability of the battery you put in there? Is that going to be prevented at phone configuration time, or is there going to be something in the supervisor processor that's going to handle that?
Definitely at phone configuration time, which includes an app for reconfiguring your phone at home with your library of modules that you have. Definitely power consumption and power capacity of your batteries are taken into account, and it will simulate and present to you expected power life given a certain configuration. If you're exceeding the thermal dissipation ability of the phone, maybe recommend these 2 high power modules shouldn't be placed right next to each other. Maybe you should spread them apart on different ends of the phone so you don't get local hot spots.
Okay, so it's going to take into consideration both thermal and current
power consumption and thermal dissipation capabilities, yes.
Thanks.
Cool. And actually similarly from Twitter, JPN_Kevin_T says, who decides the charge algorithm for a battery module? So I think it's a similar kind of question. How is this all federated? Is it happening on the system level, at the module level? What takes priority? So you've probably already answered that.
The charge-discharge profiles, it's still under development, but this is something that definitely can and should be end-user selectable. So probably there would be a default set of power management schemes programmed into the supervisory controller, but accessible through an app in Android that would allow you to choose different power profiles, or maybe even design your own custom power profiles. And I can definitely see use cases where in some circumstances, a user may prefer to deplete all batteries, drain them evenly, and maximize life, or maybe preferentially discharge their primary battery or secondary battery first, and keep the primary battery at full charge in reserve.
Okay, awesome. And last question from Ram. So this may either be a typo or a term that I just have no idea what it is. Will there be a way to expose hardware covers from the modules to the Android apps? This could be useful for debugging or performance tuning without needing I2C or UARTs. Do you understand? Counters? Sorry,
Hardware
Ram.
counters.
Cutouts? Hardware cutouts? All right, we'll get back to you. Ooh, there's some real-time Google Docs editing here. And it just went back to the bad misspelling. Okay, we'll get back to you, Ram. All right, awesome. Seth, thanks so much.
Thanks,
we appreciate
Daniel.
it.
Thanks, everybody.
Good stuff. All right. Okay, so the next speaker actually has kind of the longest chunk of time for this afternoon's MDK detail. But he's going to talk about a couple of things. And I just want to do a quick intro. So besides having the most cool and fun name to pronounce on the team, Jürgen Urban, Jürgen, who currently lives in Germany and works for Toshiba, and is going to talk about one of the most kind of really interesting, innovative parts of this whole network stack. He has an interesting story. So how many of you guys saw the Phone Blocks video before you saw the Project Ara video? Raise your hand. So most of you guys, right? And so Jürgen's son also saw it. Now, I don't know what time it is in Germany, but he's either watching this now or he might watch the replay later. And I believe his name is Jonas. And he's 16 years old. And he went to his dad. And he's like, Dad, you're an engineer? Look at this Phone Blocks thing. This guy, Dave Hackens, has a great idea. I don't know if he knows how to engineer it. Can you make it? And Jürgen's like, oh, no. There's no way. You should just read this Reddit thread and find out why. And his son's like, come on, Dad, you can figure it out. Like, anything's possible. And he's like, no. And then 5 weeks later or something, I forget, a very short time later, these crazy guys from Motorola and now Google came to Jürgen and said, hey, we want to use Unipro in this thing called Project Ara. And he's like, oh my God, it's kind of like Phone Blocks. And then as he looked at it, he's like, we can totally do this. So the moral of the story is listen to your teenagers, because sometimes they know what they're talking about. Jürgen, welcome.
Yeah, thank you, and hello. Yeah, I'm going to talk about Unipro today, and I've split my presentation into two parts. One part will be held as an official representative of the MIPI Alliance, and the second part will be held as a representative of Toshiba and as part of the project team, of the Project Ara team. The reason why that split is there because we have invented in the Google project a couple of things that are not yet specified in the MIPI Unipro 1.6 specification, and that are not yet specified in the MFI 3.0 MFI spec. And I want to have a clear separation for what is going to be the future and what is going to be available today. So here the legal disclaimer. I heard from the MIPI representatives from the councils that this is probably the most important slide of the entire presentation. So I will leave it 10 seconds on the screen. I would welcome you and encourage you really to read through that during your sleepless nights. If you suffer from insomnia, please go ahead, do that. So this is my agenda. So who is MIPI Alliance? Please raise your hand. Who has never come across MIPI? So many, great. So I would say it's about 20–30%. Well, I guess, you know, I would argue if you put out your phone and put it on the table, you will see some materialization of some MIPI specs. So probably in every modern phone today, there is a MIPI spec in that implemented. Sorry. So I will talk about Uniport, the history, motivation, objectives. Why did we start in all this? What is Uniport and how to use Uniport? That may be the most important thing for you. I will cover the application interface and the control interface and go a little bit through the Unipro states. And of course, last but not least, what is the MFI and what makes the MFI unique? Who is MIPI Alliance? MIPI Alliance is a gathering of member companies, 250 or more than 250 member companies worldwide now, and has been founded 10 years ago and has been growing ever since. And what we do is actually we drive mobile and mobile influence technologies forward and bring that into specification. It was founded 10 years ago because there was seen a need for standardization in mobile and mobile influenced devices. And basically, in the meantime, we cover really all the ranges in Unipro. So we in the mobile phone area. So we have multimedia specifications. We have chip-to-chip control and debug and trace. So this is an overview on what we try to cover. You see on the left-hand side there is multimedia coverage, there's camera, there's this so-called CSI protocol, display, DSI protocol is probably widely known. There's also storage. UFS is actually a JEDEC standard, but we provide a transport layer, which is a Uniport M layer, consisting of Unipro and MFI. Audio and voice, there's SlimBus, DIG-RF, also based on MFI. And there's interprocessor communication. There's a large variety of different standards, and Uniport M is one of them. We have liaisons with USB consortium and with the PCI SIG delivering MFI technology to them. And you can see there's also these red bubbles down the line. So many of these protocols use already MFI, and that's a good start for a mobile phone, which is supposed to be modular, probably. So here's a system diagram, how today's mobile phones are probably partitioned. You see already some sort of modularity indicated in this block diagram, even though it's not exposed to the user. But there's a lot of different interfaces available today. So it's E-Track, DIG-RF, and how they're called. I mean, it's a wide zoo of animals there. What is important here is that the red part can be already implemented today using Unipro and MFI. So we have to the mass storage, NAND flash, UFS interface. We have probably to the cameras, CSI 3. It's not really visible here. It's not really red because there's also another standard, CSI 2. But it's possible to connect cameras also via CSI 3 MFI. And there is, of course, inter-chip communication from the application processor to companion chips or to ISPs or whatsoever. Motivation, Unipro, a little bit of history. Actually, there's a long history of Unipro already. So we started probably in 2006, 2007. And actually, the idea was at that time that mobile phones will ever grow in complexity. And it was so difficult to change processors from, well, people wanted to have modular systems because there was a different delivery speed for processors, for peripheral, and they wanted to detach actually the submodules from each other and have a protocol communicating to these submodules. And basically, it was an attempt to master the ever-growing system complexity in a mobile phone by just subdividing, divide and conquer those modules. And there's a couple of phases to modularity inside a mobile phone. Yeah? So you can also talk about modularity on a chip, but the idea of Unipro was an inter-chip connection protocol. So one aspect of having such a protocol would be to be enabled to use best-in-class modules and to separate actually the interface from the functionality. People wanted to compete on functionality and not on interfaces. The interface should be there as a given and standardized. So that was actually the mission we had in these days. And the design objectives of Unipro were really that we are strictly layered. This is, I think, very, I mean, there are a couple of other layered protocols around. But UniPro is really very strictly layered. There is no fancy frilly feature for a certain dedicated application in there. It was from the beginning sort of a multi-application protocol where no specific application is ever prioritized or whatsoever. Yeah. It should be a reliable transport mechanism, despite the fact that we are running at high speeds. So we implemented retransmission in a layer 2 stack. Very similar to the internet. It's a sliding windows mechanism. The protocol should be efficient. I mean, if you look at internet protocol, maybe there's quite a lot of overhead because the traffic channels are not secure. When you talk about in-phone communication, the traffic channels have bit error rates of 10 to the power of -10 to 10 to the power of -12 or 13. Barely measurable error. So that allows us to make the protocol very efficient compared to other protocols that go over external cables. So the protocol efficiency in UniPro is about 3% overhead per fragment, which is quite good. And we thought about an extremely scalable protocol. So there is no single word in the specification about implementation. You can implement UniPro as a full-blown hardware stack running at 4 lanes high-speed gears 3 on 20 gigabits per second or even more. You can also run PWM gears, low-speed gears at 3 megabits per second on a single lane, probably using only the serializer and the hardware implementation, and go for the rest of it in a software implementation. So there is a whole variety of different implementations. And if people talk about power consumption, like we have seen, they always think about the full-blown system, but we should not forget that there is modules that use lightweight implementations of the protocol with a very competitive power figure. So what is UniPort M? UniPort M is actually UniPro over MPHY. In the early days, we had also UniPro over DPHY. We abolished that because of the superior qualities of MPHY for that protocol purposes. So UniPort M is also referred to as UniPort, and I use the term UniPort throughout the specification, throughout the presentation here. So UniPro is now in revision 1.6. That's pretty mature. When we started, we had a whole lot of problems to solve. They are solved now. MPHY is in revision 3.0. And as I pointed out, it's used actually for JEDEC, for UFS mass storage, flash storage devices by MIPI in interconnects. The infrastructure support is there. There are plenty of IP vendors you can contact. There are, if you want to integrate your own, if you want to design your own stack, there's plenty of verification IP or test equipment, protocol analyzers. It's all out there. And I think there is a list providing IP vendors. So you can always refer to that. So the UniPro working group inside MIPI, we are doing conformity specifications as well as the main specifications. We organize interoperability events also for adopters, and we maintain FAQ lists and email question lists and do everything to promote the standard. Yeah, so UniPro key features. We wanted to have a low footprint on power and area. That depends, of course, on the implementation a bit, but there are some aspects of the spec, like a low protocol overhead and really no legacy burden from non-mobile applications that allow us to go a little bit closer to that design target. We wanted to have truly bidirectional links. So on the file layer, there's a truly bidirectional link. On the application layer, most of the links will have bidirectionality. It's not a must that on the application layer you run bidirectional, but this is what we will see probably in most applications. So one of the exciting features for this Google Ara project is probably that UniPro has multi-master capabilities. So what UniPro provides is a complete application agnostic point-to-point communication. And we do not have later on topology restrictions. We are not host-centric, so we can plug in 2 masters into the system. We can plug in 3 masters into the system. And we can do point-to-point communication between 2 masters or between 2 slaves that have some certain capability of communicating with the UniPro stack. It's easy to use. It's probably not easy to implement, but it's easy to use. It's a sort of automated stack which does automatic link detection for you, which deals with all the nitty-gritties of layer 1.5 to layer 4, and even the layer 1 is correctly recognized, and I will talk about that later. But it's really easy to use from an application point of view. You just see some sort of FIFO structure. And last but not least, we have guaranteed and in-order delivery of packets. And this inside a phone, this error mechanism of repeated transmission is so good that we don't need any other error protection, for instance, in CSI 3. We just run the CSI 3 as a payload through the network. So as I pointed out, one major aspect of Uniport is really scalability. We have scalability on all levels. Most of the features in the spec are optional. Again, if you talk about power consumption, you should not think always of a full-blown system. We have a lot of options that can be removed from the spec. Not from the spec, but from your implementation. Yeah. There's a lot of fancy weightings between area versus performance or functionality. And of course, the MFI is highly scalable. You can choose the number of lanes, you can choose the speed gears, you can choose the modes, the transmission modes, high-speed gear, low power transmission. And actually, you can choose also the number of virtual channels in your protocol stack. So we have different traffic class supports. You can, for instance, opt to have only 1 traffic class in your system or 2 traffic classes. So a lot of scalable elements in the protocol stack. So how does that look like? Actually, UniPro 1.6 is a point-to-point link where UniPro actually is a cable channel for a bundle of virtual cables. Yeah. If you look at a telephone like Ara is, I mean, what does not exist in Ara is space. The phone does not have a concept of abundant space availability for you. So what you do if you have to channel, let's say, a modern application processor has probably 200 I/O. You cannot really feed 200 I/Os into every module. So what you do is you virtualize your cables. And this is what UniPro does for you. And this is the only thing that UniPro does for you. It does not try to interpret your data. There's basically the idea is to have switched packet communication from one side to the other, and you have a number of virtual channels. The entry point to the virtual channels is the so-called C port, and these virtual channels are time multiplexed, sent over the physical channel, and are output to the other side. And of course, you can do remapping. The virtual channel 0 on the left-hand side doesn't need to end up at the virtual channel 0 on the other side. So how does it look like? This is a layer stack overview. Here you can see there's layer 1, which is in our case the MFI. I've drawn here 4 TX and 4 RX. We have on the top side, we have the application layer, which consists of TX, RX data, and there's a flow control interface. Of course, the status interface to the layer 4. And on the left-hand side, there's the so-called device management entity. The device management entity controls actually the entire UniPro stack. So how does that work? So we have a medium, and I like the idea actually. I mean, we have PCB routing, we have plugs and connectors and optical. Actually, MIPI on the MFI, they do not specify, for instance, the galvanic channel properties. What they do is, sorry, correct me. They do not specify PCB routing or plugs or whatsoever. Yeah? What they do is they specify the channel properties. So as long as you are within the channel properties, you are MIPI compliant. And they have also an optical media converter. And the nice thing about that is that MFi uses only in-band mechanisms to program that inline media converter. And I love the idea from Ara, so we should send pigeons carrying electrons from one side to the others. So that would be a viable media converter. Of course, nobody uses that, but I will make that suggestion to the working group. They will think about that. So then there's the PHY. There is serialization in the PHY, of course, piezo, SIPO, all the stuff you know. Symbol encoding, and we use 8-bit, 10-bit symbol encoding. That gives us a little bit of overhead, but has nonetheless quite nice properties of DC-free transmission. There is intra-lane bit assignment. Bit alignment, sorry, that means actually that there is marker 0 control that adjusts the shift registers to the symbol boundaries. Electrical conversion, of course, in the PHY, and there is bit clock generation and bit clock recovery. The MPHY has the nice capability of transporting the clock within the data stream. That means later on for the Ara project, we do not need to transport a system clock through the system, because each module can generate its own clock, and I think the project will make use of that. Yeah, symbol encoding I already explained. It's okay. Inline link reset. That's also a nice feature of the MPHY. Actually, it is possible to send a reset command from the local side to the peer side, and the entire link is completely synchronized reset between MTX and MRX. That's very nice. We use that extensively in the protocol. So layer 1.5. When you plug in the module, the first thing you need to do is you need to check out what kind of, or when you plug in a connection actually, what kind of peer device is connected. And this does the layer 1.5 for you. It checks out how many lanes are connected, what is the peer capability of sending data. Is it only a high speed, is it only a low power module, or is it a high speed module? This detection runs completely automatically, invisible to the user. So no matter how you do the routing in the PCB, in the end, you know, there's not so many restrictions for the routing. You can have skew between the lines. The only thing you need to make sure here is that the skew, the intra-lane skew between P and N channel, it's a differential channel, of course, is balanced, but skew between the lines is possible. You can swap the skew, the lines. All that is automatically detected for you. So we have in the layer 1.5, you have a so-called PACP protocol, and this PACP protocol is a PA layer configuration protocol that allows low-level communication protocols to be sent from one DME to the other on the peer side. So that allows a complete remote control of your peer from one side of the link. That is very practical for us. I will explain that in the next session why we do that. So layer 2, data framing. Of course, you need to put your data frames together. Error protection is the reset mechanism. We have layer 2 flow control. So layer 2 sends out data only when the peer side is ready to receive data. This avoids actually data loss. There's data rate adaptation in the data link layer. That means actually that all kind of data rates that are below layer 2 may be different from the data rates on top of layer 2. And there's a traffic class prioritization, which is quite useful in UniPro, because we preempt actually traffic class 0. We have 2 traffic classes which are essentially the same from a conceptual point of view, but traffic class 1 is always of higher priority than traffic class 0. And it's very strictly implemented throughout the entire stack that traffic class 1 always precedes processing in traffic class 0. That means if there is a data layer 2 packet or frame which runs on traffic class 0, and there comes a traffic class 1 packet, the traffic class 2 fragment is completely separated, split apart. The traffic class 1 packet is scheduled in between and goes to the other side as highest priority. And why that is useful, of course, if you don't want to distribute clocks in your system, you have a unique mechanism to make sure that, for instance, timestamp packages can be sent from one side to the other with the least amount of latency. Device network routing in the layer 3. At the moment, UniPro 1.6 defines device network hooks and actually encourages further development of network layers. The network layer itself is not defined in UniPro 1.6, and that's where the next presentation comes in. Transport layer, actually we have virtual channel management, connection management, which is done there, so binding from virtual channel C ports to the destination network ID. And we have application backpressure handling. Means actually if the link is provides more data output than the application can handle, you have different ways how to handle this in the stack. You can drop data, you can implement end-to-end flow control. I will talk about that in another slide. There is a test feature that allows an easy testing of a link from an application point of view. So that test feature sends actually data to the other side, transport layer 4, and you can easily detect link errors or link problems. So from an abstraction point of view, the way how it looks like, you have independent logical channels which may have different traffic classes and different priorities. For instance, channel 0 communicates here to channel M, and typically within one channel you have in-order delivery. Of course, that's what you want, but between two different traffic classes you do not have in-order delivery because traffic class 1 can be much faster than traffic class 0. So if you want to use traffic class 1, actually the specification does not tell you really that you should do that for control signals only, but there is a hint that you should use that low latency traffic class only for control purposes and for interrupts and indications. So the application interface, how does it look like? We have, first of all, to clarify a little bit of terminology here, virtual channels are the end-to-end connections with C-port access point, and they are statically set up during the connection management of the stack. What is done during connection management is that the C-port numbers between local and peer are negotiated, and the mapping of the C-port runs into end device ID. That means actually that the entire address scheme for UniPro package on message level is actually the C-port. At the moment, there is no need to give a dynamic device ID to the stream. That may change probably later on when we talk about networking, but at the moment it's statically bound. Well, there's a spelling error you have probably spotted. Anyway, so the property assignment of a virtual channel includes actually traffic classes and end-to-end flow control, controlled segment dropping, and C-port safety valve. What that is basically all these end-to-end flow control, controlled segment dropping, and C-port safety valve mechanisms are conceptually there to avoid that there's back pressure on the link if the application doesn't pick up data. So what we want to have is a free link, and that is done basically because a network should never be congested. So in the end, any UniPro application should pick up data as soon as it's presented to it. So what are messages? Messages, basically it's a session payload and it's transmitted as bytes, as UniPro message bytes. And those messages have arbitrary lengths. It can be 0 message size and there can be infinite message size. So messages are just terminated by an end of message flag or end of message indication. This is also transferred to the far end. But besides that, messages are not at all interpreted by the stack. They're not correlated to protocol overhead. UniPro network is agnostic to the message content, and any message partitioning will not generate UniPro protocol overhead. So messages in UniPro are basically not memory mapped. There's no indication that you should send any address, whether physical or logical address, to the far end. So what you can do is you can actually say a message is a functional instruction. For instance, in the context of Ara project, a message would be insert this module on that slot, or release that module on that slot. So there's no real need to have any memory mapped content here. So what are segments? Actually, the UniPro stack chops incoming messages automatically into segments of maximum 272 bytes payload. And we thought that's a good compromise between latency, process latency, and protocol overhead, because every segment will get its own protocol overhead. And don't ask me why it's 272. That has history. Many protocols prefer 256. So CSI3 is working on 256, but that's the way it is. It's just so the application may control the segmentation. If lower latency is required, latency in the system between two UniPro stacks depends on the fragment size, on the segment size. The application can support fragmentation of the messages to less than 272 bytes by sending an end of fragment signal. So every change in C ports on the application side will trigger a segmentation in the protocol stack. So you can automatically segment your incoming payload by changing the destination. And packet arbitration happens actually on segment boundary. So between two peers, UniPro, peer-to-peer connection, there is arbitration on the between the different C ports on the application level or in the layer 4. And this arbitration happens should happen on segment boundary. So layer 2, preemption. This is the traffic class feature. I explained this already. So let's have a look at the application layer interface. So this is the basic application layer interface. There is an optional flow control implemented in the specification. But what you need to serve in any case is the data write and data read interface. And how does that work? It's really very trivial. Everybody who has connected to a FIFO will be able to handle this kind of interface. I mean, this is a non-normative part of the specification, but you can see it's very easy how to implement that. Most of the stacks implemented will probably use that non-normative part of the spec. So you have actually from the application, you have a TX valid. As soon as that goes high, your data and your byte enable and your C port ID are high. The C port ID corresponds to the virtual channel you want to send the data over. And as soon as you get the accept signal back from the stack, you can be pretty sure that your data arrives at the end. You do not know exactly when, but it will arrive at the end. And it will give you a result code. If the stack is not prepared to accept data, it will give you a result code. Well, probably remote C port is not connected or something like that. In this case, we have success as a result code. Then you have the end of message bit that is sent across the net, the UniPro connection. And there is this end of frame that supports you in segmentation, which is optional. So on the RX side, it's exactly the same. Also FIFO type of interface. As soon as the RX valid goes high, your data is valid. It tells you on which C port data comes in. There is RX data coming together with byte enable, and there is a fragmentation status. As I said, there are many ways to implement this application data interface. This is just a suggestion of the spec, but as I said in the beginning, we do allow also software implementations, and then probably this interface would look a little bit different. What is end-to-end flow control? Why do we need that at all? In a system where you have many applications, you might want to send across only data when you know that the application at the endpoint is able to receive that data. So that helps you in a phone concept like Ara. It helps you to minimize the buffers in the endpoint. So what we do is actually we use a credit system, and this is called end-to-end flow control. The remote side tells you how deep the buffer is and how many free space there is, and the local can send as many data as there is available, and in exchange it gets permanently updated by the credit system from the far end, from the remote side, and these are all known concepts basically, but yeah, it helps us to reduce traffic in the network if there is a chance that the endpoint cannot pick it up. So flow control mechanisms, again, it's very easy. The system is pretty much the same as the data interface, just that you transmit flow control information rather than data. So how to use the control interface? The stack has a very simple state machine here, because the MFI is actually in a position to do power saving on its own automatically. So what we do here is that is the power state diagram that is controlled via the DME interface. And basically, when you start up the UniPro peer-to-peer communication, you go from a link from disabled state to a link down state. And one of the sides, either peer or local, triggers the DME link startup. It can also come from both sides because the interface is completely symmetric. Now that's very important to stress. It's symmetric because that will be used later on in the Ara project. So both sides can send a link startup, and typically, if the link comes up, the link will be stable. So that is during link startup. What we do is we query all the link capabilities, and we negotiate with the far end side what kind of link is established. And then, while we are in link up, we can send data, payload data, from A to B and B to A. This payload data, actually, if there is no payload data to be sent, the MFI is in a position to shut down in the so-called auto modes into power saving status, not to consume too much power here. There's one active hibernation state, which you can enter via the DME, using DME enter hibernate, and also DME exit hibernate to go back to link up. And via the DME configuration control mechanism, you can also change the so-called power modes. That means even if you have a maximum capability of high-speed gear 3, nobody forces you to use high-speed gear 3. You can easily also use PWM gear 1, 2, 3 in a high-speed gear implementation. That's set by the DME power modes. So I talked in the beginning about this DME remote control. This is a very important concept. This is why I want to stress this here. So how does it work? So one side decides to remote control the other side. That's the mechanism that's currently used in UFS NAND flash devices. Yeah, so the UFS NAND flash device is pretty much, yeah, I wouldn't say dumb, but it's reliant on the configuration of the host. And how does that work? DME actually sends via this blue line PACP packets via the MFI to the other side, and via the means of PACP packets, it can access all the attribute space of the remote site. So as soon as the link startup is successful, you have this feature available, and that allows you completely to configure the remote site without any sideband signaling. Even if there's an optical media converter or a pigeon media converter in between, you can remotely configure without any sideband signaling. So what is import? We have an import which is actually a multi-lane bidirectional MFI implementation. So the import can carry asymmetric links. Actually, it's a plesynchronous link which has an embedded clock, and the receive clock to control the import needs to be 2000 ppm away, or well, can be in a range of 2000 ppm plus minus from the transmit clock, and it's still the data is correctly received. And 2000 ppm is a large value actually. So it allows you to control your MFI probably also via MEMS resonators. You don't need to have quads in the system. So sublinks, you have two sublinks in one import, one forward going, one reverse link. The sublinks are completely symmetric or they are asymmetric in the number of lanes, in gear or mod and mode. So within the sublink, all the lanes have equal properties. So if you choose to have a media converter on one lane in the sublink, you need to have the media converter on all the lanes in the sublink. So here's the demonstration of the asymmetric link properties. High-speed gear 3, for instance, you have maximum 3 times 5.8 gigabits per second on 3 lanes. But you can choose really to have only 3 megabits per second on one lane on the reverse channel. Yeah. It's not possible to omit the reverse channel because we do retransmission in case of an error scenario. So the error needs to be detected from the peer side by checking the CRC of which is attached to each packet. This is done by ACK-NACK mechanism on the feedback channel. And this is the reason why we cannot omit the reverse channel on the MFI. So the MFI actually has some nice features. So actually, it has DC power states. That means actually when you don't transmit payload data to the remote end, when you don't burst, the MFI goes into DC power state called sleep or stall. It's called stall when you're in high-speed mode. It's called sleep when you're in low power mode. And these modes can be terminated or unterminated. Typically on low-speed traffic, you would use unterminated links, and on high-speed traffic, you would use terminated links. But when you have short distances, you can even run high-speed on a non-terminated. That would be probably a very short distance between two chips. Clocking, well, I talked about that probably pretty much already. So one thing here is that you can even use RC oscillators for PWM mode. So if you're not talking about the full-blown high-speed gear 3 stack, like you would use in normal, well, if we are not talking about this full-blown stacks, we can do really lightweighted PWM mode implementations running without squads. So media converter support, there's basically 2 media converters envisaged in the MFI spec. There's a basic media converter that is not visible actually to the MFI. It's just a conversion from the electrical MFI properties into a non-MFI medium, into a non-MIPI medium, and back from the non-MIPI medium into an MFI specification galvanic link. And there's the advanced media converter that you have to program, but the MFI provides means to provide to program that media converter via in-band states. So this is a gear overview. there is actually no obligation for you to implement all the high-speed gears in an endpoint product. You can implement high-speed gear 3, but you can also choose not to implement high-speed gear at all. If you think your module needs only PWM gear 1 or PWM gear 2, 3 megabits per second is mostly sufficient for most of the interconnects. If you look at I2C, 3 megabits per second, for instance, is quite a competitive result, and most modules will do no more than that. So the Uniport itself will detect mismatches during link startup between the M-PHY capability and will adjust to those mismatches by downscaling, downgrading it's called, sorry. And the link is synchronized actually via the DME power mode. And the DME power mode runs a protocol where the gears and the modes between both sides exchange their control and end up in a defined synchronized state. So this is a MIPI power chart for the type 1 M-PHY, which we are using for UniPro. So here you see the high-speed mode and the low-speed mode. In the high-speed mode, you're running actually cycle from stall to high-speed burst back to stall. Alternatively, if you have a media converter, you run from stall to high-speed burst into the line config. And you need an active high-speed clock only when you're on high-speed burst. And UniPro controls the system automatically as soon as you have nothing to send. The system goes into stall. This is the so-called auto modes. And there you are in this very power-saving mode. And the same with PWM bursts. When you have no data to transmit, you end up automatically in sleep, which is a DC mode, no power to consume. Media converters, I think, many things have been said already about that. So the MIPI vision of that is actually that an MTX sends out MIPI-defined signaling. There is an electrical receiver in the media converter that receives those signals and transforms it into the non-MIPI-defined medium. The spec talks about an optical media converter, but actually you can use any media converter. We don't care really. That signal is caught by an MC-RX and reconverted into a MIPI TX, MIPI PHY signal and received by the MIPI RX. So how does the frame format of Uniport look on the M-PHY link? So actually we have this layer 2 header, which is 2 bytes, followed by a layer 3 header, which is 1 byte, and a layer 4 header, which is 1 byte, and followed by the payload, 272 bytes, and 4 bytes end of package and CRC. So that is very competitive. If you look to other protocols, you have much larger overhead. And in particular, the M-PHY supports that. There is 25% overhead on 8-bit, 10-bit encoding. But besides that, there is not so many overhead from the M-PHY. So there is a sync at the burst, at the start of burst. But that sync can be quite short. It can be as short as 2 or 3 cycles. So there's no big lead-in synchronization scheme required for the M-PHY at high-speed gear 3. So very, very robust and competitive protocol. That's my summary here. So we have a switched packet protocol based on M-PHY inspired by TCP/IP probably. That's what Uniport is. It's mature, stable, and really freaking easy to use. I mean, if you compare that to other protocols, it's really easy to use. Not easy to implement, be warned, but easy to use. We are actively supporting that by the M-PHY working group. There's a couple of smart guys sitting from various companies in the MIPI working group, in the M-PHY, and also in the Unipro. Uniport is extremely scalable, which makes it a very suitable protocol for Ara. So, if you don't mind, that's the end of this presentation. I would like to take questions for the MIPI-related part.
Woo, good stuff. Man. Jürgen, it's awesome. My 15-year-old is asleep over there, but that's only because we woke up at 5 a.m. Otherwise, riveting stuff. Okay, guys, we got a couple of questions. So the first question from IRC, from Duder Rams, this is the Duder Rams I'm thinking about. That's awesome. But it might be another Duder Rams, who says, what prevents a module from seeing traffic that's destined for another module? So how do we make sure that kind of data and communications are going where they're supposed to go and not being intercepted?
Yeah, okay. Right. This is part of my next presentation, actually. The idea is that in a network, there is mechanisms to block access. Yeah? So, of course, there are plenty of reasons to block access in a network. For instance, you might exceed the power figures of the entire phone. You might exceed the bandwidths totally allotted to your module slot. This is all done during after link startup. There's connection management, and in the connection management, there is a query of well, I should probably not preclude too much from my next presentation.
So you'll get into this in a little bit in the next section. Yeah. Okay. Okay, how about anybody here in the room? You guys have some questions you want to come up to one of the mics? Okay, so no more questions from the room, no more questions online that oh, there's a question? Where is the question? Oh, go ahead, sir.
Hi.
Hi.
Any notion of coherent protocols running over UniPro? So there's a coprocessor and the main host processor, coherency protocols across?
Well, UniPro does not preclude on the way the interface or on the remote and far-end application. You know, you can do whatever you want. You are free to have two application processors communicate between each other. You can exchange messages between passive devices. They only just need to, you know, the only thing you need to do is to feed your FIFO interface. That's all. I mean, there's no real intelligence required in your application. Of course, for a phone, it would be nice to have intelligence on board, I would agree, yeah. And talking from an application processor to a secondary processor may make sense very much in such a phone. You know? For instance, you can think about sensor hubs, where there is certainly also some sort of processing capability. They do not need to run an OS for using UniPro. You can just stuff in your payload and off you go.
Okay. Okay. Any other questions from the room? Okay, awesome. So listen, it's that part of the day when your food is settled in, when in many cultures around the world we take naps, and since we're designing for the 6 billion, we wanted to, if you want to take a nap, you can. Those at home, you're probably already napping. Those that are here, we're actually going to introduce an unexpected little icebreaker competition. So Jürgen, if you can just give us a couple of minutes, we're going to do this thing, and hopefully we'll still have some time. So,
thank you.
So those that are online, you can participate as well. So here's what's going to happen. We have David Fishman and Jason Chua walking around. They're giving 7 sheets of paper to every single blue table. The blue table that you're associated with is your team. Those that are hoarding the electrical outlets around the back and the sides, you might want to come in, because the reward for this competition is we're giving away one of the first Ara phones. Now, those that are online, so there are 2 phones that we're going to be giving away. We don't have the phones here today, but when they are available, you guys will get them for the first folks outside of our team, along with our Ara Scouts. What we're going to do is a quick 2-minute construction competition using only paper. If you're online and you're by yourself, that's fine. You can be your own team. What you're going to have is 2 minutes to construct the tallest tower out of paper. For those here in the room, it has to rise up off of the blue kind of top of your table using nothing but paper, so no other objects kind of supporting this or building upon it. Okay? So get together with your team, make sure each of you has a stack of 7 pieces of paper. And those that are online, go to your copiers, go to your office supply cabinets, get 7 pieces of paper. If you need paper, raise your hand. These guys need paper here, Fish. 7 pieces. You cannot start. You can talk about your strategy as a team, but you cannot yet start. Only 7. And we're choosing 7 because there are 7 layers to our logical architecture. Just to make sure you're all paying attention. Okay, raise your hand if you still need paper. Everyone has 7 pieces? Okay. You cannot start building. You can only talk about strategy right now. Okay, do all teams have, everyone has paper? Raise your hand high if you need paper. Okay, it looks like everyone's got paper. All right, guys, we are going to start in a minute here. You have 2 minutes to build the tallest self-standing structure only using paper. On your marks. Get set. Go! Minute and a half left. Just a minute and a half. Okay, we're halfway done, folks. You got a minute left. 60 seconds. All right, 30 seconds left. When we get to 0, you have to have hands off the paper. All right, we're getting down to 10 seconds, guys. When we get to 0, you can no longer touch your tower. You'll have to step away from your tower. 5, 4, 3, 2, 1. Okay. Everyone, step away from your towers. Okay, Jason and David, who do we got? What are the candidates here? Okay. We're going to have Jason and David, have they got a measuring stick? They're going through the audience. This team over here is still working on their tower, but they're disqualified. But I appreciate it. That's good. You want to make sure you feel like you finished. Where are we at, Fishman? Okay, we've got one measured. No, those guys are disqualified. It fell down. Yeah, where are we at? Do we have a winner, David? One more in the back. We've got 25¼ inches is our current leader. Now, if you're online and you made your own tower, you have to send us a picture with a measuring stick next to it, a measuring tape. You need to tweet it to us. Hashtag Ara Dev. And if we get the tweet within the next 60 seconds, it will be eligible for the online version of this competition, because there is a little bit of a delay. So there'll be one prize here, and there'll be one prize online. All right, Fishman, what do we got? We have a winner! Okay, team, come on up. Come on up. Come on up. We're going to have a final round. David, Jason, can you get these gentlemen each their own stack of 7? All right, guys. So this is round 2. This is the final rounds. You guys now are working as individuals. You have 2 minutes to do the exact same task, something that's lifting off of the stage. All right, we're going to get you 7 pieces of paper. And it is mano y mano, fight to the death. Do not blow on each other's towers. That is not a metaphor. Really, do not blow on each other's towers. Well, that's all right. Maybe there'll be some innovation. Let's see. I'll wait until everyone's got 7. You cannot start folding or creasing or crinkling until I say go. Okay. We ready? On your marks. Get set. Go! So for those that didn't hear, we chose 7 pieces of paper because we have 7 layers in our architecture. So just to make sure you guys are paying attention here. All right, we have a minute and a half left, you guys. You're done with 25% of your time. We have some different strategies going on. We have some accordion folding. We've got some cylinder making. I'm going to try to be very still so I create very little air. All right, guys, you got just over a minute left. Is there like a betting ecosystem going on back here? Okay. We're coming into the final stretch here. We got 30 seconds left. We have a couple of towers that are standing. We got some multi-story architectures here, and we have some disappointing kind of destruction happening. Everyone hold your breath in the front row, please. 10 seconds. 5, 2, 1. Okay, hands off. All right, good job, you guys. Fishman, who do we got? I think it's pretty clear. $22.25 and 26 3/4. Okay, well done. What's your name? Ash. Okay, Ash. Awesome. So Ash will be one of the first people outside of the Project Ara team to receive the first Ara phone. And so, awesome. Awesome. And for anyone that tweeted at us their picture with their measuring tape, we'll choose one of the folks online that's participating as well. And you're going to be among the first most active Ara scouts to... what's that? Sure. Google Glass. All right. All right, so we just wanted to mix things up a little bit and make sure that we're all awake. So thank you guys for participating. That was awesome. Okay, so let's get back to Jürgen. He's got his second part talking about the network, and then we are going to then get into our software system after that. And while we wait for Jürgen, I was kind of, as Paul asked me to do some of the emceeing, I was thinking of kind of how we could liven things up. So I had this one joke. It's the one joke that I'll share, I promise. So you have 3 engineers driving to the Ara Developers Conference, and they're all from the UK. You've got a mechanical engineer, you've got an electrical engineer, and a CS major. And along the way, the car breaks down. And the electrical engineer is like, oh, no worries, I can fix this, and pulls out his multimeter and starts opening the dash and testing the kind of electrical system in the circuits. And the mechanical engineer is like, no, I got this. He pulls out this kind of super cool like multi-tool, opens up the hood, and starts messing around with the gears and trying to figure out how this can be solved. And then the computer science guy, he's like, hey guys, come in the car. I know how to fix this. So they come in the car. He's like, here's what we do. We close all the windows. We get out of the system. We kick the boot. We get back in and open all the windows. That's how I solve all of my computer science problems. See, that's why I'm not telling any more engineering jokes. That's the one that you're going to get. Okay, awesome. Jürgen, welcome to part 2 of your network talk.
Yeah, I hope you are refreshed now by this little exercise, icebreaker exercise. I hope I didn't sedate you too much. Let's go into the next session, which is probably a more exciting one. This will be presented on behalf of Toshiba, because we have been participating in the Ara prototype development. And actually, it was our part to provide the UniPro network. And I will talk about the ways we implemented it and the challenges. And yeah, let's have a look how that turns out. So the first thing we have to clarify, what is the UniPro network, because MIPI doesn't do that at the moment. So we hope that the results of the project Ara networking will be fed back into the MIPI, but that should not preclude any kind of solution that we envisage for MIPI. It's just such when you engage into such a project, defining networks on a mobile phone, and you need to do some system simulation, you need to do system evaluation work, and that's what we've done actually. It takes a long time, so here we are. So what is the network? A UniPro network is actually nothing else but a bunch of point-to-point connections between switches. You cannot use a traditional bus architecture at 6 gigabits per second. You cannot tap your signal, so it's still point-to-point, of course. So the switches actually, here you see them in yellowish, orange, and the endpoints are in blue. And the way how UniPro 1.6 works at the moment, there's nothing preventing you setting up such a network already with the existing spec. You have to do that in the application layer. And that's how we started actually. We implemented the switch in the application layer because we wanted to be compliant with the standard. And it turns out that there are a couple of choices we should better have not done. So during the course of the project, we changed this architecture from a layer 4 application switch network to a layer 3 network. And that turned out to be much more useful. So in that network, in the UniPro network, actually, you're open to any kind of topology, simply because the end-to-end, the point-to-point connection has no preference who's master, who's slave, who's server, who's client. They are completely symmetric, the links. Yeah? So you can use any kind of topology in the network. And that's quite useful for our project because we don't want to be host-centric. And the reason why we can use any topology is because UniPro by MIPI has not defined any network features, so there's also no restriction to topology. So the physical device boundaries do not need to coincide with the network topology. So you can imagine, for instance, that a switch has its own endpoint and they reside in one device. That's very much possible. And in the UniPro network, you have maximum 100 128 endpoints. One of it is reserved later on for the supervisory controller. That's why I say here 127 endpoints. And when the switches have its own endpoints, it's obvious that switch and endpoint do a total maximum of 127. The target for the switches, of course, we want to be as transparent as possible for the application processor, for the OS. We don't want to change too much the OS, at least not for the prototype. In the end, for the target, for the objective system, quite a lot of things will need to change in the OS. Yeah, so we want to be symmetric in our switches. We don't want to prefer one switch port over the other, which you might think is a good idea if you have only one application processor. Yeah, you would think you give it higher bandwidth or whatsoever, or a better throughput, but we don't want to do that in the switch because actually our application processor can sit in any kind of module slot, so we do not know where it connects to the switch network in the end. So we defined, first of all, a couple of choices for our network we use in Ara. So what we want to do is we do not want to allow round trips. That makes routing tables complicated, it makes control complicated, and there's actually no need for it. So we just dump that. We want to allow only one routing path between two endpoints. That means actually that if you have two endpoints on two different device IDs, what that is, I come to that later, then we want to see only one static routing path. This static routing path is set up during the connection management. When the modules get inserted, you set up the routing tables, you set up the connection management, and then actually that routing path should be stable until it is reconfigured. That means static. So it's pseudo-static. You can reconfigure it on the fly, but it's not meant to be dynamically rerouted. And there is, of course, in our UniPro network, a guaranteed delivery of all message fragments. So if there is in our switch, if there is congestion because of arbitration congestion, then we simply stall the pipes, but we do not drop packets. And we made the choice that TC1 is good for control, and TC0 is good for data traffic. So TC1 will have eventually very low latency variance, so that can be used for global timestamp delivery, for instance. So how does it look like? So this is the phone itself, and we use as a topology a star topology in Ara. So basically that means we have a uniport switch bar. And the yellow thing here at the left-hand side is the supervisory controller that controls the switch bar. And we have, in the telephone, we have 14 UniPro interface blocks. And in this diagram here, there is, on small modules, there is one block. On large modules, there is two blocks. All those blocks, all those slots have the same properties. But not all of the slots need to be populated. The MFI is designed such, if you don't connect to it together with Uniport M, this is detected and simply the lane is shut down, not to consume power. If you decide to put in a dummy module, which has no electrical properties or whatsoever, then automatically the uniport in the switch bar for that dummy module is shut down. So per interface block, we have 2 TX lanes and 2 RX lanes. That makes 11.8 gigabits per second into each direction, maximum. Still keep in mind, we will not be able to run all these ports in high speed, so there is limitations to the architecture, of course. But there will be also low power implementations of PWM only. So how does that work? Oh, yeah. Right, so addressing scheme, I mentioned that. So every endpoint device has a unique device ID that corresponds a little bit to an IP address in the internet world. And the switch itself is reserved to run on the device ID 0. So if any of the module wants to send a message to the supervisory controller, it just addresses the device ID 0 and knows it arrives at the supervisory controller. Connection management. We statically tie the device ID to the ingress C port. So if a module sends data to a C port, the C port knows automatically to which device it is addressed. And the reason why we do that is, first of all, we don't want to burden the user of a module with some complicated addressing scheme. And the second reason is that we don't want to have the user autonomously spitting out data onto a device which should not be accessed by the endpoint. So how many IPs? One of the design requirements was actually that the entire system works also with 0 IPs. The reason for that is you do not want to have any sort of order in which you insert the modules. Yeah? So if you have a bare naked endoskeleton and you want to insert your modules, there should be no need to insert the AP first. You can insert modules in any kind of order. And typically, the prototype will have one AP, but of course, in the objective system, at longer time scales, there will be many APs possible. So UniPro supports up to 2047 C ports per endpoint. In reality, that will be less, simply because nobody wants to send 2047 streams into the system. So I would think the endpoint will work on 8, probably 16 endpoints, C ports. That's it. So you need to implement only the number of C ports that you really need for your endpoint. And yeah, in reality, this will be around maximum 32 C ports probably, because actually UniPro shares the device ID address space together with the C port ID address space, and 127 endpoints in the system correspond to 32 C ports each. You have the possibility to stack up to a higher number of C ports, but you have to sacrifice the number of endpoints in the system for that. So any endpoint that uses more than 32 C ports will have a reduced, will actually result in a reduced end device ID address space. So peer-to-peer communication is possible, and this is probably one really important aspect of this phone. The power plan for this platform will look much different than from ordinary phones. So we try to we will have a power overhead of UniPro switch bar, and we try to mitigate that by allowing direct peer-to-peer access. You can think about audio playback directly from NAND flash. You can think about tethering from your Wi-Fi module into GSM without the presence of an AP, or with limited presence of an AP. So we want to traffic the data where it belongs to and not channel it through the central application processor. Sorry. Yeah, one important concept here is that the switch supports collision-free traffic, for instance, between the yellow traffic channel on the right bottom side and the red traffic channel. As long as they do not have the same destination endpoint, there is collision-free traffic possible. Well, on the other hand, if you want to channel, if you want to connect 2 channels from the same service, you need to open up 2C ports. There is no such thing like broadcast envisaged at the moment. Yeah. So the network can be cascaded. That's simply quite useful if you know that there is 3 different form factors of platforms available. Then you might think about a bigger form factor like a tablet or whatsoever, where you want to cascade one switch bar to the other, and that is very well possible. And those cascaded systems still have only one supervisory controller that controls the entire network. So we have also another possibility of cascading, which is actually inside the module. If your implementation, or if there are implementations that implement switches in the module, then it's very much possible to have 2 endpoints in one module. You know, you can think about a combi module. And well, the benefit of having a switch inside the module is that you can better control your arbitration. If you leave the arbitration to the switch, you need to rely on the arbitration algorithms in the switch. And this way, if you plan to do a combined module, say wireless LAN and Bluetooth in one module, then it might be better to have the switch directly in the endpoint. So the supervisory controller, what does it do? Actually, what is it? It is basically a small low-power CPU sitting there and waiting for commands. And what it does is actually it takes away the layer 1 to layer 4 configuration of the switch from the AP. So the AP doesn't have to care about that switch configuration. That's quite useful in virtualized systems where you have different streams trying to configure something independent from each other, and you get into collisions if you say this kind of configuration is done by the supervisory controller, then the AP doesn't even know that there is a switch. In theory, in practice, there will be interference, but we keep it as minimum as possible. So the switch configuration happens via TC1 frames. So they have always the highest priority in the network. There is not too many TC1 frames, only from and to the supervisory controller. That means there is no congestion for all the control. The switch is basically congestion-free for control and interrupt. So the supervisory controller acts as a command interpreter for high-level OS commands, and the OS would probably just say, okay, please eject the module, or please start up that module, and sends a macro command to the supervisory controller. Supervisory controller unrolls that into command traffic in the switch and makes sure that it arrives at the right modules. So the supervisory controller in the objective system will also be responsible for QoS surveillance. So if there's, for instance, layer 3 arbitration problems between packages going to the same destination, the supervisory controller would monitor that. If there are too many arbitration collisions, it would probably send a signal to the AP to reconfigure or to reorganize bandwidth schemes. And yeah, this is one of the tasks of the supervisory controller, to have this QoS surveillance. Another story would be, for instance, if there is, for some reason, a bad link. Might be that somebody shot the pigeon, like there's dirt under the capacitive coupling or whatsoever. Then of course, the supervisory controller would monitor the increase of bit error rate and probably flag up in a GUI, please reinsert your module, clean your capacitive coupling or whatsoever. And in the switch, the supervisory controller takes care of bandwidth control. The arbitration will be bandwidth controlled in the layer 3. So we think about a bandwidth quota system for every endpoint. This is not completely elaborated, so probably I will talk about that in one of the next DEF CONs if they still invite me, if I did not sedate you too much. So once we have a solution for that, we will let you know. And the supervisory controller will handle power mode and hibernation requests from the endpoint. The endpoints themselves will probably not autonomously go into hibernation, simply because that means that we cannot keep track of the entire end-to-end path. When we have to go into hibernation, it might affect also other modules, and that's where the supervisory controller resolves conflicts. Yeah, and the supervisory controller is also responsible for layer 1 to layer 4 configuration of the endpoint module itself. That is a very important concept. You do, as an application user of the endpoint, you do not have to configure your own UniPro stack. The only thing you use in the endpoint is the data interface and the flow control interface. Very convenient. Yeah, what is the task of the AP? Of course, it runs the OS, maybe layer 5 and up. It will have local flash, local SRAM, local DRAM, local graphic engine. I was asked frequently about what about a graphic engine sitting on one module and the AP on the other. Probably the latency requirements for graphic engine are so tight that we cannot accomplish that in the UniPro network. But we have to see. I mean, this is part of an investigation we have to drive. So for the AP, several times said already, any slot is permitted. So a 2x1 slot, of course, a 2x2 slot. You can plug it in anywhere into the endoskeleton where you like. And the switch works also on basic operation without any AP. So how does an AP connect to the endo switch? Basically, on the left-hand side, this is the system we envisage. Probably there will be application processors running Uniport. So either one Uniport or two Uniports. Remind you, in the 2x2 that we have 2 interconnect blocks, so it may connect to 2 Uniports. For Spiral 2, most likely the application processors running on Uniport are not yet available. So in order to make Spiral 2 possible, we think about a bridge. And I think my colleagues here from Toshiba will tomorrow talk about that bridge project a little bit. So I will not go into detail here. So how does the switch architecture look like? There is actually the layer 3 part that is different from the standard UniPro 1.6. Anything else should remain the same. So in the end, it should be possible to seamlessly attach UniPro 1.6 modules to that switch and basically see the switch as transparent UniPro 1.6 endpoint. We will not change, or we do not change in our project here, the protocol layer. So everything that exists in UniPro 1.6 will continue to exist in this Ara project. Then we have a layer 3 switch, and that is really the only difference. We have an arbitration scheme there for every port. We have routing tables we need to program, and there's a connection status memory, which actually tells the switch whether access to a certain Uniport is blocked. I think that was one of the questions, or is granted. So that connection status mechanism needs to be convinced to release data traffic to the Uniport, to the endpoint. And if that is the case, then traffic can freely flow. But the supervisory controller has also the possibility to block access. So the endpoint can run multiple applications, and multiple applications require multiple C-port streams and multiple virtual channels. So they need to be multiplexed and arbitrated. So current scheme is actually that we use a round-robin arbiter, very simple. And actually, The only thing we have to take care about is that the application streams in sum do not exceed the total bandwidth that has been communicated by the device descriptor base to the endo switch. If we make sure that that doesn't happen, there will not be back pressure from the switch. If we exceed the bandwidth that has been informed to the supervisory controller, the switch will automatically block access and grant it only on when there is no application, when there is no arbitration backlog from the switch. Endpoint connections. How do the endpoints connect to the switch? Actually, as I said, all the stack control is handled by the supervisory controller. That means the DME, the device management entity, cannot be actively accessed from the endpoint. The only thing we want to allow is status messages and indications to the application so that you know that your stack is in a sort of erroneous condition or not ready to accept data or whatsoever. But it should not be required from the endpoint to do an active setup of your stack. That should not be required because you can do a lot of things wrong there in configuring the UniPro stack. So that's a task we would like to leave to the supervisory controller. So the endpoint maps actually a device descriptor into the DME management space. And actually this interface table, or this device descriptor has things like interface table, like map table, like functionality, like device class and maximum bandwidths, streaming functionality, all this kind of information. And the way how that works, if you insert a module, let's say the left-hand side module will be inserted into the right-hand side skeleton. How it starts is that you do the mechanical insertion into your slot. At some time you get power. The module powers out on reset, powers up on reset, and will start autonomously a link startup request. The link startup request to the endoskeleton will start the layer 1.5 link discovery procedure. Unused lanes will be shut down. The speed will be negotiated automatically, and the module user would not even notice that all this happens in the background. It will be done automatically for you. Once that has happened, you have link startup, and the supervisory controller has access to your device database. And the first thing the endoskeleton does on a module with link startup is it magnetizes the EPMs. It sends a magnetizing pulse. The module is basically fixed in its slot, and it queries the DDB and knows actually what kind of module is there. Yeah? Now you can, the endoskeleton, the supervisory controller, makes a choice, probably together with the AP, whether to connect or reject the module. Reasons for rejection could be that the power plan is exceeded, that the bandwidth is exceeded, that the module is blacklisted for security reasons. If all that is not the case, we connect with connection management. We enumerate our device, we attach it to the network, we set up our CPORT channels, and we can transmit data. This is a little bit subject to change. I mean, this may change in details in one or the other way, but that's the way how we envisage the access control to the network. So how can endpoints be implemented? So in the prototype, of course, we have an FPGA implementation on the left-hand side. But FPGA implementations, we use actually the parts from Lattice because they have a very small form factor and the only form factor that fits onto a 2x1 slot. FPGA implementations, in my opinion, they are not really limited to prototyping. Yeah, so the reason for that is that people will have imagination and they will come up with all kinds of application scenarios that may require only
once an hour, taking a measurement sample of your environment. So why not doing that in FPGA? I mean, as long as the module is dead, it doesn't consume power. Thanks for the time allotting. So, yeah, in a way, it's I think it's a viable solution to allow also FPGAs in a final objective system. And we should think about that, how to make that possible. One possibility could be to hook up a Unipro M5 stack on top of a lattice FPGA, for instance. Yeah? So then for the lightweight modules, a software implementation could be envisaged. And I mean, the less speed you need, the more you can implement in software. A PWM1 may be completely available in software. PWM Gear 2 may have layer 1.5 in hardware and the rest in software. So the more speed you need, the more you will need to implement in hardware. And a full-blown high-speed Gear 3 system requires certainly a full hardware implementation up to stack 4, or layer 4. And that would be then the right-hand side architecture. Yeah, one story here. The first sentence seems not to fit into that slide. It belongs probably to the last slide. Anyway, I just want to mention that the endpoint is forced to pick up data from the endoskeleton as soon as it's presented, just to avoid back pressure from the switch. So FPGA prototype, what did we do there? So the objective was, first of all, proof of concept for this novel Unipro networking system. And actually, we wanted also to have a module development platform for you to start with. And the idea of that FPGA platform was, I mean, that started off with Motorola, not with Google. And Motorola had probably not the control over the AP Android system that Google had. So the objective was, do anything, make anything possible, but don't touch the operating system. So we wanted to leave the AP software as untouched as possible. And that led to the following system design. We had an application processor that runs standard protocols. We choose 5 of the most widespread standard protocols and routed them into Unipro Bridge. The Unipro Bridge converts that 5 protocols into Unipro and sends it to the switch, and the switch distributes it to the endpoint, to the target endpoint. And the endpoint can be in the prototype something like we call the fun modules, which is, for instance, a heart rate monitor, or thermal imager, or whatsoever. I don't think we have the heart rate monitor, we have the oximeter. It can run to an endpoint, battery charger system, or to a display, or to a Wi-Fi module to set up a Wi-Fi connection. And the differences between the FPGA and the objective system is actually due to size limitations in an FPGA implementation, which is normal. We implemented only 6 active slots, 6 active interconnect blocks. And we use only one single lane. The protocol we use is so-called TMPI, which is actually an M5 emulator protocol, which is specified in Unipro. It's a test protocol which can be used for testing, but also serves for all purposes to do an FPGA system. The maximum net bit rate is 600 megabits per second. And I just give you a precaution. We run the display, the high-resolution display, due to that data rate limitation to less than, well, I think equal to 15 frames per second. Yeah? So you will not have the look and feel of the objective target system. It will be a little bit bumpy before there are complaints. I just mentioned that. It's simply owed to the fact that we can run only 600 megabits per second into the display. We did not implement TC1 traffic. So in that FPGA controller, the configuration routing from to the supervisory controller uses traffic class 0. We can do that because the star point architecture has very predictable latency behavior. And the switch arbitration uses a simple round robin, and probably in the final system we will have a bandwidth-based quota system for arbitration. So instead of protocol-agnostic bridges, we are sending L5 messages. The AP interface just tunnels the standard protocols, and these 5 standard protocols are SDIO, I2C, I2S, DSI, and GPIO. They tunnel these protocols over to the other side. In a target system, you would probably want to avoid tunneling those protocols directly, but instead you would send layer 5 messages to the endpoint, and the endpoint can do whatever it likes to do with it, unrolling it into I2C, I2S, or GPIO. And the link startup in the protocol, in the prototype, does not use hibernation. It does rely on sideband signaling for power up, power down, and the LVDS is DC coupled as source synchronous implementation and not as plesynchronous M5 system. There's no capacitive coupling, and we do not have a global time synchronization. So on the I2S, we use data dropping and data interpolation to make up for lost data rate or increased data rate from the host. So that actually finishes my presentation. Not quite. So here you have. That's the last slide, I promise. So that is a typical example of an endpoint, and you see it's really easy. As soon as the UniPro stack is there, you just have to convert your legacy protocols into a data stream. You run that into FIFO, and the FIFOs have arbitrary lengths depending on the bandwidth you feed into that. They go into a C-port arbitration, and off you go through layer 4, layer 3, layer 2 into TMPI, from there into the LVDS SerDes. And that's how it's done. And the endpoints, they look very much similar, only into the other direction. And then on the lower part of the image, you see the EPMs. They get magnetized via the device entity, the device management entity from the supervisory controller. And the DDB will be queried also from the supervisory controller. Has no direct access of the standard protocols to EPM or DDB. Yeah, so if you want to access your EPM, the only way how that works is to send messages to the supervisory controller sends the message to the AP, AP starts up a GUI, you press the button, please eject my module, the GUI the AP sends back the message to the supervisory controller sends back the message to the EPM and demagnetizes it. So that's it from my part. Time for questions.
All right. Thank you, Jürgen. Well, first of all, I got to tell you that on IRC, there's a fan club starting to develop for you, especially Smadger. He says, "We love you, Jürgen." And then Yari2 is saying, "I love you more." So anyway, so we actually have a good number of questions. We're running a bit behind time, though. So let me just ask what I think will be an easy one, and then the rest of them we'll share the questions with Jürgen so he can give direct answers. Okay, so the question here is, what is the minimum latency between EP to EP?
Minimum latency is basically determined by a couple of system parameters. Basically, it's the layer 2 buffer that adds to latency. You need to have one frame in the layer 2 buffer. There's no write-through buffer implemented in UniPro. So 2 endpoints make up 1, 2, 3, 4 frames latency plus the M5 speed latency, of course. You can reduce latency by downsizing your frames. 4 buffers latency, so 4 times the traffic time you need for 272 bytes packet. I hope that answers the question.
I believe it does. That's great. Okay, we have a bunch of other questions, but we're going to save those for later and give direct answers. So let's give it up for Jürgen. Amazing. Awesome. Thank you.
Yeah, thanks.
I love that last slide joke. That was awesome. Okay. So now I'm just going to welcome back to the stage Ara Kanayan and Marty Bolivar. All right. So you already know a little bit about Ara, but just a quick thing about Marty. So, he's working at Leaf Labs. He's heading up some of the software aspects of Ara, and he just got his first phone, not just smartphone, but like phone, what, about 2 weeks ago? And according to his, what's that? He had one 5 years ago, but for some reason he discontinued use, and his friends have been telling me how frustrating it was to connect with him because he just thought he'd be on email all the time. So anyway, we're very glad to have someone who just bought their first phone a couple weeks ago to be leading our software work for Project Ara. All right, so these guys are just getting their final miking up, and we're getting to the end of the day. After that, we're going to have Elwin come back up on stage and talk a little bit about the environmental and certification. There were some questions earlier about dust and water and some of that stuff. And then we'll end out with just some description around what's happening with the licensing. And after that, we have a little gathering down below. There's a really cool maker. His name is DJ Poet. And he's actually, he does a lot of DJing and collaborations with the Black Eyed Peas. And last summer, he connected with us because he wanted a hackable phone to do some really cool stuff around 3D printing and photography. And so we invited him to come up, and he's super excited. He's got some members of his crew. He's going to be setting up. I don't know what he's got planned, and we could barely understand exactly what he was saying on the phone. He was so excited. But that's going to be happening. So that's going to be happening downstairs in the main area and outside. Okay, I think I've stalled long enough. Welcome, Marty and Ara.
All right, thank you, Daniel. So I'm just going to, this talk is this afternoon is a guided tour through the MDK, and there's a section of the MDK called System Services that covers some things that didn't fit anywhere else, and so I'm going to tell you about those, and then I'm going to have a call to arms about how we should develop the peer-to-peer future of device drivers, and then I'm going to turn it over to Marty. So the first thing is in the system services, there's an out-of-band wake signal that is in the platform, and this has to do with how the system powers on, right? So the idea is this is a truly modular phone. It is not a phone that has some peripherals added, but the whole phone is modular, and so the power button can be on any module. And from an actual dead stop with no power consumption in the phone, then it has to be able to be powered on with the power button in any module. And also, we want to be able to support multiple modules being able to power up the system. So for example, you could imagine an audio module that included a always-on speech coprocessor that wakes the phone on a hot phrase, or features like that we want to be able to support with the platform. And so you see on this system diagram here, there's the endo in the middle, and then there's these two modules shown. And on the bottom there, in the blue arrows, you see there's the MFI or LVDS transporting Unipro that you've heard a lot about, and then there's also logically a wake signal, and the endo can wake a module, or a module can wake the endo. And in a module that has the power button, this wake signal is connected directly to pressing the power button of the module connects the power and turns this on. Now, in the objectives, so the idea is when you press the power button on a module that has a power button, that wakes the endo, and then the endo can then go ahead with waking up the rest of the phone and starting up the system. In the objective system, our plan for this is to use a CW burst on the capacitive data interface, which can then be received by a diode detector, which is zero power, right, on the other side, generating a CMOS level that then can wake the system from a microamp state. In the prototype, we're using the DC level of the LVDS pairs. You'll see in the schematics in the MDK, there's wake lines that go between the modules that allow a module to wake the endo or the endo to wake a module. Module detect is another topic. So how does the system know when a module has been plugged in? And there were some things we've talked about for maybe there should be an optical sensor, maybe there should be a leaf switch, or things like that. And we've just tried to be really minimalist on this. And And so what we've converged on is there's, first of all, no detect when the system is powered down. So if the phone is actually off, it's not able to tell that a module has been inserted, although you can if you insert a module that has a power button, you can press the power button and turn it on. So there's no sort of startup problem there. And in the objective, our plan for this is to use M-PHY linkup, which could be from the hibernate state, so it could be while the phone is in sleep, to detect the insertion of a module. And in the prototype, we're doing this using the DC level of another LVDS pair. So the same mechanism for wake, but here used for detection of insertion of a module. Enumeration, Jürgen talked about this some, so I'm not going to belabor it, but just enumeration is via Unipro DME, and there's a Unipro vendor and product ID that every module developer will get. When we have functional drivers, which I'll talk about in a middle, also in the DDB, there's device class specific parameters defining your screen resolution and things like that. Now, of course, there's also nested enumeration for bridge devices, meaning that if you plug in a device that has a Unipro to USB bridge on it, right, then of course the operating system is then going to enumerate your USB device after that, or the same with an SDIO device and so forth. EPM control is via Unipro DME. Jürgen has completely addressed this, so I'm not going to take any time with it. Okay, so now I want to talk about another topic, which is peer-to-peer drivers, peer-to-peer communication. So the physical layer and the network layer supports peer-to-peer communication between modules, which is exciting and which is different than USB, for example, which doesn't. And so it would be great if the ecosystem of modules and drivers and such develops such that peer-to-peer communication can be utilized in a useful way. And you could imagine peer-to-peer communication between modules is very good for two reasons, right? One, it reduces the power consumption of the system because data does not have to go through the application processor and consume power there and then come back out. It increases the speed of the system and responsiveness. And then another thing it does is it fundamentally improves the modularity picture, right? So if you have an application processor that's old and you get yourself a brand new modem and you get yourself a brand new Wi-Fi, right, then you could do tethering, really fast using the fastest new, 6G cell phone network and Wi-Fi, the new Wi-Fi standard not yet developed, right? But if you have your old application processor in there and all the data has to be funneled through there, then you can't do that unless you upgrade it. And so the modularity picture is not as good. And so this chart is just showing all these different use cases for communication peer-to-peer, tethering, phone call, music player, video recording. Every line on this chart represents some useful use of peer-to-peer communication, I suppose except for the module lines that go to the application processor. Now, the thing about this, though, is that in practice is tough, right? Because you need a lot of shared functions, which are normally in the SoC, right, to be able to really make use of this. Like you need, for example, format conversion. If I am compression and decompression of audio or video, merging and splitting of network streams. My tethering thing doesn't work if the TCP IP stack only lives in the AP. Video compositing for having a live preview on the camera, audio mixing, all these shared functions that sort of more and more are getting put into SoC hardware, but there are not standards for how to do these things on a network. And so all of us together here, right, should figure out how to create this peer-to-peer future. It would be great. Now, there's a start out there right now. There's these MIPI standard device-independent protocols that could be used as the protocols for this, right? There's CSI3 for video streaming, DSI2 for display, UFS for flash storage, right? All of these define how to talk to a device without any of the specifics of the register arrangement of the device and that kind of thing mattering. It's going to be a big project to actually do peer-to-peer layer 5 plus communication, though. So in the near term, we're also supporting host-centric legacy device attached via bridge chips. And you'll hear a lot more tomorrow about these bridge chips that bridge Unipro to USB, SDIO, I2C, I2S, GPIO, that kind of thing. And the layer 5 plus, meaning the layers above UniPro, protocol for communicating with these is RPC to a remote host controller. So for example, the I2C interface, right? There's a concept of an I2C transfer, and any I2C interaction can be embodied in this abstraction, and there'll be an RPC mechanism so that you can, straight from your app, communicate with your I2C device. So with that, I'm going to turn it over to Marti, who's going to tell you about software.
Thanks, Ara. Am I on? Is this thing on? OK, good. Hi, my name is Marti Bolivar. I'm here to talk about software. In particular, I'm here to talk about Android. Everybody here knows what Ara looks like in terms of its hardware. And that hardware has some implications which imply challenges that we're going to have to overcome in terms of supporting Android on it. So you can see over here on the left, you've got your traditional phone, and on the right, you've got your Ara phone. And these are the characteristics that differ, which are most important in terms of supporting Android. Pretty much, they all have to do with fixed device configurations and lack of hot plug support. There's also this issue that there's a single vendor per phone in a traditional phone, and they make the system fingerprint. They say, like, this is the Android that runs on this phone, and ship it off to Google for certification. Whereas here, there's this giant ecosystem of vendors that's contributing towards the configuration of any phone at any one time. So we're going to talk about all these issues and how they affect us and how they affect Android support. And we're going to start from the bottom at device drivers and work our way up all the way through the Android platform. Before I get there, though, let's talk a little bit about how Android is built today, just to try to keep the talk accessible to people that haven't done any Android platform development work. At the bottom of Android, there is a Linux kernel. And so the kernel's primary responsibility is to abstract the hardware that's present on the system and provide higher-level interfaces to the rest of the operating system. And then in addition, and this is something that's not common on other Linux-based systems, which is sort of unique to Android, is that on top of the kernel, there are a set of hardware abstraction libraries, or HALs. And the APIs for these libraries are defined by Google. And usually the vendor will go ahead and fill out those APIs. And the product is provided as a set of shared libraries that are put into the phone and used by the higher levels. And those higher levels are the meat of the Android platform, which are provided by Google. And they take the form of some system services. And so if you're familiar with the traditional Linux, these look a lot like daemons, but they're not called daemons in Android. They're system services. And they are the basis of what is essentially an object-oriented operating system that's running on top of a Linux kernel. So all the way at the top of that are applications, all the apps. They communicate with system services over an interface called Binder. And the system services then proxy what to do to talk to the kernel, usually through a HAL. So the HAL library gets dynamically linked into the process that's running the system server, or whatever service in question. The HAL will usually issue whatever syscall is necessary to get the kernel to do the hardware, to make the hardware do what it is that we want. OK, so let's move on, now that we've all got a bit of context, and talk about the requirements that we have developing Ara for our device drivers. One of the main ones, of course, is that we have to support device drivers that have never been written yet, device drivers that we have never conceived, that are not part of any existing kernel. Another one that is important, especially on mobile platforms as we know them today, is that our drivers have to work on various different kernel releases and on various different processors. So many of us are familiar with the fact that most phones are based on ARM SoCs. And the ARM architecture, pretty much just defines the instruction set and leaves the rest of the hardware, peripherals and interfaces that are available on the application processor up to the vendor to provide and to specify. So there's going to be a bunch of different, ways to access hardware depending on the chip you're using. And in addition to that, the internal kernel APIs that device drivers use are wildly unstable over time. Probably a bunch of us are familiar with stable API nonsense.txt in the kernel's documentation directory. It says, the API is unstable. It will always be unstable. There are really good reasons for this, and there are. I'm not trying to say that there aren't. But it does sort of provide a challenge to us in that, even the exact same kernel sources, if you compile them with different flags, you're going to end up with structures that have different sizes and alignments. And so a driver that's compiled with the wrong flags isn't going to work on the same kernel sources on the same processor. So that's a challenge. And then these final two requirements are mostly security related. We need to ensure that malicious or misbehaving drivers don't mess up anything else. Don't bring down the system, don't DOS us, et cetera. So these requirements taken together have led us to conclude that there's pretty much a two-pronged approach, which we're going to take, and that seems to be the viable solution. That's outlined here in our objective device driver slide. So this, as I mentioned, is a two-pronged approach, and on the right-hand side, there is this approach where we've got device class drivers. These are, we've talked about these before. They're going to be based on Unipro. We will provide these drivers for SoC vendors to integrate into the kernels that they release with their AP modules. And the expectation is then that, it's kind of on the SoC vendor to ensure that the device class drivers are well integrated and that, supported device classes which work with these drivers are going to be functioning properly. So that's, in-kernel drivers, and since we're providing the class driver and, we're checking out the kernel that's given to us by this SoC vendor, there's a reasonable expectation that the result is going to be secure and perform well. On the left-hand side, we've got a user space solution that Paul alluded to earlier. And this is what is going to be used to cover cases like modules which use bridge chips, which interface with chips that are not speaking Unipro, like maybe they speak I2C or some other protocol. And so the way that that's going to be supported is that, again, we will provide a driver that is going to be able to communicate with the bridge ASIC on the other side. So this GP bridge ASIC, or general purpose bridge ASIC, is going to live on the module, the non-AP module. And its responsibility is going to be to intermediate between the Unipro network and whatever existing protocol like SDIO or I2C is in use by the chip that the module vendor is interested in. So somebody has to drive that, and it'll be this driver. And then in order to allow the module vendor to support that chip or the specific functionality of that chip, we're going to provide a set of stable ABI. So people love to fight about what's stable ABI, and we're going to say what we give you is stable. Now, maybe it's going to be a magic device in some ioctals. Maybe it's going to be a special socket. We haven't nailed down the API yet, or the ABI yet. But we're going to say, this is going to give you a stable interface that userland drivers are going to be able to use to issue commands to the host controller on, or the host controllers, I should say, one for each protocol, on the GP bridge ASIC. So that's a two-pronged approach. Either way, whenever a service or a HAL, how does this work in terms of the syscall interface? Well, on the right, it's very traditional. The syscall goes down to the class driver, it talks to the native Unipro module, result comes back, everybody's happy. The solution on the left is going to be very familiar to anybody that's familiar with Fuse or the file system in user space. And what's going to happen there is that the service, or more likely the HAL, is going to issue a system call, which goes down into the, a device driver will end up needing to deal with. That goes down into the driver core, which we've augmented to bounce the result back into the userland driver, which the module vendor has provided. The module vendor driver bounces the result back down into through our stable ABI into the GP bridge ASIC driver, which does the I/O with the remote side. Result comes back, winds its way down, and up into that S shape back into the original process that issued the syscall. So that's our device driver story in the objective. Next slide. OK, now what about the rest? What about everything that's on top? Well, the situation can be summed up simply as Android is not modular. It's awesome, and it was designed for today's phones, but that has some implications which are challenges for us on Project Ara. So for example, if you're porting Android to your device, there are a bunch of configuration files that you have to write. You want to support audio on your device. Well, here's some files that you have to write. Say, these are the audio interfaces I support. These are the bit rates that they support. By the way, these are the hardware codecs that are baked into my machine. What do you do with those files? You take those files, you stick them into a read-only partition, and you wait for Android to read those files once at boot. Super hot plug, right? Similarly, a lot of these HAL APIs, so Google provides these HAL APIs, and module vendors hardware vendors fill them out. The shared libraries are also stored in a read-only partition. Their APIs often preclude hot plug, so like it's, there's a giant angry comment in one of the graphics or one of the display HAL's APIs that says like, thou shalt not hot plug the primary display. Everything will break. Sensors assume that the set of sensors on the system is fixed. The list goes on like that. Another issue that you might not think of originally is that, well, okay, well, why don't we just like let module developers get into the house and fix this situation up? The reason you can't do that, and that's one of the reasons why we want to segment the userland drivers into their own processes, is that these HALs get linked into some fairly privileged processes. Almost all of the services on Android live in the giant system server process, and so we can't have unknown code that hasn't been, metaphorically using Paul's earlier statement, X-rayed by the government to be OK. And additionally, the HALs as they exist today end up being pretty tightly coupled to whatever kernel driver you're using to actually support your chip. There are some other issues, like the system fingerprint that I alluded to earlier, that the phone manufacturer ships to Google to say that like this is the gold standard Android that I'm about to OTA to all my phones. Is that OK? Includes in the checksum all of this information, like all these static config files, all these HALs, all this stuff. So that's no good. And finally, as I mentioned earlier, ARM pretty much just specifies the instruction set, leaves the rest of the details to the SoC vendor, and so it hasn't, taken the time, it hasn't, it's chosen not to provide us with the mechanism to sort of generically query and enumerate the hardware that's available on an ARM-based system, which is in practice what we're dealing with most of the time, not always, of course. OK, so what to do? Well, what have software engineers done always? We generalize and we abstract. We're going to have to take these static configuration files and replace them with a dynamic alternative. We're going to make that discoverable through the HALs, which we will update the APIs so that system services can be notified of the way that the hardware configuration of the phone changes so that they can react appropriately and ensure that apps can do the right thing. We're going to have to take all of that stuff that's currently hardware related and that is included in the main build image for the phone and stick it into another partition, which we will specify so that when you're making your AP module, you can still get certified without having to know what the phone looks like right now. Yeah, that's the objective modularized Android. OK, to sum up, I want to talk a little bit about how this kind of interacts with the hardware. And Paul showed this slide earlier, so I won't spend too much time on it. But you see on the left, there's Android. There's that Android stack in miniature that we saw earlier. That, of course, runs on the application processor. And there are two classes of drivers. One talks to a class-conformant device, which we expect to speak Unipro natively. And the other one is a legacy or non-class-conformant device, which doesn't. And you can see that the AP is going to talk through the bridge ASIC. I guess a lot of this has been covered already. When I made my slides, I didn't know. So I won't spend too much time on this since we're running low on time, and I don't want to bore you. But yeah, that's how it all fits together, hardware, software. And that's what we want. What do we have today to get going? As Jürgen said, we kind of made this prototype under the idea that we should try to leave as many device drivers, et cetera, unmodified as possible to get off the ground quickly and to enable you to get off the ground quickly, solving a lot of the electrical and mechanical and other firmware problems that you're going to run into as ASIC development and all this driver development can proceed in parallel. So we've got some hardware. We've got some development hardware. We've got a development switch. We've got a development AP board. And we've got a generic kind of endpoint board that breaks out all those native protocols that we can talk to today and intermediates that to the Unipro network. There is a talk, a development hardware software talk tomorrow, and there will be a panel. I'll be on it. I'll be happy to answer any questions you have about it. And in addition, to support the AP board that we have, we've got, as has been mentioned, we forked a Linara release of Android, and we added a little bit of extra prototyping sauce to kind of make it easier to get off the ground in some cases. I think earlier there was a question about like, could I make could I make a thermal imager or a pulse oximeter in a day? We did, as I recall, write the pulse oximeter app in like a week, right? And that was made possible because we added a bit of extra special sauce to access, system buses like I2C and GPIOs from apps, so that you don't have to worry about writing your own device drivers if you're dealing with kind of simple cases like this. And all that code is going to get open sourced. And so watch the Project Ara website, and we'll announce the release when it's ready. So that's what I got. Thanks very much.
All right. Welcome. Ara, why don't you come on up. We got a couple of quick questions for you guys. Dieter Rams, again, asks, will the information be unicast or multicast for multiple modules that need the same information?
So I believe, as Jürgen mentioned earlier, and he can correct me if I'm wrong, the Unipro network as it stands does not support broadcast. So you'll need separate connections to each module.
All right. Easy. Smadger asks, is there a way to isolate a module from communicating peer-to-peer with another module, but still keep its functionality?
Yes, that is largely the job of the supervisory controller, which controls the routing table on the network.
Awesome. Those are the two questions we got. How about from the room? Anybody got questions on the software side? I'll bet there's a bunch of folks that are trying to think about how to make this their modules work in this environment. Got a question over here? Yeah.
Just a quick question on implementing drivers via the user space API for high data rate applications.
Mm-hmm.
I'm curious whether you have any idea of whether the scheduler C groups or CPU set C groups are likely to be able to achieve good real-time bounds at present.
Yeah, that's a really good question. Of course, when you're dealing with any user space drivers, there are a lot of issues. All the extra context switching can imply extra latency. There's a lot of concerns that are mostly performance related with that sort of architecture. I think that we're going to have to bite the bullet and just try to cover the really important cases with class drivers. And then maybe there will be more of a performance hit for these sort of special purpose cases. Of course, as you mentioned, there are a lot of knobs you can tweak in your system to try to control the priority of various access to different resources. Yeah, I think, to my knowledge, that there are still some open questions in that regard, and so I would say that my answer to that for high-performance cases is try to fit within a device class, and it'll be incumbent upon us to provide satisfactory device classes to cover those cases.
But that's good feedback too. It's good feedback.
Yeah. All right, we got another couple of questions here. Go ahead.
I also have questions about your idea to put drivers to the user land, user space.
Right.
I'm wondering, did you guys already make some research, and you confident that it's possible? Because there's many reasons why drivers typically reside in the kernel.
Sure.
And I'm just wondering, let's say, video driver or Wi-Fi driver.
It's a what kind of driver? Sorry.
Video controller driver or Wi-Fi driver. They're always part of the kernel. My question is, for example, for your prototype device, if you already ported driver to the user space and you are happy with functionality and performance?
No, I think that Fuse is the main existence proof that this sort of approach is feasible in general. Whether or not it's going to be performant in every case, I think, is going to vary a lot by case. And so we are going to have to punt a bunch of stuff into device classes for, as you say, cases like video or other high-throughput applications. And I think there are a fair amount. There's a fair amount. For throughput, you can do a lot in user space if you're not so concerned with latency.
I think also it's important to point out that, for example, for a video device or a network device, would almost certainly be served either through a class driver or through the Unipro to USB bridge or Unipro to SDIO bridge. It's probably unlikely that someone would build a network device with a special purpose Unipro interface that was not conformant to the class driver. Either it would be an existing networking chip that connected through the bridge. In that case, it does go right through the kernel, and there's no user space driver. Or it would be if it was a Unipro M5 Wi-Fi chip, right? Then hopefully it would be conformant to the not yet existing MIPI spec for those, right? And then could use the class driver. So it's sort of only the case of devices that are not in a sort of not in a defined class, are not using a bridge, right? But also need sort of low latency, that this is an issue, which actually we're interested in sort of soliciting what those use cases are. We've been trying to think of a use case like that, and honestly, we haven't been able to think of one. But if the group of us all here can think of some use cases in that area, we'd like to know.
Okay, and another question right here.
Sure. Can you talk a little bit about how the drivers will get provisioned when a user buys a module?
Yes. So we expect that, okay, there's a bit of a bootstrapping problem in the case of modules that provide network services. But in other cases, we think that there will be a mechanism very similar to the way that the Play Store works now, where when you install your app, there's a set of supporting server infrastructure that lets you get any drivers or any additional module-related software configuration that's going to go along to support it. Yeah.
We have a couple other questions that were earlier, maybe more directed towards Jürgen, but I'm just going to ask them because we're one team, and you guys might be able to get into these. So MBG asked earlier, if it's possible to set up an assured pipeline between two modules. So the scenario they give is, for example, someone develops a VPN module for connecting their VPN concentrator, and you can assure that all traffic from Android goes through that module before going to Wi-Fi or to 4G. Is that something that you guys have any thoughts on?
It's certainly possible if you trust the switch, if you trust the supervisory controller.
Yeah, that is supported by the network architecture. Yeah.
Do you trust the switch?
I trust the switch.
Okay. Okay, here, let me ask another question that maybe Jürgen will jump in on here. So is there a way, and the usernames here is Andrew Ara Crew, David Ara Team, Jason Ara Team. Is there a way to remotely access data from DRAM of one EP to DRAM of another EP, like RDMA?
I think we're not expecting that the RAM would be in a separate module from the processor that was accessing it, just because the latency of the network is low. It's a few microseconds, but it's not in the sort of tens of nanoseconds range that you would want for that use case. I think certainly if you have information on one module that another module wants to get, of course you can transmit it. But in terms of having shared memory between processors on different modules, I think we're not expecting that the platform is going to be really capable of that.
That's kind of an architectural consequence of Unipro not being a memory-mapped communication interface.
Okay, and we have a question over here.
Yeah, we're seeing Android running on a myriad of devices nowadays, on cars, fridges, everything. It sounds like Project Ara is an attempt, in part, to make Android run on a lot more things, a lot more easily. Would you guys be able to comment on what Ara might mean for the Android ecosystem outside of Project Ara?
So we're pretty excited, just personally. I think I'm personally excited personally about the idea of being able to do a project, right? Starting with one of these phones and making a custom module that makes it the controller for some other device. I think that'll enable all kinds of sort of small volume, cool stuff to get built, and might make it get built with an Android, Android-based UI. So. I'm not sure if that answers your question or not.
Yeah, because almost thinking figuratively a little bit, if you can get Android to run between all these blocks, perhaps you can get Android to run on blocks that aren't part of the Ara phone wirelessly to other devices and such, if that makes any sense.
Yeah, it's a natural scenario. It's one that kind of Paul had addressed earlier today, that while those things get us excited too, that we're really focused on making a great phone. And you can see that there's other efforts across Google, such as Android Wear, to really think about tailored scenarios where we want to make sure that hardware and software work well together. So we get excited about those, but we're not making any promises or any kind of commitments to really focus outside of that core scenario for now. Okay, we got another question over here. Go ahead.
So have you guys thought of a scenario where one sensor is used by multiple apps, and like there could be some issues of like they sharing data between multiple apps for one sensor only? So that is like a sensor for like measuring sugar from the blood samples, and there are a couple apps trying to use the same sensor. So maybe there is like conflict, maybe not. Somebody wants to like proprietary log their sensors only for their apps. So is there any like concerns or something?
Let's see, so locking to a particular module vendor app is not something I had personally considered. I think that to answer your more general question about like contention between apps, I mean, you could think about like audio being a shared resource that's presently, different apps are going to contend for it. Maybe you get a phone call while you're listening to, music, and it seems like this is kind of a solved problem. The system services are always intermediating between apps and hardware, and so they can control access and arbitrate.
Marty, in this case of sensors, there's the sensor API, right?
Yeah, and exactly. To address your question specifically, yeah, there's like a sensor service which distributes sensor events, to any set of interested apps.
Okay, that makes sense.
Yeah.
All right. Well, thank you, gentlemen. Awesome. Well done, Marty and Ara.
Thank you.
Fantastic. Okay, I just wanted to give a quick shout out to Kyle Carpenter, who online submitted his paper tower within the appropriate timestamp, and he used a very simple approach, and he is our online recipient of kind of one of the first Ara phones. So congratulations to Kyle. Okay, we're down to our final couple of sessions for today, and we're going to talk for a little bit around certification and kind of environmental concerns. And then we're going to wrap it up with some licensing. So I want to bring back Elwin back to the stage, who's going to talk about environmental stuff. And while he comes up, he was actually in an earthquake in '94 in LA when everything was going around him. So he has a very personal desire to make sure that our Ara phones can withstand crazy stuff like that.
Well, maybe not earthquakes, but yeah. All right, thank you. So I want to go over the environmental specifications of the MDK, but more generally I want to talk about environmental testing for modules as well as touch on the certification, both for the regulatory certification and what we see as what would be needed for entry into the module marketplace. Where's my clicker? So the goals of the environmental specs are twofold. One, it is to protect the end users, then the modules, and the platform in that order of priority. Secondly, because we are intending this phone for the entire world, we want to make sure that the modules will be able to operate through a range of environments and geographies. So we were part of Motorola, and so we had access to lots of mobile standards and specifications in this area. And so what we are doing currently is trying to figure out how to adapt those best practices to the Ara platform. So we can't just use them outright because we're very different, right? Unlike a traditional smartphone, where essentially you have a one-off device and you can do a bunch of testing on it, we have potentially an infinite number of potential configurations, right? And secondly, we're not just one manufacturer. In fact, we have all of you. So we are currently doing some functional testing on the prototype, and we will adapt those standards and then push out what we learn into the MDK in the future. So when necessary, our strategy is to aim to provide just survivable limits for each of these areas, and then leave the details of the qualifications up to you guys. because inherently you guys will have your own qualification procedures for your companies. But in the case that if you don't, we will also provide reference implementations, which are essentially test procedures that demonstrate compliance. So let's get started with thermal loads. So thermal loads are very, very important on the Ara platform. So heat generated from components in a module either travels up through the module shell into the end user, which is bad, or it goes down through the PCB into the endo and spreads to other modules. So in the prototype, we control thermal loads by essentially setting limits on the average power that a module can get. In fact, there's a 2 amp current draw limit for any module. We envision, however, that in the objective platform, that we would have a much more sophisticated active thermal management system. So we've begun some preliminary analysis on trying to understand how heat dissipates on the phone. We have looked into trying to put together an active thermal management system with a thermal controller, with a bunch of thermal sensors, both in the endo as well as potentially in the modules. We've looked at other ideas like a heat transfer system whereby we essentially move the heat source or heat from a major heat source away from that module into other areas of the phone. We're also thinking of potentially involving the user, right? So if you have a phone configuration where 2 very active and very hot modules are placed right next to each other, we could send a notification to the user and tell them, this is not an advisable configuration, please swap your modules. And then lastly, we have looked into the fact that you can potentially use diversity from inherent in your set of modules to reconfigure the phone on the fly. So as an example, if you had an LTE module and a Wi-Fi module, and if one of them were to get really warm, you could turn it off and then essentially just use the other one. So the next slide is electromagnetic interference, EMI. So ultimately, here we want to ensure that modules don't interfere with one another. Right? And we have several approaches to this challenge. The first is that the MDK specification requires all modules to have a safety shield to cover essentially all the electrically active components on the PCB. Now, this serves 2 purposes. One, it prevents users from accidentally touching the sensitive components on the PCB, but it also provides a very convenient Faraday cage. So we've actually specified that the safety shield should be made of, I think, nickel or some other functionally equivalent metal. So when we talk about EMI, we are concerned about radiative coupling. And to an extent, regulatory requirements provide us a convenient baseline on which to use for our own requirements. But we really have to look beyond these radiative coupling limits because we have modules that are operating essentially very, very close together, centimeters apart, right? As you've heard, we also have this contactless, high-speed contactless data interface that uses both capacitive and inductive coupling. And then to top it all off, we have electropermanent magnets. So as you can imagine, this is Maxwell's soup in this very, very concentrated and tiny region. So what we've done is we've been working to model and understand the EM environment within our phone. We're also in parallel looking at ways to develop both non-emitters and emitter modules. So Derek Linden, in fact, from X5, will give a presentation tomorrow on how we intend to do RF modules. Of course, all this, once we've learned more, we will flow down what we've learned into requirements and push that out in future MDK releases. Next up is SAR, specific absorption rate. So this applies to emitter modules. This is the level of RF energy that an end user can receive. And it's strictly set by regulatory bodies around the world. I am here to say that the ARA platform provides no additional requirements beyond those that are required by current regulation. Next up are environmental specifications that relate to effects on the modules. So starting with ambient temperature and humidity. So the MDK currently provides this table and lists them, has them as operational limits for the prototype modules. That is strictly not correct. These numbers actually correspond to the maximum range for an accelerated aging test using this thermal cycling profile you see here. They're not meant to be operational limits. So we've received a lot of comments, in fact, on this in the forums. This is exactly the type of feedback we want to get from you guys. We flagged it, and I personally will be looking into it and providing further clarification in future MDK releases. Next up is electrostatic discharge, ESD. Here we have pretty wide consensus on an industry standard. And so we use the IEC standard as well. It specifies the discharge rates as well as the processes and the configuration for how one does ESD tests. So the exact discharge locations are currently TBD'd, but you can guess that they'll be around areas between part lines, right? So between the module base and the module shell, and in other sensitive areas like the interface blocks. Next is vibration. So vibration ensures that we have structural integrity for components within a module and between the various subassemblies. These are some very typical test specifications for that. You essentially put your module or your device on a shaker table, shake it in each axis for 5 minutes using those parameters. Finally, we have shock or the drop test. So I'm going to say first and foremost that we are concerned as well about modules breaking apart or the phone breaking apart and the modules flying out of the phone when a user drops it. So we're working currently to understand what that looks like in a real functional prototype. And so whatever we learn, we're going to feed back into our design of the EPM and on specifications for the drop tests. So industry standard for drop tests is between 3 and 5 foot. So we've chosen 4 foot as a starting point. There are, of course, various ways in which one can perform this test. Orientation of how you orient the modules. We will probably have to do a test where the module is by itself and when the module is in a phone. And then, as you can see here, this is a human-enabled test, but perhaps there will be more. There'll be an opportunity to do some kind of robotic assist on these tests. Next up, I want to share some initial thoughts that we have on how regulatory certification might work for our modules. So We envision that you, the developers, the module developers, will be responsible for certification of your modules with some assistance from Google. So when you have a module ready for regulatory approval, you will apply to the regulators yourselves. And for example, you would get an FCC ID for your device. Then Google will supply you with two things, with one of two things, right? We can give you a high fidelity computational model of the phone, and you will use your corresponding high fidelity computational model of your module, and then using that, you can perform computational analysis to figure out what the worst case conditions are in terms of EMI and SAR. Similarly, in a more traditional method, we'll give you an endo, a test endo with some test modules that, again, simulate worst case RF conditions. And then you plug in your module, figure out, what are the interactions between these other test modules, and see what the worst cases are. You can use, for example, a near field rapid scanner to help you do that quickly. Once you figure out what the worst cases are, then you take the results to an accredited lab where they'll probably want to do more tests and then submit the results for approval from the regulators. And finally, so the details of the module marketplace are still being worked out, but as a condition to entering the marketplace, we think there will be some minimal certification required. And so this chart includes a laundry list of all the types of data that we think you might need to provide to Google. So starting on the left side, these are items that pertain to the fact that you will have a business relationship with Google. So you'll need a digital signature to verify that you are who you are. You'll have a reputation score on the marketplace, which is informed by consumers. You'll have some sort of customer support back-end interface so that consumers can know who to call when they have a problem with your module. Second column is tech data package. So these are electronic files that you will submit. So drawings, manufacturing, and QA processes. If you have specific userland drivers, shell geometry and antenna geometry. So not every module will have this, of course, but if you do have a custom module shell, you'll have to submit drawings for that. And then lastly, performance specs and compositional rules. So compositional rules are if your module has can only fit at the top of the phone, things like that. We also envision that you would send actual engineering samples to Google as well, and then we would take those engineering samples and run a bunch of tests on it to verify quality and spec compliance. So the first thing we would do is probably just to verify that your module meets geometric constraints that we've set. For example, your module actually fits into an endo. We'll verify that the EPMs have the sufficient hole strength. We'll do a voltage and current sweep, and then do a bunch of tests to exercise the network stack and the Android and software stacks. And then lastly, we'll probably do some version of all the environmental tests that I previously went over. And lastly, the last column is a set of artifacts if you intend to use the metamorphosis models and tool suites. And these are some of the artifacts that they require. So if you do that, then we will have essentially a formalized model that is equivalent to your engineering samples. And this could help speed up a lot of the certification efforts. So I think that is it for me.
All right.
Questions?
Elwin, thanks so much. That's great. All right, we've got a question from IRC. This is from RAM. They show drop/shock test for a phone. What if there is a bad module design which cannot withstand the drop shock of the phone? Are there guidelines on drop test on those particular modules?
So as I said, we're still trying to work through how a shock test would work in our platform. And so once we do perform a test on the functional prototype, and we'll be able to answer that question much better.
Okay. And then Jürgen's fan club is looking for him. Will Jürgen be there tomorrow? Will Jürgen be there tomorrow?
Jürgen will be here tomorrow.
So Jürgen, you are in demand. Let's see what other questions we got.
Easy question. Come on.
Oh, I got a question from Twitter user Ermenko_Paul. Did you mean to say the contacts are coated with nickel or nickel-plated steel?
Sorry, they are nickel-plated steel.
Okay.
Yes.
That was a totally random question from the internet.
Nickel will probably not be good.
Yeah.
Right,
Yeah. Okay. That was great. Okay. Those are all the questions we got, but we got a couple of folks in the room. Go ahead.
Hello. Let's make an assumption that somebody's trying to submit a module that is like, for example, super sensitive sensor, which doesn't meet, for example, vibration requirements.
Okay.
But like it doesn't meet it because it cannot, like due to its purpose, like it has some details or something like this. So would you approve this one, or you'll reject it because it doesn't meet the requirement?
Yeah, I think we're working out the exact nature of how that certification will work for the marketplace. But I would hope that we would make conditions available for special cases.
So then I have the next question, which comes out of this. So these will be like individually, or like you'll test each module individually. It wouldn't be like automatic. So like some are getting.
Yeah, we totally envision all the, at least for the Google certification part, to be completely automatic. That we get the samples in, we'll place it on some sort of rig, and all the tests will be completed automatically. Especially when we get up to hundreds and thousands of modules, it's going to be impossible to do this manually.
Okay, thanks.
All right, let's go over here.
Yeah, just one point of clarification. I mean, normally when they build a phone, the phone is certified, for example, by the FCC as a complete unit.
Right.
Now, are you saying that every module, whether it's an emitter or not, I mean, obviously there will be some level of emission from any digital circuitry or what have you, but you're saying that every module has to be independently certified, say, by the FCC?
So let's be clear, right? So currently, there are various ways in which the FCC provides equipment authorizations, and so non-emitter modules currently are just digital devices, right? And you don't need to go to an accredited lab to get it certified. You can do that through a verification process. Right, and the same would apply to our modules that aren't emitters, right?
Okay, so it would depend on what class of module
but the device is at the module level, right? So that's the distinction, I think, that you were trying to get at.
Okay, thanks.
You have a question over here?
Yes, will users be able to plug in modules that don't go through the certification process? Say they buy something from SparkFun as a development kit or something. Will they still work or is there going to be an interlock that prevents non-approved modules from going in?
That's a great question. I think as a whole, we want to. I mean, there's you know, there's this spirit of making, right? And that's throughout this project. That goes throughout the vein of this project. And so I think that would be something that we would want to support, right? So that people at home who want to make a module for their own use, right? And that, by the way, is a specific exemption from the FCC. If you make 5 or less and you don't sell it, you don't have to care about the FCC at all. So in those cases, yeah, absolutely, I think we want to support that kind of effort.
What's the difference between Android, where you can load your own apps, or an iPhone, where you have to go through the Apple Store? So I'm hoping, yeah, this will be the same.
All right.
Yeah.
Paul, any color to add to that answer? No, you're good. All right, cool.
I'm Joseph.
Oh, hey.
Do you have any future plan for FDA certification as a medical device, something like that?
Yeah, actually, originally we were planning to release some initial what do you call it, guidance on FDA certification, but we pulled back because we're still trying to figure out what it is we should say in those areas. So stay tuned.
Cool. A couple other questions popped up on IRC. So PF420 says, the certification process sounds expensive. Are there plans to offer discounts or additional assistance to startups or academic customers?
Well, which certification effort?
I don't know, the process.
Okay, so the regulatory certification is no different for the Ara platform as with any other device, right? So they don't incur any additional costs there. For the module marketplace, those details are to be worked out, but I think at least for the computational models that those would be relatively inexpensive. I think we would make those relatively inexpensive. So.
Okay. And then the other question that popped up from Smadger on IRC is, okay, so how will refunds work through the marketplace for faulty modules?
That is beyond my expertise. Sorry.
Okay. It may be too early to even address that, I think, as Paul indicated earlier. What really ATAP is focusing on is developing...
All modules will just work. They will never fail.
That's right. There'll never be anything that doesn't work.
Yes.
But clearly that's something that...
That's going to be a requirement in the MDK, actually. Yes.
Yeah.
Yes.
So, Paul, anything to add to that? Okay. Okay, great. Well, Elwin, thank you so much. I appreciate it. Good stuff. Okay, so our last speaker, but definitely not the least, is Stephen Hahn, who is our legal counsel at Google. And the interesting thing about Stephen is that he is probably one of the top 100 people that understands the life and the experience and the history of Genghis Khan. So, Stephen Hahn, Genghis Khan.
Hi, everyone. My name is Stephen Hahn, and I work in the legal department at Google. Super excited to be here. This is one, if not the most exciting project here at Google. It's been a real pleasure to work with Paul's team. Having said that, I realize that we are minutes away from the happy hour, so my presentation will be extremely brief. I just had two quick goals in this session. One, to describe the licensing philosophy behind Project Ara, and two, just briefly walk through the key components of the license agreement. No presentation given by a lawyer would be complete without a disclaimer. And here it is. The information presented today is not provided in the course of and does not create or constitute an attorney-client relationship and is not intended to convey or constitute legal advice. Please refer to the MDK license agreement text available at projectara.com. To state the painfully obvious, I am not your lawyer. I'm Google's lawyer, but we're all working together. Project R is built on a permissive licensing regime to foster a hardware ecosystem to drive innovation and deliver the mobile internet to the next 5 billion people. It's free and accessible to all developers and informed by the Android multi-sided platform model. You know, there are really two goals. The first goal was, the initial goal is get as many great developers into this system as possible. But we have to balance that with creating a governance structure to drive quality interactions in the ecosystem. And the way we sought to achieve this is through the MDK license agreement. There are really two key buckets to the license agreement. There's one, that Google's grant to developers, the IP grant that Google grants to you guys. And two, what I call the rules of the road for the ecosystem. First, Google's grant to developers. There are two distinct licenses in the license agreement, actually. First, there's the development and testing license, and that's very simple. You get a worldwide royalty-free license under Google's IP in the MDK and the related tech to develop and test modules, full stop. And what's really powerful about the MDK license agreement is that you also get from day one a commercialization license. You receive a license to sell and distribute your modules based on the MDK. So first I want to talk about, yikes. The key, now the keys, what I call the 4 key rules of the road. All right. First, no fragmentation. What do we mean by no fragmentation? It seems vague. What we mean is that if you sign up for the MDK, you will agree not to take the MDK, take Project Ara, modify it / duplicate it, and then create your own Project Ara called Project Kickass. You know, that's what we don't want you to do. If you want to come with us within Project R, we'd like you to work within the ecosystem. If you commercialize meaning if you start selling or distributing modules based on the MDK, there are a couple of other key rules of the road that we're asking everyone to sign up to. First, the injunction ban against other developers. Here, it sounds a bit technical, but all it means is, let's say you are a module developer and you create, I know Paul has given this example, you create the incense burner module. And let's say there's another Mr. Naughty developer out there who creates another incense burner module. And you believe that Mr. Naughty module developer has infringed your IP on the incense burner. Well, what we're asking is that it's your prerogative to go sue Mr. Naughty module developer and get damages for yourself. We're just asking that you don't get an injunction against that developer, because that will freeze the ecosystem. Second, license suspension. This one is this is simple. License suspension for IP claims against Project Ara. If you sue us for an IP claim based on Project Ara or the MDK, we may suspend our license to you. And finally, a limited license back to Google for interoperability. What we mean there is you may have IP that reads on the MDK or the endoskeleton or interoperability of modules and the endoskeleton. If you use our MDK to commercialize your modules, then you're granting a license to us for that IP. I mean, to be clear, you are not granting us IP, any IP in the modules themselves. Of course, that is yours. But we want what is really a license grant back for any IP that you may have that reads on the MDK, the endoskeleton, or interoperability. And so that's it. Those are the key rules of the road. Developer responsibilities. Really, I see you have three. One, user privacy. Obviously, please take it seriously. If you develop modules for end users and users provide you with personal information, you must provide privacy notice and comply with all the privacy requirements that you'd have to, irrespective of Project Ara. And if your modules store personal information, you've got to store that information securely. Second, your use of third-party resources. You should just be aware that third-party resources or applications that you use to develop your modules might be subject to some other third party's IP rights. The MDK license agreement doesn't address that relationship that you might have with that third-party resource or application provider. It's up to you. And finally, indemnification. When you sign up with us and decide to use the MDK and commercialize, you are indemnifying Google for your use of the MDK and any IP claims on your modules. All right? Here, I wanted to throw up this slide just to make crystal clear about, this is a snapshot of whose IP sits where. Developers retain all developer IP in their modules. And what Google retains is all Google IP in the MDK itself, and to the extent it is used in modules. And believe it or not, this is the next to last slide. Beyond the MDK license, I know other presenters have talked about the planned module marketplace. And those details and those terms are being thought about right now and will be ready soon. But basically, you can think of it as it'll be analogous to the Google Play Store. And that's it. Thanks so much.
Right. Genghis Khan, awesome. That's great. This is the only session, of course, that we have no Q&A afterwards. So, okay, you guys, well, listen, we're running a little bit of ahead of schedule, and so what we're going to do is just a super quick activity. It's something that we wanted to do a little bit earlier, and then I'm going to introduce the third member of our team here. Okay, so when you guys signed up to be a part of the in-person or the online conference, we asked you to talk about what module area you were interested in. And we've had some conversations with a number of folks that have been coming over to us and saying, hey, I'm really interested in imaging. And do you know anyone else working on that area? And so what we wanted to do just is a very quick activity where we just kind of identify folks that are working on a particular area so that tonight when we have our social gathering, you know visually who you might want to connect with, to either collaborate with or otherwise. Okay, so this will be super quick. Now, if you're online, we want to involve you as well. If I call out a module category and you want to be known as someone who's going to work on that kind of module space, just hashtag AraDev and also with the category that I'm talking about so that folks on Twitter and elsewhere can kind of find each other. Okay, so super quick, anyone who's working on a communication-related module and you want to collaborate with anyone else, just please stand up just for a brief second. So we got, stay standing. So for communication folks, look at each other. These are the folks you want to kind of hang out with over dinner. Okay, great. How about for medical sensors? Please stand up. Anyone working on medical sensors? Okay, look around. This is the medical sensor posse. Awesome. And then we got a hand back here, Ash. Everyone's going to be popular with you, man. They're going to be trying to get you to give them something. Okay. All right, sit down. And now anyone working on sensors other, which is kind of a vague category, but just other exotic sensors that we really haven't talked about. Look around. Awesome. I see someone standing up twice. You're either making lots of modules or your module is like super multifaceted. Okay, now sit down. And then how about anyone working on batteries or power? Batteries or power? We got some couple of power people. Check out each other. Over here too. Okay. Just a couple more here. How about displays? Anyone working on displays? All right. You're going to make a killing. How about processing and computing? I guess that's like application processors and other, yeah? Okay, you'll be talking to yourself. Okay, how about projection? Okay, how about keyboard and tactile stuff? Kind of input, okay. How about accessibility? Okay. Last two, security and authentication. Anyone working on security and authentication? Look at each other. Yeah, find each other. Sweet. Okay, and then, oh, actually two more. So second to last one is fun and games. Anybody? Fun and games? Controllers? There's somebody back there dancing. There's some fun back there. Okay, and then the last one, who's trying to do some stuff that may or may not be a particular module, but it's really focused on just the software and kind of the OS, kind of system stuff. Okay, great. All right, so you have a quick visual on the folks you want to connect with later on. And for those on Twitter, you can find each other as well, and you guys can look on Twitter and find those folks. Okay, well, listen, we're about to wrap up the live stream part of this. Afterwards, we're going to have some instructions for dinner. I just wanted to say, again, thank you for coming. We're trying to work on an impossible project at incredible speed, something that everyone has told us is we're just not able to do. And with you here, we feel, for the first time, I think, deeply confident that this is going to be possible. And we're really excited to work with you guys. For the online folks, we've had over 2,700 people joining us online, actually. And you guys have been an awesome community of folks. Let's give it up for the online folks. And so tomorrow, we have another series of sessions. Tomorrow, we start the first half of the day all together. And then in the afternoon, we have a couple of different tracks. And so we'll be live streaming the first half of the day for everyone, and the last half we'll be kind of selecting one of those tracks to live stream. Okay, so thank you guys now. So we're done with the live stream. We'll see you guys tomorrow. Have a great time on the line. Okay, now, for those that are local, I want to introduce to you the third permanent member of our team. This is the Jason Chua.